Good morning, sir.
Good morning.
Good morning. Good morning, sir. Good morning. Yeah, there. Hi, Professor Surya. Hi, sorry. Hi, Professor. Yeah. Yeah. Maybe, yeah. Glad to meet you. Yeah.
Good morning. Good morning, everyone. Good morning, sir.
Good morning. Good morning.
Good morning.
Hi, Professor Bala. Good. Yeah.
Good morning, Satish.
Good morning. Good morning, sir. Good morning.
Good morning to all of you.
Sir. Sir, wish you very happy Statistics Day.
Thank you, and same to you.
Hi, Professor Logana.
Good morning. Happy
Good morning.
Statistics Day. Wishes to you all.
Good morning, Loganathan.
Good morning. Good morning, Professor Muralidharan.
Good morning, sir.
Hi, Professor Reddy. Good morning. Yeah. Now the time is, in fact, I am waiting for Professor Balakrishna of Kusat, ISPS president. തുടങ്ങാൻ പോവാ തുടങ്ങിയപ്പോ സമയം കഴിഞ്ഞു പെട്ടെന്ന് സാറിനെ വെയിറ്റ് ചെയ്തോ അല്ല 8:40
Reddy sir, good morning. Reddy sir, good morning.
Yeah, good morning, Muralidharan.
Good
How
morning,
are
sir.
you? Happy
That's
National
fine, sir.
Statistics Day.
Happy Statistics Day to you also.
Thank you.
Jagdish Saran from Delhi. Good morning, sir.
Yeah,
Oh,
good morning. Good morning, everybody.
Jagdish sir. Good morning.
Yes, sir.
Good morning.
Good morning, sir. Good morning.
Good morning.
hello Shubha teacher Shubha
Yes, sir. Yes, I'm here. So, shall we start?
I think we can start the program because not wasting the time. Professor Balakrishna will join in the meantime.
Okay, we shall start.
Otherwise, it will affect the timing.
Yeah.
You
Yes.
can, first.
Yeah.
Yeah.
Okay.
Yeah. Left to you.
Okay, thanks, sir. So, good morning, esteemed professors and dear participants, and welcome to the 5th International Webinar on Recent Trends in Statistical Theory and Applications. A very happy National Statistics Day wishes to all of you. Let us begin this wonderful journey of 4 days by bowing our heads humbly in front of the Almighty in silent prayer for a few seconds. Thank you. I welcome our esteemed professor and convener of the webinar, Dr. Satish Kumar sir, to welcome the gathering, to welcome the esteemed guests to the webinar.
Warm wishes to each and every one on this National Statistics Day. Throughout our country, almost all statistics departments are celebrating National Statistics Day in honor of Professor P.C. Mahalanobis, father of Indian statistics, and for popularizing the power and scope of statistics among the youngsters. We are also joining this celebration through organizing an international webinar on recent trends in statistical theory and applications in a befitting manner. Indian Society for Probability and Statistics, ISPS, and Kerala Statistical Association, KSA, also joined with us in organizing this mega event. Since 2017, our department is celebrating National Statistics Day through or arranging national level seminars or workshops, conferences, etc. in a grand manner. Most of on these years or these national seminars were raised to the level of an international event through the participation of internationally well-known or reputed statisticians and researchers in the area of statistics. Due to COVID pandemic, last year, we held a 3-day national level webinar starting from early morning 8:30 a.m. to 9 p.m. the night. This program received a great attention and acceptance among the statistics fraternity as the first of its kind. Several internationally accepted and well-known scientists, experts in the area participated in that event. This year, we had initially planned a national level event, but it was raised to an international event due to the support and blessings from well-known statisticians gathering in this, through this event. The sessions are scheduled tightly due to the large number of speakers. We are blessed with internationally well-known giants in the area, like Professor Balakrishnan of McMaster University, our Professor Hira Kaul, Professor Jamalamalaka Srinivasa Rao, Professor Ashish Chan Gupta, Professor Kacheshvili, and in fact, several, others. In fact, this list is not complete. We can see the details of these experts in the website. I'm not Professor Thomas Matthew, all are there in the group. Professor David Banks, Professor Richard Burke also joins that group, several. Through this webinar, we wish to honor eminent statisticians, stalwarts in statistics, in the area of statistics, like in fact, it is trivially for Professor P.C. Mahalnobis, especially Professor C.R. Rao, Professor D. Basu, Professor S.N. Roy, Professor A. Mathai, Professor K.R. Nair, Professor U.S. Nair, Professor Sukhatmi. We have certain sessions through dedicating certain sessions to honor these stalwarts in our country in statistics. They have contributed great. I would like to welcome in this occasion to each and every one of you to this event, especially in this inaugural function. In fact, Professor Balakrishnan agreed to inaugurate this webinar. I utilize this occasion to invite Professor Balakrishnan to this gathering. Professor Kalyanaraman sir is our lighting force, leading all the time. Professor Kalyanaraman sir and Professor Balakrishna of Cochin University of Science and Technology, the present president of ISPS, agreed to say a few words in this to felicitate this inaugural function. I welcome each one of you to this gathering. Our Professor Reddy is, in fact, it's a motivation behind me to do this event. I utilize this occasion to invite Professor Reddy to this gathering. And several Professor Hira Kaul, Professor Loganathan sir, and several are there in the Professor Muralidharan and Professor Jagadish Sharan, and several are there. I'm not naming all. I utilize this occasion to welcome each one of you to this webinar and this inaugural function. Also, more than 1,000 participants, registered participants are there to watch these programs via Google Meet, YouTube Streamline. I utilize this occasion to invite each one of them to this event. Hope, in fact, more than that, my colleagues are there. Dr. Sathar, Dr. Manoj, our Yagin Thomas probably will be in the group, and my teachers, Leslie teacher, and several are there probably, I hope, in the group. I utilize this occasion to welcome each one of them, and especially our research scholars and researchers throughout in India to this gathering. Hope we will have a very fruitful deliberations and interactions in the coming 4 days. In fact, here also we tied starting from 8:30 to night 10:10 or 10:30 time. Without having much breaking time, only lunch break time, and 5 minutes etc. only there to adjust the timing. Expecting the cooperation and support from each one of you, my beloved professors, scientists, researchers, for the success of this event. I remain, thank you all, welcoming once again all of you. Thank you.
Thank you, dear Professor. Professor Kalyanaraman sir, the retired professor from our department, is actually a much respected personality among the statistics fraternity. He can be called a pioneer in statistical computing in the Department of Statistics as well as the University of Kerala. An evergreen presence in all our programs, a well-wisher of our department, and a person of extreme repute whom we highly respect, I request Professor Kalyanaraman sir to say a few words of blessing on this occasion. Please.
Good morning to all. It's a very happy occasion to be back in the department after 20 years of retirement and sitting from my house. It's really a very great experience. Quite a few years. Our successors in the departments are doing certain academic activities which can never be explained in small words. Somehow or other, these successors, starting from Satish, Manoj, Satar and others, have designed a particular way of attacking the entire academic activities, and they have a sequence of activities every day which is being repeated at international level, national level and local level. Somehow or other, I happen to be a participant in all these things, even though not in a very serious manner, but as a participant as such. So as part of one of the very important day, that is the birthday of the celebrity Mahal Nobis, which is being declared as the National Statistics Day by the Government of India. They are organizing this seminar in a very big manner this year. And I don't have to describe or narrate the achievements of Professor Mahal Nobis. However, I try to share some thoughts that come to my mind. One of the points which I would like to point out is the selection of the title of the journal, Sankhya, for the journal being published by the Indian Statistical Institute. There is some reason behind it. As far as our Indian thought process is concerned, there are, I'm told, 6 different schools of inquiry. That is Nyaya, Vaisheshika, Sankhya, Yoga, Mimamsa and Vedanta. Mimamsa and Vedanta are systems of inquiry depending more on deduction. And yoga is a totally different mode of inquiry. But the 3 other things, that is Nyaya, Vaisheshika and Sankhya, are supposed to be methods of inquiry using practical side. Because the Vaisheshika, the pramanas, that is the method of finding out something new, darshana they call it, that is already existing, I am trying to understand what it is. So Vaisheshika uses perception, inference, analogy, postulation and cognition and privation. All these things are taken as modes of inquiry and modes of providing evidence for a problem. Vaisheshika turns out to be using only 2, perception and inference. But Sankhya introduces something new behind. So between perception and inference, they introduce pratyaksha pramana, that is experimental material. That is, you do an experiment and try to find out something. So these 3 constituting perception, experiment, followed by inference, is the system that we do in statistics, as I understand. So the reason for putting this name, Sankhya, for the journal being published by Indian Statistical Institute is not without reason. It has its own reasons. And I think that there is an article on that in the second issue of Sankhya, if I remember correctly. So, however, this great school behind the inquiry for unknown subjects, as encouraged by our elders, are being followed by the current generation in a totally different way. So in this respect, I would also like to mention one request. My friends in the department, please understand that Dr. U. Shivaraman Nair was a contemporary for Mahalanobis. At the same time, when the Indian Statistical Institute was started, His Highness Maharaja Chitrachitarnal Balarama Varma of Travancore created a Central Institute of Research, Central Research Institute, with statistics, aquatic biology and English as the departments, which later merged into the University of Travancore, which later turned out to be the University of Kerala. Hence, I would request my friends in the department to organize a seminar at the time of, on the day of birth of U. Shivaraman Nair also in future. Please think in these lines. That would be a major achievement that we will be doing the sequence. So with this, I am very happy to see major celebrated professors in statistics. Even though I am just crossing 80, I am not just leaving statistics, at least from the point of knowing new things that are happening over the last 4 days. It was really an experience for me. That is, Professor Balakrishnan spoke on 4 different topics. I don't know how he gets the time for doing all these things. And one of the major finding what I could see was whatever that he observes, he converts it into a problem. I do not know how he gets this idea. And yesterday he was saying just because of an accident, he could produce at least a dozen papers. And that's something that every student should understand and see for themselves how to go behind it. However, it's a very great occasion. I am very happy. I'll thank my friends for giving this opportunity to meet all the celebrities in the world as such on this day. And I wish the function all success and all my blessings to those who do these exercises in the department. Thank you.
Thank you, dear Professor. I would now like to welcome Professor N. Balakrishna, a professor in Cochin University of Science and Technology, who is the current president of ISPS, a visiting faculty of the Department of Statistics and Actuarial Sciences in Waterloo University, as well as a visiting scientist in the School of Mathematics and Statistics, the University of Birmingham, England. Professor N. Balakrishna is a person of high esteem in the field of statistics. My professor too, I humbly welcome him to say a few words on this occasion. And we thank you, sir, for conducting this program along with the Department of Statistics, University of Kerala. Professor Balakrishna, sir, please.
Okay. Can you hear me?
Yes, we can.
Okay. So, good morning to all delegates from North America, in India, and good evening to all the delegates from North America. Nice to see all great personalities on the screen. I'm not a person to give long speech, but this is a good occasion to remember one of the great visionaries our country has seen, Professor P.C. Mahalanobis. And as you know, as already mentioned by Professor Satish, Government of India started or declared this 29th June as the National Statistics Day to celebrate his birthday. It's a good honor to him. And Professor Satish has been organizing this annual conference almost every year since I think 4 or 5 years. This year, because of this pandemic situation, we thought the ISPS Executive Committee felt that it may be a good idea to join the Department of Statistics, Kerala University to organize this conference. So they have agreed to this proposal, and first of all, I thank Professor Satish and his team for giving an opportunity to ISPS also to join them and celebrate this occasion. And on behalf of the Executive Committee of ISPS and all the ISPS members, I wish all of you a very happy National Statistics Day. And I wish that the conference, the next 4-day webinar is going to be very successful. And I wish you all the best. And thank you very much for this occasion.
Thank you. Thank you, dear Professor. Now we are reaching the important part of this program, this inaugural session, that is inauguration of the webinar series. Professor N. Balakrishna, a distinguished university professor in the Department of Mathematics and Statistics, McMaster University, Canada, needs no words of introduction among the not just the statistics fraternity, but among the scientific community of the world. A postdoctoral fellow from McMaster University. Actually, his accolades are many. He was a visiting professor and in various universities around the globe and has received so many honors and memberships, including the elected member of the International Statistical Institute, fellow of the American Statistical Association, fellow of the Institute of Mathematical Statistics, fellow of Turkish Statistical Association, so on and so on. I think he's one of the legends in statistics that is among us now. He's also the editor-in-chief for reputed journals like the Communications in Statistics Theory and Methods, Communication in Statistics Simulation and Computation, Communication in Statistics Case Studies, Data Analysis, Applications, associate editor for so many internationally reputed journals, and actually a true statistician. As Professor Kalyanaraman sir rightly pointed out, I think he's a person who can convert everything around him into statistics. As sir was saying, actually we were astonished when we heard his talk in the last program, when he was saying that the accident that he had gone through has created so many thoughts in his mind, which is a surprise for students in statistics like me, because it's actually, we are extremely privileged to have your presence and blessings in our functions, and we find ourselves extremely honored to be among you, among people like you. I invite you to inaugurate this session, and we are waiting to hear your honorable words. Please, sir.
Thank you. First of all, I wish to express my sincere thanks for inviting me and allowing me or providing me an opportunity to be part of this National Statistics Day conference in honor and memory of Professor Mahalanobis. I first want to start thanking Dr. Satish Kumar and his colleagues. I have been giving lectures for the last 4 or 5 days, and this is the final one in the series. And it has been a great pleasure to present talks to the department, the colleagues, and the students, and have some interesting discussions following that. Today, I noticed that the participants are from all over the place, all across India, and also some from abroad like us, like me and Dr. Hiralal Kaul. We are close to midnight now. It is 11:48 here. I think COVID pandemic has put a serious dent in academic activities, because many conferences, workshops were cancelled for the last 16 to 18 months for good reason. But what is important is that people do not give up on having meetings, and it becomes all the more important to have events like this, precisely like a webinar, for two reasons. One is that the academic interests and discussions are kept alive. And the second one is usually a delay or a lull over a period of time can impede future growths in the field. People lose interest, people lose the momentum. Research is based on momentum. Once you stop, it is hard to start again. So events like this is very important. The other thing I noticed is I read an article in New York Times. It reminds me of this event in the sense that the New York Times had an article which says that there are a lot of bad things that happened during COVID pandemic, but a few good things happened. And one of the good things that they point out is how people adapted to running events, having meetings, successful conferences, etc. online. 2 years ago, none of you would have imagined taking part in an event like this completely online and having access to all the people from across the world at your disposal. And that is a good thing that has come out. And it is good that Kerala University, headed by Satish Kumar and his colleagues and students, have taken this initiative to put this event together, one among many events that they have successfully organized. And I have taken part in a few of them. I can say and vouch that the events are well organized, well planned, and has tremendous academic merits. So I am looking forward to this one. And with great pleasure, I inaugurate this webinar today, this morning, on the National Statistics Day. Thank you.
Thank you, sir. We are always obliged to people like you for supporting us in all our events, because it is your support and your blessing that turns everything into success. So thank you once again, sir. We have actually reached the end of the inaugural session because we are tied up for time and we have to swiftly go into the technical sessions also. So I would just like to say a few words of heartfelt gratitude to all the esteemed professors, all the great personalities who are a part of this program, who are a part of the journey of our department into maybe higher levels of success. And I would like to thank Dr. N. Balakrishna, Professor Kalyanaraman sir, Professor Loknath sir, Professor Balakrishna sir from CUSAT. I think both the names are same, so that is why I'm adding the department also. And all the other reputed professors who are present here, and especially a special word of thanks to ISPS and the Kerala Statistical Association for joining hands with the Department of Statistics joining hands with Dr. Satish Kumar sir in organizing this program. Once again, I extend a heartfelt gratitude to one and all of you, all the reputed speakers who have agreed to be a part of the program, all the participants who had so willingly and so taken part in the program with so much interest. And I think once again, a word of thanks to all of you. We will end the official inaugural session and we'll swiftly go into the technical session, which is a keynote address by our esteemed professor, Dr. N. Balakrishna sir. I would like to request Dr. Kalyanaraman sir, who is the session chair of the program. This is a special session in honor of Professor P.C. Melanobis. I request Professor Kalyanaraman sir to invite the keynote speaker, Professor N. Balakrishna sir. The topic is random sum Wilkinson statistic and its applications to analysis of ROC and LROC data. I request Professor Kalyanaraman sir to please take up the position of chair for the session. Thank
you. Dear friends, again, it's a great occasion, honor that I get to chair a session in which Professor N. Balakrishnan will be delivering a lecture on random sum Wilcoxon text statistic analysis of ROC and LROC data. My association with Professor Balakrishnan started in the late 80s in Asia until I came to face with him 3 years back in Trivandrum. Late part of 80, I came across an article in American Statistician. I don't remember the title, I think it is some art of statistics, where I saw the name N. Balakrishnan, then thought that it should be someone from our area. Because this Balakrishnan is a name which is specific to Kerala and Karnataka rather than Tamil. But later I came to know that he is from my place itself. So from that day onwards, I started seeing his name in so many other papers very regularly. Then by the time when Dr. R. Pillai generated a distribution called the Methodological distribution, which happened to be a long tail distribution, I was just thinking about some methods of estimation of parameters. Then I came across a paper by Dr. N. Balakrishnan, I think it should be in IEEE, on the estimation of location and scale parameters in extreme value distribution or something like that. So if I remember, because I lose my remembrance very slowly, and I remember that the journal was not available in the department. So I went to the Engineers Club, which is available in Trivandrum. They used to get this IEEE very regularly. So I remember that I had seen this. Also, I remember another paper which I was very interesting. Is a characterization of exponential distribution using something like conditional independence or something like that. If I remember correctly, I do not know whether I am speaking correctly. So this is to say that I am associated with you for a long time in absentia, but only very recently we came to know each other in person. And it's a great occasion, and I am very happy to be part of the seminar in chairing the keynote session where Dr. N. Balakrishnan will be delivering his lecture. I now invite Dr. N. Balakrishnan for his lecture.
Thank you very much, Dr. Kalyan Raman. I appreciate it very much. Your kind words, which shows your generosity in terms of words, and I don't think it justifies in my case. Today I'm going to talk about a topic. It belongs to non-parametric statistics. And I chose this topic because this is some phrases of this everybody knows. For example, a Wilcoxon statistic. Even introductory statistics students see Wilcoxon rank sum. And some others may know what is a ROC data. So that is why I chose this topic. I am going to make it into a full screen. I hope it is visible to everyone. Is it clear?
Yeah, Professor, it is clear.
Okay. So I'm going to talk about a twist to Wilcoxon statistic. And in the process, I'm going to point out that Wilcoxon statistic is used quite often in medical statistics wrongly. And that is something that started making me think about how to do the non-parametric analysis with Wilcoxon statistic, but in a correct way. And I will point out what is wrong and what is a correct way to do. This is a collaborative work with Larry Tang from George Mason University in Virginia. We met in one of the JSM, we started discussing, and this paper and the subsequent paper, which I'm not going to talk about, came out of that meeting. So here is a roadmap of what I'm going to talk about. I will first introduce the problem, then I will state what my objectives are. So I will introduce what is a common form of Wilcoxon statistic that people know from non-parametric literature. And what is the problem? The problem is that common form of the Wilcoxon statistic is wrongly used in many cases. So I am going to modify the Wilcoxon statistic, and that is what is random sum Wilcoxon statistic in the title. And then it can be applied to different types of diagnostic data. The different types of diagnostic data are the ROC and LROC data that I mentioned in the title. Before I apply it to some data, I will use some simulations to show why the modification that I discuss is important and necessary. Then I will take two illustrative examples. One is a LROC imaging data. The other one is a cancer biomarker data with a limit of detection. I will explain all these things. Finally, I will conclude there are lots of open problems in this area, but the mathematics is quite tricky. So, but still one can carve out some nice research problems from here. So we all know what is a Wilcoxon-Mann-Whitney statistic. It is a commonly used distribution-free method for the comparison of two groups. It is the sum of ranks of all observations. So what you do is you have two groups of observations, call it as X sample and Y sample, pull them together, then rank them, then you sum the ranks of all those observations that come from group 1. In the case of ties, the statistic has to be modified. Suppose there are two values, both the 13.6, and if they take the ranks of 12 and 13, you will give mid-ranks. Mid-ranks means if there are two observations with ranks 12 and 13, you will give 12.5 and 12.5 to both of them. Those are called mid-ranks. So the use of the Wilcoxon statistic, the most important use of the Wilcoxon statistic assumes that the sample sizes for the two groups are fixed. So if I decide to take a number of observations from X, number of observations from group 2Y, the number of observations that I take, M and N, should be fixed. And if it is not fixed, then you cannot use the Wilcoxon statistic in its form. Unfortunately, this is where a lot of the medical research goes wrong, because in many cases, as I am going to illustrate, the sample sizes are not fixed, it's random. Then they just pretend these random numbers are fixed numbers, and they use a Wilcoxon statistic, in which case the conclusions drawn can go wrong. However, this is violated in some of the applications. That's what I'm going to talk about today. One application is a medical imaging study. Medical imaging studies usually use either a human person or a computer algorithm. For example, CT scan. CT stands for computer tomography. CT scan. It is an observer to identify a lesion location. You have a cancerous growth, a lesion, and to identify a lesion location on every image. And then this computer algorithm will give a rating to the image. For example, if somebody is diagnosed with some form of cancer, then they will say that, oh, it is stage 3 cancer, stage 4 cancer, stage 2 cancer. And that is done by the medical imaging study. It may be a human person involved as an expert. Quite often they go with the computer algorithm, and the CT scan is one of the examples. And they give a rating to the image according to the belief of lesion existence. So the data that you get consists of ratings of a random number of abnormal images correctly identified by the rater. So for example, if the rater is a medical doctor, one who can read the scans, you give 30 scans and tell them that can you identify a lesion location. Even though you have given 30 scans, not all 30 scans have a lesion location. So what he will do is he will look at the scan and he will circle one of them and say, this could be a lesion. He will go to the next one and it looks normal. He will go to the third one and he will circle somewhere else and say, this could be a lesion. At the end, you may get 21 scans, but that 21 is not a fixed number because you started with a fixed number of 30, but a random number of them gets identified by the rater. So the ratings is not a fixed number of ratings. Such examples can be found in studies involving mammogram. So women go through mammogram scan, and the scan is given to a computer algorithm or to a human rater. And if they are given 100 scans, the human rater may come back and say that, oh, there are 17 that look suspicious. So that 17 is a random number. Even though the 100 scans are given, the data finally you get is a random number of observations. And also you have PET scans. A PET scan in human liver or lung tumor screening. PET scans are very common. If they suspect you have breathing problem, they do a PET scan. Once again, they want to see whether there are blockages and or there is some growth in a human liver. And once again, the random number of scans is what is going to be identified. And there is a data. There is a paper in 1991 in Statistics in Medicine by Seltzer et al. When I read this paper, I got interested because they were using non-parametric statistics, but they were pretending the random sample size was actually a fixed sample size, which is not correct. That is what perked my interest to modify the Wilcoxon statistic. Seltzer et al. Considered a radiologist's performance in reviewing liver computed tomographic images. So that is a CT scan. In this study, there were 46 normal CT images without lesions and 46 abnormal CT images in which they simulated tumors. So what they wanted to do was to evaluate the performance of a radiologist. How good is this radiologist in assessing the CT scans? So they gave 46 normal individual CT images and they artificially introduced tumors in 46 other CT images and presented it to a radiologist and asked them to evaluate. The observer was told to specify the most suspicious location and give a 6-category rating to the location, 1 to 6. Since each image has only one rated location, the rating of the location is used as the rating of the associated image because there is only one location. So I'm going to first give you the data. Table 1 gives the ratings and localizations on liver CT scan. You see here the ratings 1 to 6. You see here there are abnormal images and normal images. And the normal image, there were, how many were given? They were given 46 normal images. Out of the 46, the person actually rated 19 of them to be rating 1. That means it's a very small possibility that there is a lesion. 6 is the highest rating, that there is a very strong evidence there is a lesion. You notice that he did a very good job, he or she did a very good job with normal images. And the 19 of them, he said that there is not much evidence towards lesion, which is true, but all of them had no lesion. But he identified 8 of them had mild lesion, 8 of them had moderate lesion, etc. This is one error. The other error is there were abnormal images. The abnormal images had lesions deliberately introduced by simulation in the program. And he correctly identified, once again out of those 46, correct location 3 times when the lesion was small. But when the lesion was small, he wrongly identified the location 9 times. But when the lesion was large, he correctly identified the location 6 times and he wrongly identified the location 2 times. So now you have to use, if I have 2 such people who are evaluating, which one is better? I have to use a Wilcoxon statistic to assess. If I want to compare his success rate among normal images and abnormal images, I have to use a Wilcoxon statistic. It's a 2-sample Wilcoxon statistic. My question to you is the following. Do you think that the sample size that you get, suppose you look at here, I have 3 plus 3, 6, plus 6, 12, plus 5 is 17, plus 6 is 23. 23 of them he correctly identified the location, 23 of them he wrongly identified the location. So my question to you is, do you think that the two sample sizes are 23 and 23, and will you use a Wilcoxon statistic? Obviously it is wrong, because these numbers that you get here are random, because he is assigning, but you don't know beforehand how many he is going to correctly identify, how many he is going to wrongly identify. And that is what I mentioned here. As mentioned earlier, since the number of correctly localized abnormal images is random, the usual Wilcoxon statistic cannot be used in this case to summarize the performance of the observer. So I cannot use the Wilcoxon statistic to compare how well he identifies the lesion location in abnormal images compared to the normal images. So we need to introduce a random sum Wilcoxon statistic that is particularly useful for analyzing this type of data. And so there are limitations in the use of the usual Wilcoxon statistic for other types of diagnostic data as well, not only random sample size. For example, it is used to evaluate the accuracy of markers in marker studies when a marker is measured on both the diseased and non-diseased patients. This is presented in the book by Zhao, 2002. The magnitude of the Wilcoxon statistic indicates how accurately the marker can distinguish the diseased groups from the non-diseased ones. However, in some of the studies, marker measurements have zero values, not because they have actually zero value. It is because there is a limit of detection. It is like I tell you, go to the nearest lake and measure how much of mercury is present. Every measurement tool will have a limit of detection. If it is below 0.0005 per million parts, the measurement scale will tell you that it is not present, it is zero. It is not actually zero, it is just that it is below the minimum threshold value, below which you cannot identify what the true value is. Non-zero values, which are the actual observed values. Actually, there is a paper in Statistics and Medicine by Wexler et al., where they say that in many measurement scales, that there is a limit of detection below which you always get a value of zero. For example, in environmental pollution data, etc. So this results once again in random numbers of actual measurements, which means the usual Wilcoxon statistic cannot be used once again, because there will be a random number of zero values. So what you are left with is non-zero value, which is a random number. Still, if one were to use the Wilcoxon statistic for the comparison of the two groups, close your eyes, say that I'm going to pretend the two sample sizes are fixed, do the calculations, but what would happen? In this case, the type 1 error that you fix of 5% may be seriously violated. I will show you the simulation results later. Instead of a 5% level of significance, you may end up with a 1% level of significance. You may ask, what is wrong with that? It's still 1% below 5%. If it has 1% level of significance, the true power may be abysmally low. So that's the price that you pay if you use the Wilcoxon statistic. So the objective is to define a random sum Wilcoxon statistic for the comparison of two groups whenever I have random sample sizes. Then you know that the Wilcoxon statistic has asymptotically normal distribution. Typically how that is done is you use U statistic idea to prove the asymptotic distribution is normal, or you use the theory of ranks from Lemon's book. Asymptotic theory of linear combinations of ranks is normally distributed. You can come up with asymptotic properties. I can prove asymptotic normality for this random sum Wilcoxon statistic, and I can show what its performance compared to the Wilcoxon statistic under null and alternative hypothesis. Then I will describe how the proposed statistic can be used for location receiver operating characteristic studies and biomarker studies. And then I will evaluate the finite sample performance of the asymptotic variance that I show, and I will show that the asymptotic variance is quite close to finite sample results, even if you have a sample of size 25 or 30. Finally, I will apply it to two data. One of them is a liver CT scan, and the other one is a biomarker study, and I will show how the methods can be used. So what is a Wilcoxon statistic? Let us first talk about the basic version of Wilcoxon statistic. There are N1 subjects in group 1 and N2 subjects in group 2. Observations from different subjects being independent, and the two groups are independent. The sample sizes N1 and N2 are prefixed. Let Xi be an observation on the ith subject in group 1 and Yj be an observation on the jth subject in group 2. So I have two samples, X sample which is of size N1, Y sample which is of size N2. I'm going to denote the distribution function for X to be F, the distribution function for Y to be G. Those are the cumulative distribution functions. Then the usual Wilcoxon statistic, you can write it as a sum of U statistic. This is the U statistic form. Sum I goes from 1 to N1 for the first sample, J goes from 1 to N2 for the second sample, Uij. What is Uij? It is a value which is usually a Bernoulli value. It takes the value 1 if Xi is bigger than Yj. It should take the value 0 if Xi is less than or equal to Yj. But in case of ties, what you can do is change it. You can introduce a half if Xi is equal to Yj and make this to be less than. So this Uij is basically like a Bernoulli variable if there are no ties. If there are ties, you have to introduce these mid-ranks and make an adjustment, and this is described, for example, in the classic non-parametric books by Eric Lehman. So in terms of probability, what does this W evaluate? Usually in statistical hypothesis testing, you think of W as a test statistic. So you always say, well, what happens if many X's are bigger than Y? If many X's are bigger than Y, the ranks of X values will be large, ranks of Y value will be small, so W will turn out to be a large value. So then you will say that large values of W lead to the rejection of the null hypothesis. But instead, for some intuitive reasoning purpose, I'm going to look at W as an estimator. What does it estimate? It turns out that it estimates I have N1 and N2 here, N1, N2 terms. So I have a multiplication N1, N2. Then what it evaluates is Uij. But Uij takes the value 1 if probability, if Xi is bigger than Yj. So in terms of probability, W actually estimates probability of X bigger than Y plus half of probability X equal to Y. For all practical purposes, you can leave this term. X and Y are continuous random variables, so the probability they are equally 0. Although in real life data, you can get equality. So it actually evaluates N1, N2 times probability of X bigger than Y. This probability of X bigger than Y, a lot of people write that this is the stress strength probability, etc. But that is present in the Wilcoxon statistic in a natural way. That's what we are estimating. So if I divide W by N1, N2, I will have a 1 over N1, N2. That is precisely the estimate of probability X bigger than Y. So an expression for variance of W, it is given in the classic text by Lehman in 1998, and it goes back to this Uijs. So we use the Uijs to find the variance. It will be N1, N2 times psi1, 1 minus psi1, psi2, etc. What are the psi1, psi2, psi3? Those are precisely the three probabilities that I introduced here. Probability X bigger than Y, probability X equal to Y, probability X less than Y. Those are the psi 1, psi 2, psi 3. So psi 1 is the probability X bigger than Y plus half of probability X equal to Y. Psi 2 is the expected value of the product of two Uijs. That means I have fixed an I. Individual from the X group is fixed. J and J prime are two individuals. And I am comparing them. And that is what is I2. It's the expected value. Then they are not independent. You cannot multiply them because I is common. You are comparing I with J, comparing I with J prime, so they are dependent. Same way psi 3 is you fix the jth individual in the second group and you pick I and I prime and you look at the expected value of that product. Clearly, the product can take only three values. Either it is 1, half or 0. It can also take 1/4. But if I don't allow for equality, it can take only 0 or 1. When it is both of them are 1, I will get the value and that will be the probability psi 3. So the expected value here in the case of no ties is simply the probability both Uijs are equal to 1. And that is the variance. So the Wilcoxon statistic is commonly used to test the hypothesis H naught F is equal to G against the alternative F not equal to G, especially when the normal assumption of the distributions is suspect. And that is when you suggest instead of a student's t-test, you want to use a Wilcoxon test. And how do I conduct the test? I take the W, I subtract the expected value of W under the null hypothesis, divide by the variance of W under the null hypothesis, and this will have asymptotic normal distribution, standard normal distribution under the null hypothesis, and you do the test. So under H naught, we know the expected value of W is N1, N2 times half. How do I know? Remember that N1, N2, probability X bigger than Y. But when X and Y are the same, probability X bigger than Y is half. So the mean turns out to be half N1, N2. The variance I can calculate. And notice here that the second term you don't see in many textbooks. Only the first term you see. The second term is necessary to allow for ties. So in the presence of ties, so DI. DI is nothing but the number of ties in the ith location. So if DI is only 1, that means there are no ties. DI cube is 1, DI is 1, it will disappear. So that is the formula. R is the number of distinct values. DI is the number of observations equaling the ith order statistic in the pooled sample. When we consider Xi and Yj as measurements of a diagnostic marker on a disease group and non-diseased group, another commonly used version of Wilcoxon statistic is not to take W minus expected value of W divided by square root of variance. It is common in the medical imaging literature to take W divided by N1, N2. W divided by N1, N2 is an estimate of probability X bigger than Y. That means you are estimating what the probability is for the diagnostic marker on a disease group to be correct compared to the control group, which is the non-disease group. So this is what is called as efficacy compared to non-disease group. So it gives an empirical estimate of the area under the receiver operating characteristic curve, which is nothing but ROC curve. Nowadays, you can't publish any paper in medical statistics without an ROC curve. What is an ROC curve? It is a common measure of accuracy of the marker to distinguish the disease from the non-disease subjects. So think of a 0 by 1, 0 by 1 square. On the horizontal scale 0 to 1, vertical scale 0 to 1, you draw a diagonal. Diagonal will go from 0, 0 to 1, 1. And that is the diagonal which says the person has no ability to differentiate between the disease and the non-disease group. So it is as bad as random selection. The best case scenario will be going directly up and then horizontal. And that is a perfect matching. And in between, you can have a ROC curve. How big is it in area? the triangular area is 0.5. So any area under the ROC curve above 0.5, you will think of it to be better than random assignment. So you don't want it to be close to 0.5. You want it to be close to 0.8, 0.9. That tells you that the assessor is more accurate. Clearly, a continuous marker with no distinguishing power results. It's like me taking an image and deciding. I have no knowledge. I just randomly assign, saying that, oh, this looks like a tumor. This does not look like a tumor. I am randomly selecting. In which case, my area under the curve will be half because I will be along the diagonal line, which is also the expected value of W divided by N1, N2, because W expected value was N1, N2 divided by 2. So that tells you that the normalization of the Wilcoxon statistic by the denominator N1, N2 directly relates to area under the curve. And that will be half under the null hypothesis of F equal to G. So now what I am going to do is I am going to take N1 and N2 to be the original sample size, but K1 and K2 are two independent non-negative random variables that take on positive integer values. And these K1 and K2 are the numbers that come from N1 and N2. Remember that N1 and N2 are the number of images, diseased images, non-diseased images given to an expert. Out of that, he is going to select a random number of them and say these have the tumors. And that is going to be random. And that's what is K1 and K2. I'm going to assume this AL and BL square are the mean and variance of this K1 and K2. So, for example, if I assume K1 and K2 are binomial, obviously I will have AL and BL square to be the mean and variance of binomial. You can assume any discrete distribution you want. So, my samples now are Xi, not I equal to 1 to N1. I equal to 1 to K1. K1 is a random number of disease subjects that the marker identified. Yj, J going from 1 to K2 is the random number of observations from group 2. Allowing ties, I am now going to introduce a new Wilcoxon statistic, which is sum of Uij, except I goes from 1 to K1, J goes from 1 to K2. And I put a R there. The R is there because it's a random Wilcoxon statistic. K1 and K2 are not fixed. So you cannot use the usual asymptotic theory of ranks to derive the asymptotic distribution of WR. What are Uij? Exactly the same as before. Because I have a bunch of X, I have a bunch of Y. I ask, is Xi bigger than Yj? I will take Uij to be 1. Otherwise, take it to be half and 0, etc. is the same. For continuous data, the probability of having a tie is 0. So the expectation now, it is not going to be simple. When I want to take the expected value of Wilcoxon statistic, I took N1, N2 here. So expected value of Uij under the null hypothesis is half. I get N1, N2 half. I cannot use that formula because K1 and K2 are not fixed. They are random. So you have to use what is called as a double expectation formula. What you do is you first condition on K1 and K2, then you find the expected value of WR, then take the expectation with respect to K1, K2. If I assume K1 and K2 have means A1 and A2, I immediately get this formula A1, A2, psi 1. And the variance of WR, I use the same. The variance of a random sum is the expected value of the variance plus the variance of the expected value. So I can write immediately everything that I need by using the conditional expectation and conditional variance formula. So I have the expectations. What about the limiting distribution? That is completely a different thing. Suppose the distribution of Ki depends on a parameter tau I and has an asymptotic expression as tau I goes to infinity. Think of the following scenario. I started with a sample of size Ni. I find a random number of images in the CT scan to have the tumors, and I put a probability pi. Now I can let ni go to infinity. So in this case, the parameter tau I going to infinity is same as ni going to infinity. Then I know ki is simply asymptotically normally distributed with mean ni pi, variance is ni pi qi. So I can use this sort of reasoning. I define a function u as 1 if x is bigger than y, half if it is equal, 0 if x is less than y. I have put a less than or equal to because if you have no ties, you can get rid of the middle case. Then I'm going to define a Wilcoxon random sum Wilcoxon statistic and normalize it. Normalization is done by a random mean. Remember, Wilcoxon statistic does not have a fixed mean. Only if I take double expectation, it will have a fixed mean. Otherwise, it will be a random mean, K1, K2, Psi1. So this is like normalizing with respect to the mean. And I define a S this way. And I have Psi1x that I have defined is the expected value of u function minus Psi1. Psi2y is the expected value of u function minus Psi1. Then I have some scaling. S is scaled with respect to tau1. T is scaled with respect to tau1. And those I denote by S star and tau star. These are scaled versions of S and T. Now, I need the following assumptions. I'm going to go over it quickly. Ki is asymptotically normal, which is because of binomial. I have some limiting results. The ratio of the two means goes to a gamma, some finite non-zero constant. Bi squared by ai, that is the variance divided by the mean, goes to delta I. So this is called Fisher index. It goes to delta I for some finite positive constant delta I, and I have a normalization constant. Ai to the power rho divided by tau I goes to lambda I. Under these conditions, we can establish the following result. First one is a lemma. Expected value of the statistic T star minus S star square goes to 0. What does this prove? This proves that I have the mean square difference between the two statistics, the T star, that is a random Wilcoxon statistic, S star is a univariate U statistic, that squared expectation goes to 0. What this says is that S star is a Hayek-like project. Hayek had a paper in which he talks about the projection. The projection says that I do not know what the distribution of T star is, but I know what the distribution of S star is because that is like a U statistic. So S star has a normal distribution. If I look at this expected value squared difference goes to 0, then T star, S star is a Hayek-like projection of T star. So that means T star has the same asymptotic distribution as S star, which is the random summation of IID random variables. But I know.
I think slides are not moving sometime. Sorry.
Oh, is it not? Is it moving now? Yeah. So S star is a random sum of IID random variables. Thanks to Robin's pioneering work in 1948, I know this guy is normal. So T star is normal. And this is a much different proof to show normality for a Wilcoxon statistic than using the U statistic principle. This uses a very powerful method called Hayek-like projection. You know something, you know its limiting distribution is normal, you prove that this guy goes to 0, therefore the limiting distribution of T star has to be normal because S star has normal. And that is a very, very nice book. Both of them have visited me several times, Boris Gnedenko and Korolev. They have a book-length account on the limiting distributions of random sums. And they all generated from a 1.5 page paper by Robbins in 1948. Most of these existing methods consider the summation of independent random variables. While the problem that I am considering is more complex because it is a random summation of dependent random variables. Uij's are dependent and I have a random sum. So I need this particular result of Hayek. Hayek-like projection is important, prove the asymptotic distribution. And that is what I mentioned here. The existing results cannot be directly utilized. Combining the lemma with the results of Robbins, asymptotic normality of the proposed statistic can be established. And that is the main theorem. The proof is a bit complex because you have to prove that expectation goes to 0, then the result becomes simple. I have the random sum Wilcoxon statistic normalized with respect to the mean, scaled so that the variance, so that this stabilizes the limiting distribution to be normal with mean 0, variance given by this quantity. Psi 1, psi 2, psi 3 are exactly as defined before. So the power of the random sum Wilcoxon test can be easily studied analytically. You don't need to do simulation, but I'm going to show you some simulation results and some application. First, I'm going to start with application to diagnostic data. LROC studies. This is a medical imaging study. An observer has good performance on localizing lesions is important, and that is what is this paper of Kalergi et al. A good observer should be accurate in diagnosing medical images and localizing lesions. In a lesion localization study, an observer is asked to identify and mark suspicious lesion locations. Yes, radiologist is asked to mark the malignant location, etc. In such studies, each image has only one rating and one marked location. So, a radiologist is free to mark a location. The highest malignancy rating is what is given. So, if you go for a cancer test, they say that from the scan, we decide that you have a stage 2 cancer. And that is done precisely by these markers and comparison with the previous existing thing. And application to diagnostic data continues, and the rating is then used for both the lesion and the image. So Xi in this case will be random because out of scans of 100 people, maybe 13 of them show lesions, the remaining 87 has no lesions. So K1 is a random number and N1 is the number of abnormal images. Yj similarly gives the rating of a suspicious location, but you know all these are normal images, so all of them are wrong decision. So whatever I find here, if they say that it's a suspicious location, I will have my entire sample to be wrong detection. So I take K1 to be binomial N1 P1. P1 is the probability of correctly localizing a lesion in an abnormal image. So from the past data, I need a preliminary value of P1, like the Bayesian setup. That's a prior. I will use the P1 for my decision making. Star et al. Introduced a location response receiver operating characteristic curve. That is what is called LROC. LROC stands for location receiver operating characteristic curve, and that is what can be done using this random sum Wilcoxon statistic. If I put the LROC curve in a probabilistic form, quantile form, I have 1 minus u goes from 0 to 1 in ROC, G inverse takes the quantile at 1 minus u, then under F, you will ask, what is the probability below that? I multiply by P1 because P1 is the proportion of observations correctly localized. So the empirical LROC curve will take G inverse, its quantile estimate, F, empirical CDF estimate, P1 hat will be the estimate of P1 that I have to give. This is my empirical LROC curve. So based on these data, we can express simply K1 by N1 because P1 hat is K1 by N1. K1 by N1 times this sum. This is nothing but a Wilcoxon rank sum statistic, random Wilcoxon statistic. Therefore, a non-parametric estimator for the area under the LROC curve, this is LROC curve at a point U. I have to integrate from 0 to 1 to find the area, and that's what I call as AL. If I put this in here, that means I am integrating from 0 to 1, and in this particular case, it will turn out to be 1 over N1, N2. N2 is fixed because that's a number of normal images. K1 is a random number of non-normal images identified. I am summing Uij. This is a random sum Wilcoxon statistic. So an AL of P1 by 2 means that the observer is performing the same as random guessing. I can use the test of hypothesis to see whether it is better than random guessing. Another one I mentioned about marker data with limit of detection. There is a paper by Schusterman et al. In Statistics in Medicine. When there is a limit of detection, below a certain value, you have all zeros. How do I find the ROC curve? What Schusterman et al. Say is just you discard those observations, treat the remaining observations as sample size, which may not be correct. So, LOD, limit of detection in diagnostic marker studies, has been discussed by many authors. More than 20 papers exist. So I'm going to take X1 to XK1 denote non-zero marker measurements, but XK1 plus 1 to XN1 are zero measurements. But non-zero measurements are random. Y1 to YK2 are non-zero measurements. YK2 plus 1 to YN2 are zero measurements. What these guys do is they say treat K1 and K2 to be fixed sample size when it is not appropriate. So you can look at the probability of detection. The area under the curve will be written in this form, probability X bigger than Y. Then you find a non-parametric estimator for theta. It turns out to be simply one term here based on K1 and K2. The last term is the random sum Wilcoxon statistic. So the area under the curve with the limit of detection involves random sum Wilcoxon statistic again. So I'm going to show you a simulation study quickly. It will take only 2 minutes. Then I will come to the lifetime data analysis just a few more minutes. I have two normal samples, different means, different variances, log normal samples, exponential samples. For each model, we simulated 1,000 data sets with two sample sizes. Both are 50, both are 100. The probability of observing a subject from either group was said to be 0.4 or 0.8. For each data set, we simulated binomial NLPL observations from group L. So that will tell you how many zeros are there, how many non-zeros are there. So to produce ties, you can take R categories by using cut points, C1 to CR plus 1. C1 is minus infinity, CR plus 1 is plus infinity, and I can create, if any observation falls in the interval C1 to C2, I will treat them to be equal. If any observation falls between C2 and C3, I can create them to be equal. So I can produce ties in this way. Subject is assigned a rating R if the observation falls between CR and CR plus 1. So we used 5 categories, 8 categories in the simulation study. So I want to show you the results, and from the results we can make some comments. Here are the 3 models. N1, N2 are 50 and 100. P1, P2. P1 is the probability for zeros and non-zeros, etc. Bias and mean square error and coverage probability. You can see that there is bias. The bias is present because we get only fractional data. As the sample size increases, the bias will tend to decrease. Mean square errors are small. That proves that the estimates are consistent. Coverage probabilities are close to 95%. If P becomes large, that means I observe most of the data. Only 20% of the data is made to 0. Obviously, the results will turn out to be better. So I now ask, What is wrong in using the Wilcoxon statistic itself? Why go through this hassle of random sum Wilcoxon statistic and make our life more complex? And once again, I take the same simulation. X and Y to be normal, X and Y to be log normal, X and Y to be exponential. Same distribution. So F is equal to G. Now, I produce the type 1 error values here. Simulated type 1 error rates. I took P1 to be 0.9, P2 to be 0.4, etc. I have the random sum Wilcoxon statistic and the Wilcoxon statistic. What do you observe? You observe that when the distribution is even normal, the regular Wilcoxon statistic will have much lower significance level than 5%. But the random sum Wilcoxon statistic always maintains the level of significance close to 5%. Much worse when the distribution is not normal. Particularly in survival analysis, lifetime data, you have non-normal distributions which are skewed, like exponential. If I don't use the random sum Wilcoxon statistic, I notice my level of significance can be as low as 1.8%. That will, of course, affect the power. The power will be much smaller. And that problem doesn't go away when I increase n. You notice even when n1 and n2 are taken to be 100, under exponential, the Wilcoxon statistic has a significance level to be 1.9 when it should be 5. So the random sum Wilcoxon statistic protects the normal significance level, and therefore the power is better. Now, final part is the data that I started with. There were 46 normal scans, 46 abnormal scans. Remember the data. Now what I'm going to do is all the normal scans, I'm going to say that there is no random number there. Everything is fixed, 46. But N1 is 46, but the number of correctly localized images out of that 46 was random, is K1. So I'm going to treat it to be binomial with 46 as the number of trials, P1 as the probability of success. What is the estimate of P1? I ask, how many of it correctly localized? K1. And that K1 in my data was 23. So 23 divided by 46 gives me an estimate of P1 to be 0.5. So now I can find the non-parametric area under the LROC curve. Turns out to be 0.3922. The variance is variance of AL, which is 0.0047. So under the null hypothesis of no localization accuracy, that should be P1 divided by 2. P1 divided by 2 should be the hypothesized value. I have to ask, is this 0.3922 much larger than P1 by 2? Depends on P1. You give me a priori value of P1. Suppose P1 you give me as half. Then my normal test statistic, Z test, will tell me that the test statistic is 2.73. The P value is 0.003. So that tells me that this person has very high accuracy in correctly localizing the CT scan. So that P1 becomes important. So I have to keep track of how often this expert was correct. And if I do it longitudinally, I can keep on updating the P1 value. If the P1 at some point turns out to be 0.7, 0.7 by 2 will be 0.35. 0.35 is very close to 0.3922, in which case you may say that it is not an improvement. He has reached a stable probability of success. That's how you will make a conclusion. So an investigator then needs to specify the null value P1 from past data. From this, you see that there is enough evidence to conclude that the observer is more accurate than random guessing in localizing lesions and in discriminating between abnormal images from normal images. In fact, you can go one step further. Suppose I have a job available to be hiring an observer. 2 people apply, 3 people apply. I can give them the same images and I can compare this value that I found, AL, for the three of them. The larger the AL value tells me that that person is better. So the larger AL value I can use to discriminate between different observers. And that is what is done in cancer biomarker data. So the cancer biomarker data is 7 diagnostic tests, 135 cancer patients, 218 non-cancer patients. This is a data that is given by Lloyd in 1998. And 0 values were assigned to those observations which were less than certain threshold value. So the data are biomarker data with a limit of detection. 10% of observations for each biomarker got trimmed due to the threshold value, and this is the estimated AUCs. You see here, I have 7 markers, A to G, and I have theta hat, the estimate, non-parametric estimate of the area under the curve, goes from 0.7159, 7565. I have given the variance of theta hat. I have given the 95% confidence interval for theta based on the asymptotic normality that I established. By looking at this, you can immediately conclude which marker is quite good. For example, 0.7662 is significantly larger than 0.7159. You would say marker B is much better than marker A. And you have a smaller variance as well, and we can do the hypothesis testing. So there are many things you can decide from here, that how to choose the best marker. The best marker that I chose, marker B, is he significantly better than marker D? I can do the hypothesis testing because I have 2 independent samples, both are asymptotically normal. I can do a Z-test. All these are possible because of the asymptotic theory for random sum Wilcoxon statistic that I discussed. Last page is the problems of further interest. I mentioned that each marker marks only one location that they suspect is a lesion. What if you allow the marker to indicate how many lesions there are? Instead of just one, he could circle 3 of them. And in this case, the method has to be extended because in each scan, CT scan, they may circle 2, another one they may circle 3, and in this particular case, how do I extend my random sum Wilcoxon statistic? And that's a point. One idea that I had was instead of taking all of them, you take the worst case scenario, which is the maximum rating, and use that. But there will be a loss of information. Method can be used to estimate the expected power when sample sizes can be only approximated a priori. For example, if somebody says, well, in my past experience, I have read many CT scans, I think only 15% of them show real lesions. So if only 15% of them show real lesions, I can expect what should be K1. K1 should be 15% of N1. So if I calculate, if I want to have a 90% power, what sample size should I use? And that is a sample size determination that can be done. Finally, the statistic that I proposed here were comparing disease group and non-disease groups. What about if there are 3 groups? For example, you can think of 3 groups as 3 stages of cancer progression. Early cancer stage, medium cancer stage, and advanced cancer stage. In this particular case, I have 3 groups I want to compare. And then you need to consider a generalization of what I have presented here to the K-sample case. This is something that we have done a little bit. We have published a couple of papers on it. So here are some important references. I want to point out only a few references, and particularly students who are interested in this type of research should have the knowledge of these books. The first one I'm going to mention is the book of 2002, John Wiley and Sons, Statistical Methods in Diagnostic Medicine. It is by Zhao, McLeish, and Obuchowski. Some of the data that I mentioned and some of the wrong applications of Wilcoxon statistic is present in this book. The other book is the Lehman's book. Eric Lehman's book is classic, non-parametrics. I would not touch any other non-parametric statistics book other than Eric Lehman's book. It's a 1998 classic book. The book by my co-authors, Boris Gnedenko and Vladimir Korolyev, where Gnedenko died, Korolyev is alive. He's about 93. He lives in Ukraine. And they have a book called Random Summation, Limit Theorems and Applications. It's about a 400-page book in which all you see is different types of limit theorems whenever you have random sums of independent random variables. They do not have dependent random variables. So that's something that you have to think of. Now, another one that I want to mention is this paper, Herbert Robbins, 1948. I told you he was the first one to give asymptotic normality for random sum of IID random variables. That's an extension of central limit theorem. So that was the first paper. The title is called Limiting Distribution of Random Sum of Random Variables. It is a paper which is remarkably cited, more than at least 1,000 citations of this paper. And you see the length of the paper. It is 1.5 pages. Page 162 to half of page 163. Proceedings of the National Academy of Sciences. So that is the paper that gave the first result on how to treat limiting distribution for random summation of variables. After that, Gnedenko and Korolyev was a student of Kolmogorov. They wrote many papers on random summations and limit theorems. And that book we use quite a bit in my work. I have the copy of the book signed by both of them in my office. So the rest of the papers I told are all applied medical papers in statistics in medicine, American Journal of Epidemiology, biometrics, etc. Medical papers in which non-parametric methods are used quite significantly. And I will stop there. That completes the talk. Thank you very much for listening. I am open for questions.
Hello, Professor. This is Dr.
Keeping your time. Now the floor is open for questions.
May I ask Dr. Pramod Gupta from the India?
Yes.
Professor, there is a nice presentation and I have no objection of your theory, whatever you have presented. I have one query to ask. You said your K1 and K2 you select from the N1 and N2. And K1 and K2 is the lesion that detected by the expert, that is maybe radiologist or somebody else.
Correct.
And N1 is the group, N1 is the sample which is like a abnormal sample, N2 is the normal sample. So you are talking about only the true positive, because K1 is the true positive if there is a case. But you are not talking about N1 minus K1, which may be the normal, but the guy has detected is the abnormal, and which could be the abnormal, but the guy has detected is the normal because they did not find any lesion. So that is my question, how you will incorporate this true negative or false positive case in your situation? Have you incorporated? I couldn't see this.
Well, in the simulation study, we know exactly where the exact lesions are located. So when the expert identifies, we know whether the person, there are two types of error. When I give a disease patient's CT scan or a MRI image, the person can say that this person is a diseased patient, that may be right, or say that this person has no lesions, that's a wrong decision. There is another wrong decision. They may say that this person has a lesion, but identify the location wrongly. That's the case that we are looking at. So in that particular case, when I define the ROC turns out to be based on K1 divided by N1. N1 minus K1 as a subsidiary result of the ROC. The ROC curve, when you work out the probabilities and write down the ROC as an estimate, it automatically turns out to be a function of K1 divided by N1. That is what I denoted by theta 1. So 1 minus theta 1 is what you are talking about, N1 minus K1. But in the ROC curve, only theta 1 appears, not 1 minus theta 1.
So you are saying that in K1 divided by K1 divided by N1 incorporate the rest of the part, which is maybe the true positive or true negative.
Right. The K1 by N1, if you think of them, you remember that we started with IID subjects, right? If they are IID subjects, I have only one parameter. The parameter that I am interested in is theta. Because I have started with a Bernoulli distribution, my P1 is nothing but K1 by N1, a sufficient statistic. So it contains all the information about P1. That is what I need to construct a ROC curve. So I also use it in my hypothesis testing at the end. You remember that I asked, what is the expected value of this? And it turns out to be P1 divided by 2. I need to specify that P1. If I say from past experience, if I want to specify to be P1 to be half, that this person has a 50% success rate, I will be testing it against 1 quarter. That is what I did at the end.
I got your, because your premise of the problem is that you assume that there is a 50% success rate, but you are not considering. I mean, what I feel, maybe you are considering and I couldn't get it. What I feel that there is a case where it could be the cancer and there is a false diagnosis, and there is could not be a cancer, there is a false negative diagnosis. So that what I mean, I am trying to understand whether how we could incorporate this concept into your problem. That was my question. And what answer I got, that N1 divided by K divided by N may be the answer of my question. That's what you wanted to explain, right?
If you look at the formula after I plug in and simplify the calculation, my ROC turns out to be a function of K1 by N1, and that is what is P1 I have to specify.
I remember. Thank you very much.
Thank you.
No,
Hello,
I think
sir.
that we are reaching the time set for the particular program, first program. I think that I can allow one minute is allowed.
Yes. Just one question.
There is 1 minute available. Any questions?
Sir, hello.
Yeah.
Hello.
Yes, Satish.
Yes, good morning. And Professor Balakrishna, you are actually considering a binomial sum, right?
No. The limiting distribution is general for any K. And then, as an example, I considered K1 to be binomially distributed. But
it is binomial, right?
What's that?
It is binomial, and then you are considering its asymptotics, right?
No. The asymptotic form had nothing to do with binomial. I started with N1, N2, from which a random number is identified as K1 and K2, and I assume that has finite mean and finite variance, A1, B1 square, A2, B2 square. The limiting distribution has nothing to do with the distribution of K1 and K2. It is purely based on these means and variances. It is always normal. Then, what distribution you want to use for your data analysis? It makes sense to use a binomial, because I give N1 scans to the expert and ask them to identify the location. A random number they identify, and it says that, oh, you can assume to be binomial. Nothing forces you to assume binomial. For example, I can assume a discrete uniform. I can assume any discrete distribution that goes from 1 to n1, and I have the same limiting distribution, means and variances will be different. That's all.
Okay, okay.
Okay, thank you. I think that we are nearing the completion of the keynote session. And on behalf of all those present in the Department of Statistics and ISPS and Statistics Fraternity Kerala, I thank you very much, sir, for your enlightening speech on this topic. And we expect that you come back again with more topics over the next millennium, I would say, because it's not because you are going to create problems and write papers very regularly, and we expect you to come back again. Whenever you write a paper, please give us a chance to hear you. Thank you on behalf of all present here and the Department of Statistics, ISPS, and Kerala Statistical Fraternity. I extend you a warm thanks, sir. Thank you very much.
Thank you very much. I appreciate your kind words, and for all of you to be patient through my talk and also to have some discussions at the end. Thank you very much.
Thank you, Professor Balakrishnan. Thank you, Krishnamurthy, sir.
Thank
you. So, mic is to Satish.
Thank you, Professor Balakrishnan, and thank you, Kalyanaman sir, for chairing this session. And we have a very nice keynote session. And now, plenary session. To chair this, in fact, this session, our Devasis Kundu, and to chair this session, we have Professor Loganathan sir. Loganathan is professor of the Department of Statistics, Mananmaniam Sundarnar University, Tirunelveli. And he is a very energetic, very active and serious researcher in especially, in fact, he has more than 50 research articles of high repute, and he completed more than 10 students for their doctoral research. And he is the editor of certain volumes of the current trends in Bayesian and methodology and applications of CRC Trust. And also he is editor of several other volumes connected with Indian journals and other journals. And of course, he has several projects complete, and he is an expert in the area of Bayesian estimation, acceptance sampling, clustering, etc. And I am on behalf of the Department of Statistics, University of Kerala, and other ISPS and KSA, I would like to invite Professor Loganathan sir to chair this session, because we have a little bit late, we are running. So please, that does not affect the time of Professor Kundu. He has to give 40 minutes. Professor, please. Loganathan sir, please. I'm handovering the mic to Loganathan sir to invite Professor Kundu. Thank you.
Thank you, Dr. Professor Satish Kumar, for giving me this opportunity. So the session is allotted with 40 minutes. Am I right, sir?
Yes, sir. Yes, sir.
Okay, right. Thank you. Thank you. Well, good day to all. Happy 36th day to all. Let me first thank the organizers of this international webinar, Professor Satish Kumar and his colleagues, and the other co-organizing societies for inviting me to chair this plenary talk session. Our speaker is Professor Devasis Kundu. Is a professor in the Department of Mathematics and Statistics of Indian Institute of Technology, Kanpur. Before inviting him, let me say a few words as a very brief introduction about the speaker. Let me not be a hindrance between the speaker and the participants. Let me make it as brief as possible. Of course, he does not require any introduction to the statistics fraternity, because quite often you can find his name in many journals for many papers. Professor Kundu, Devasis Kundu, he did his studies in Indian Statistical Institute for both undergraduate and postgraduate programs in statistics. and he has also obtained a postgraduate degree in US also. And he did his doctoral program under the supervision of the living legend statistician, Professor C.R. Rao, the great, in Pennsylvania State University. He has varied topics of research interest that includes statistical signal processing, of course, that happens to be his topic of doctoral research. Later on, he also contributed many results in the fields of distribution theory, reliability, and survival analysis. Out of his research, he has published more than 300 research papers in peer-reviewed journals of international repute. Of course, this number also include nearly 15 to 18 papers which are to appear in many internationally reputed journals. He is a co-author of 3 books. One was published by Academic Press, the other one was published by Springer, and the third one was published by Nerosa. The publication, The Statistical Computing, published by Nerosa, has got a lot of reception among the statistical researchers because it focused many practical problems of statistical computing. And he has supervised the doctoral thesis of 18 candidates, and he has a lot of teaching experience. He started his teaching career in University of Pittsburgh as a teaching assistant in 1984, and now he is a professor in the Indian Institute of Technology, Kanpur. And he got special appointments to visit several academic and research institutions abroad as well as in India, which include Penn State University, Indian Statistical Institute, Indian Institute of Science, University of Brunswick, and so on. He has carried out many research projects with funding from funding agencies, national level funding agencies in India, and he has a very lengthy list of awards which he has received. He is a recipient of several distinctive awards, which include the Fellow of National Academy of Sciences India, Fellow of Royal Statistical Society, and so on. He is a life member in several scientific societies in India and abroad. And with this brief introduction, let me invite Professor Debasis Kundu to deliver his talk, a plenary talk on the topic, a simple step stress model for Lehman family of distributions. Professor Debasis Kundu, please.
Okay. Yeah, thank you. Can you hear me?
Yeah.
Okay, good. Thank you very much for the kind introduction. And since Bala is here, so Bala, I would like to thank Bala because I was introduced to this problem quite long back about this stress modeling. And in fact, that was a funny incident. I think there was a famous paper in the stress modeling, and Bala, in his usual way, find an error in that. And that summer, I think I was visiting Bala, and we are discussing, and he said this one, look, I think there is an error in that problem, and then I think it should be corrected and all these things, and then it was finally published. I mean, we make that corrections, and Bala, myself, Nandini, and Tony, I think that was the first paper on this one, and I'm still working some of this problem. And in fact, Bala, please excuse me because I think you have heard this talk just few days back in this Arnold's volume, but I think that's okay. That's fine because I'm not. That's okay.
I can hear it again and learn something new.
I'm not as Bala is doing every week, maybe a new problem solving. But anyway, that's okay. That's fine. I mean, yeah. So let me just share the slides. Can you see? No.
No, I cannot see. Now it's all loading. It's loading.
Is that no?
Professor, you are loading? Okay.
Yes, I am.
Yeah. Okay. Try. Otherwise, we can.
It is not.
Yes, it is visible.
Is it
Your
coming? No.
laptop. Yeah. Now it is
visible.
To make it full.
Comes and goes.
Can you see the slides? No.
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 There is some problem. Slides.
Just 1 minute. Just 1 minute. Let me just try it once more. I think now it will. Yeah. Can you see? No.
Yeah, now it is coming. Now it is okay. You can make it full screen. Yeah.
You can switch to full screen.
Yeah, let me just try. Does it work? No. Is it working?
No. It's not.
Can you go to the top, Debashish, view and then switch to full screen?
Yeah, that's what I'm trying to do.
No? Oh.
Is that okay?
Yeah, you are on full screen now.
Is that fine or no?
Yeah, okay.
Yeah.
Is that okay?
Yeah, that's okay.
It's okay. It's okay.
So yeah. So the talk of my today is a simple stress model for layman family of distributions, and well, it is a joint work with my student Oyon, and Oyon Pal and Debashish Samanto is actually also was our student. He was our MSc students, and then he did his PhD from Bardon University, and Sharmishta is our colleague. Okay, so let's move that. We have this is basically the outline of my talk. I'll give the introduction, brief introduction about this modeling part, and what are the existing models. We'll be talking about it, and then I'll be talking about the likelihood inference, and I'll go for the data analysis. Okay. Okay, so let's go to the introduction, and well, I mean that is one of the general goal of a live testing experiment is to find out estimate the lifetime distributions of the underlying process based on the available data. Okay, so that is basically our ultimate goal. We have this data from an live testing experiment, and based on the data we are trying to obtain what should be the estimate of the lifetime distributions. Okay. So in many cases, we need to deal with highly reliable products. Okay, so that is one of the standard problem nowadays, and therefore we may not able to observe enough failures. I mean, within a given point of time. I mean, that is usually a big problem nowadays, and so therefore, if we conduct the experiment under the normal operating conditions, so at the end of the day, we may not observe enough failure. Okay, so that is basically the whole problem. So that's what is going to happen. Okay, so because of that, there are lots of process what we are using nowadays, and one of the particular things what you do, we do these things. We perform these things at the higher stress level than the normal conditions, so that we can observe more failures. Okay, and this is usually known as the accelerated live testing experiment. So this is one of the standard things what we perform nowadays. That's what we do. That we perform the experiment other than the normal operating conditions. Now, what are the advantages? I mean, if you do this one, of course, if you increase the stress, the reasonable number of failures is observed. So that is one of the nice part. I mean, you can observe the reasonable number of failures if you increase the stress level, and which naturally reduce the experimental time. Okay, so that is definitely one of the big advantage of using all these accelerated live testing process. Okay, But what are the disadvantages? Hello, can you hear me?
Yes, Professor. Yes.
Yeah. Sorry. So the major disadvantages is that need to know the exact relation between the stress level and the lifetime distributions. Okay. So see, our ultimate aim is that to estimate the lifetime distributions under the normal operating conditions. But if you increase the stress level, definitely the lifetime distributions are going to change. So we need to have a relations between the stress level and the lifetime distribution. So that is an important thing, and that is one of the major disadvantage when you are going for this accelerated live testing experiment. Okay. The second thing is that a model must take into account the effect of the accumulation of stress, because since we are increasing the stress levels, so therefore it is important that we should know how this effect is taking place. Okay, when the accumulation of the stresses takes place, how the model takes care about this one, and naturally that makes the models become more complex. And even in a simple case, what we will see, the analysis becomes much more difficult than the usual one. Okay, so these are the major disadvantages of this accelerated live testing experiment. Okay. So as I said, as I mentioned in the previous slide, that one of the major concern is that to find the relation between the stress level and the accelerated live testing experiment. Okay, so the relation between the two, that is an important one, and because of that, we will see this one that there are lots of models which are available, but we have a different forms of this accelerated live testing experiment, and we will be mainly talking about the stress experiment, which is a particular type of the accelerated live testing experiment. Okay, and one of the most common the stress experiment, we can describe it in a very simple manner. Which is as the intuition says, as the name also suggests, that I have different stress level. Say, for example, say S1, S2, Sn+1, be n+1, the predetermined stress level, and we have the predetermined time points, tau1, tau2, tau n. So the standard thing is that we start the experiment at the initial stresses S1 with n units of time, and then you keep on increasing the stress level at a regular interval. So for example, you change the stress level at the time point tau1 to the next stress level S2, and similarly you go to the next stress level tau S3 at the time point tau3, and so on. So what happens that you put the n items on test, and then you keep on observing the failures. Okay, keep on observing the failures. So you note the number of failures or the time point of the failures up to the time point tau1, and then you move to the next one. So it keeps on going, and then when all the items fail, you stop the experiment. Okay. And so you can put them in a simple manner that between 0 to tau1, I put this 0 as tau0. So between tau0 to tau1, you put the stress level at S1. Then between tau1 to tau2, you put the stress level at S2, and so on. And then between tau n to tau n+1, where tau n+1 is infinity, you put the stress level as Sn+1. So you can see that I am putting n+1 different stress level. And in this case, I'm looking at the simple situation. We wait till all the items fail. Okay, but it may not be the case, of course. We can have it more complicated situation also. I'll come back to that one. And that is the multiple, the general step stress experiment what we can talk about. And this is what we call as a simple step stress, where we have only two stress levels. That means up to time point tau, you have a one stress level S1, and then at the time point tau, you increase the stress level to S2. So you have two different stress level, S1, S2. So if you have only two different stress level, we call this one as a simple step stress. And this particular one has attracted quite a bit of attention because it is relatively naturally, you can see this one, that it is relatively easy to handle. Okay, so in this particular presentation, I will be first talking about the simple step stress one, and then I'll mention this one, that how it can be extended even for the multiple step stress situation. Okay, and as I mentioned, that in this particular case, I have talked about so far. I have talked about the stress changing at a fixed time point, and we observe when all the items fail, but well, we can make the things more complicated, and that's what it happens in practice. That well, we can have the stress changes can be at the random time point also. I mean, it is not necessary that those time points are prefixed, those tau 1, tau 2. Say, for example, you can change your stress level when you observe maybe the R1th failure. Okay, you move to the next stress level. Then you change your stress level when you observe the next R2th failure, and so on. Okay, so you can see that in that case, clearly your stress changing time points are no more prefixed. Okay, so they are random variables, so it is possible, but that makes the modeling, of course, more complicated. Okay, the second thing is that, of course, your data can be censored also. It is not necessary that you will observe all the failures. Your data can be censored. That means that well, it can be type 1 censored, it can be type 2 censored, and things like that. Okay, or it can be even hybrid censored also. Okay, so all sorts of things are possible. So data might be censored also. Well, and the third one is that we might have even the more than one failure. Okay, so it is not necessary that we'll be just observing the failure type. Sometimes we observe even the cause of failure also. In the statistical literature, this is well known as what is called the competing risk. Okay, so you might have more than one failure where I mean, in a situation like this. So that is also definitely also possible. Okay. So there are three major issues what we usually face, what we usually address in a step stress experiment. First of all, as I mentioned again and again, that the modeling part. That means that, I mean, how do you relate the different stress level with the associated distribution functions at the different stress level. So the stress factor and the distribution function. This is the modeling approach. The second thing is that the analysis based on the model. Okay, so we have the data, we have the model, and then the analysis based on that. And of course, at the end, which is also very important, what is called the designing of the experiment. And so this particular one, which also has received quite a bit of attention, because see, at the exposure model, but there are certain issues associated with this cumulative exposure model, and therefore we can think about the tempered failure rate model. Okay, we have this tempered random variable model and the cumulative risk model also. But I'll be mainly talking about the first two. I'm not going to talk about the last two, because our attention will be just restricted to the first two, the cumulative exposure model and the tempered failure rate model. The cumulative exposure model, actually, it was first introduced by these Bogdanovic's in 1978 from using the idea of this Sediakin, but I think it makes it very popular by Nelson in the 1980, and after that it has basically took off, and an extensive amount of work has appeared in this particular one. Okay, so let's try to understand what is this cumulative exposure model, which is a quite easy to follow, and that's the reason that I think it has received so much of attention. So let's put the some notations clear that let's denote this. I'm talking about the simple step stress model at this moment. So I have only the two stress levels. Okay, so I'm not talking about the multiple at this moment, but we can extend that one easily for the multiple also. But I'm restricting myself only to the two simple step stress one. Okay, so we have these distribution functions, capital F1 and capital F2. That's what at the two different stress level. That's the notation I'll be using. The associated survival functions are S1, S2. The hazard functions are H1, H2, and the corresponding density function are F1 and F2. Okay, we are talking about the absolute continuous distribution function. Okay, so that's the reason that we are assuming that the density exists. So all these things are fine actually. Okay, so yeah, so the overall, the cumulative distribution function, survival function, hazard function, and the probability density function will be a capital F, capital S, small h, and the small f. Okay, so that's the way, that's the notation it is. Okay, so the cumulative exposure model, which was first introduced and which can be represented very simply, that because remember that we are changing the stress level at the time point tau. So basically, my capital F, the overall distribution, which is taking the form capital F1 up to the time point tau, and beyond tau, it is of the form of capital F2 as t minus capital tau plus tau star. Okay, the reason is very simple, and one of the reasons that because basically I have two distribution functions before tau and after tau, and basically we are making the continuous one. Okay, we are making the two distribution functions to be continuous at the changing time point tau, and that's the reason that we need this restriction that F1 tau is equal to F2 tau star. So you can see that it is true for any arbitrary distribution functions, of course, absolutely continuous, the capital F1 and capital F2, and that's the restrictions we are putting in. So basically, for any given distribution function, I mean, any two distribution function, F1 and F2, that means a tau star will differ. Okay, so that's the reason that it has to come from these equations. Okay. If you look at the associated hazard function, and that is actually an important one, the associated hazard function actually satisfies these two equations, H1 and H2, and which will be also in a similar form under the cumulative exposure model. Okay, so if you look at the exponential distribution, which takes a very, very simple, nice form, and so that's what we have. The two distribution functions, capital F1 and capital F2, which are nothing but the exponential with the mean theta1 and theta2. So it has this particular form, and so now since it has to satisfy those equations, so my F1 of tau has to be equal to F2 of tau square, and so that basically gives me that my tau star has to be equal to theta2 by theta1 times tau. Okay, so that gives you, so you can see this one, as I have mentioned, that it depends on the distribution. So that means you can see that depending on the value of your tau1 and tau2, of course, your tau star is going to change. Okay, so that the cumulative exposure model takes shape. Okay, so in case of the exponential distribution, actually the distribution function capital F2, which has this overall form, capital F2 is equal to 0 for t less than 0, of course. 1 minus e to the power this quantity between 0 to tau, and it is 1 minus this quantity for t greater than tau. So that's the reason that's what is going to happen in case of the exponential distribution. And if you're looking at the corresponding, the probability density function, overall probability density function, which will take in this particular form, okay, which is simply the derivative of that. And along the same way, this Bhattacharya and Sejotti has introduced this what is called the tempered failure rate model. And the tempered failure rate model, which basically what they have done, they have introduced it through the hazard function, because it is expected that that when you increase the stress level, the hazard function is going to change, and in fact it is going to be a more severe hazard. And so that means that if your alpha is greater than 1 in this particular setup, you can see that then it is a severe hazard, and if your alpha is less than 1, then is of course it's a lesser hazard. Okay, so that's the way they have modeled that. They have modeled it, the overall hazard HT, in the form of H1T times alpha times H1T. Okay, so that's the way they have modeled the tempered failure rate model. And the nice part about this one is that in case of the exponential, they turns out to be the same, the cumulative exposure model and the tempered failure rate model. And that actually follows very easily. If you look at this particular relation, the cumulative hazard, which is of the form of capital HT, which is simply nothing but integration of HU du. The survival function is capital ST, which is e to the power negative capital HT, and the density function is this quantity, HT times e to the power minus HT. If you look at this quantity, actually, in case of the exponential distribution, they turn out to be they turn out to be same. Okay, so what we are saying in this one that let's put this the hazard function of the generalized tempered failure rate model, instead of putting as alpha times h1t, we are putting it simply h1t and h2t. So h2t can be completely arbitrary. Okay, it is not necessary that it has to be of the form of alpha times h1t. So the generalized tempered failure rate model, which is a simple generalization, which we can think of this way. Okay, so we are basically working on this one under this generalized tempered failure rate model, and we are looking at the class of distributions, what we call as the Lehman family of distributions, which is of course is a very, very rich class of distributions, which has this particular distribution function, which is capital F of t alpha lambda, which is of the form of the baseline, what we call as the G naught t lambda to the power alpha. Okay, and this G naught t lambda, which is of this form, we can put it as 1 minus e to the power negative lambda times qt. Okay, so now you can see that if you take these different forms of the qt, if you take qt as t, it gives the exponential distribution. If you put qt as t squared, then it will give the generalized Rayleigh. If you take qt is equal to log of 1 plus t, it gives the exponentiated Pareto. And if you give this qt is equal to 80 plus bt squared, then it gives the generalized linear failure rate distribution. So these are just some of the special cases. I mean, you can have lots of other distributions in this particular one. Okay, so if you're looking at the corresponding associated hazard function, which is simply from the definition of the hazard function, which is in this particular form, it turns out to be this one. Okay. What is important here that we have used the generalized and the tempered failure rate model. So what we are assuming this one that the connection between the stress level and the distribution function through this hazard function form, which is my ht, which is h of t of alpha 1 lambda 1 and h of t of alpha 2 lambda 2. So that means I'm taking those parameters alpha 1 lambda 1 alpha 2 lambda 2 completely arbitrary. So that makes the model more flexible. Okay, so therefore what we can see that under this assumption, which the overall distribution function takes this simple form actually. Okay, so I have the G naught of t lambda to the power alpha 1, which is the baseline to the power alpha 1 for less than tau and for greater than tau, which has this particular form. Okay, and so that is the relations what we have between the stress factor and the associated the distribution functions. Okay, so let's look at the corresponding the likelihood inference which we can obtain. So if you're looking at the likelihood inference based on the type 2 sensor data which has been developed, of course you can do it for the other sensoring scheme also. We can do it for the type 1 or you can do it for the hybrid one. It's not a problem at all. But what is important here, what we have observed that if you're looking at the likelihood function, the likelihood function of the type 2 sensor data. So this is not the derivative, by the way, this is the type 2. So that's the reason that I'm putting it 2. So L2 theta d, this d is the data. The script d is the data, and of course this theta is a vector, which of course involves all those parameters alpha 1 lambda 1 alpha 2 lambda 2. So the overall likelihood function, the log likelihood function, rather overall log likelihood function, the nice part about is that we can break it up as a function of alpha 1 lambda 1 and as a function of alpha 2 lambda 2. That I think is a major one of the very, very important thing, that because what we can see this one that in general we have a 4-dimensional optimization problem. I mean, if you take this alpha 1 lambda 1 alpha 2 lambda 2 as the single vector, say a single element. But we have only we have 4 parameters, but at least the 4-dimensional optimization problem, we can break it up into 2-dimensional optimization problem. And that's a very, very nice part. And not only that, actually, what it has been observed that G1 of alpha 1 lambda 1 can be maximized by using the profile maximization method. So which basically tells me that, one of the 2-dimensional optimization problem can be solved using a 1-dimensional optimization problem. And And that is a very, very important one, because see, one of the major issues about that whenever you are talking about the 4-dimensional optimization problem, I mean, we often do not bother about whether all those maximizations are unique or not, whether it has a multiple solutions. We really do not bother, but I think we have to be careful about these things, because often it happens that all those higher dimensional, the likelihood surface or the log likelihood surface has several local maxima. Okay, and often, I mean, that is my own personal experience tells me that, well, if we start with see, because any of these likelihood functions, if you have to find out the maximum likelihood estimates, you have to go through with some of the standard optimizations routine. Okay, and often it might get stuck with one of those local optimization, local maxima rather than the global maxima. But on the other hand, if we can break up the problem in a lower dimensional problem, so for example, in this particular case, when you're looking at this G1 of alpha and lambda 1, you can simply plot the functions and you can see this one, that whether that function has a unique maximum or not. If it is not, at least where it has the global maximum. The same thing with the G2 alpha 2 lambda 2. You can see this one that, well, it's a 2-dimensional one, but at least you can plot the contour and you can have a nice idea that whether this particular surface has a global optimum or a local optimum and things like that. Okay, but you do not have any such idea if it is a 4-dimensional one. Okay, so that is definitely one of the very, very positive point. Another simple thing what we have observed that, well, if you have the complete data instead of the type 2 sensor data, actually in the case of the complete data, it is not only G1, you can obtain G2 also. The maximization of the G2 also can be obtained as a one-dimensional optimization problem. So in both the cases, that means you just solve a one-dimensional optimization problem instead of the 2-dimensional optimization problem. Okay, that's what it says. Okay, we can go for the testing of hypothesis. That means you can simply go for whether your alpha 1 is equal to alpha 2 versus alpha 1 not equal to alpha 2, or you can go for your lambda 1 is equal to lambda 2 versus lambda 1 not equal to lambda 2. Those kind of the testing can be easily performed. Okay, let's look at the data analysis. What we have done, I mean, we have observed, we are basically taking this particular data from the 15 fish. Actually, this particular experiment was done to check that the effect of the pollution in the fish. Okay, how much it affects the fish, and the way this experiment has been done, that what they are doing this one, that they are increasing the stress level, and the way they are doing these things, basically they are increasing the flow of the water. Okay, and at a regular interval. Okay, at the regular interval, and they are observing that how when the fish stops swimming. Okay, that's what it is, and that's a way the data have been collected. And so the 15 fish which has been put, and they are changing the stress level at a regular interval, but we are taking it as a simple stress 1, so simple stress level. So we have assumed this one, that the stress changed at the time point 150. Okay, and we observe the data point which at this one. Okay, the complete data. So we have tried with the different of those the Lehman family. We have worked with the generalized exponential, we have worked with generalized Rayleigh, we have that exponential Pareto, and the case distance and the p-values are like this, and you can see that based on this, we can see that the generalized Rayleigh is the best fitted one. Okay, let's look at some of the extension, what you can think of. And I think that makes the thing more interesting. It can be easily extended for the multiple step stress model. Okay, and so that is, I think, one of the important part. I mean, that is, I think, one of the strong point of this particular one. And so let's recall the multiple step stress one. I mean, the multiple step stress one, that you change your stress level at the time point tau 1, tau 2, and tau m. And so you can see that up to time point tau 1, you have this stress level S1, and you observe the samples as T1, N, T2N, T capital N1N. So that means you observe N1 failures in the stress level S1, which is before tau 1. Okay, so that's what we have. Similarly, you observe T2N things like that. Okay, so that's what we observe. All these data points. So this is basically your the multiple step stress, and what we assume that, well, we are looking at the generalized tempered failure rate model, and we are looking at these things at HT, which is H1, H2, HM. They're completely arbitrary. Okay, and then if we're looking at the corresponding the likelihood function, log likelihood function for the complete sample, which can be written in the form of G1 of alpha and lambda 1 up to Gm of alpha and lambda. Again, as I said, this is what I think one of the positive point. That means that we can break it up into m separate problems, okay, separate optimization problem. Okay? So we can obtain the maximum likelihood estimates by maximizing it separately. Okay, this is another quite important one which has received a considerable attention, that what we call as the order restricted inference. I mean, if we go back to our the simple exponential model where we have these exponential distributions, theta 1, theta 2, theta n plus 1, so which is a particular case of this one, and we want to have an order restricted inference. That means we have this experimental unit, and we know this there is a restrictions on the orders on the theta i's, and which are like this: theta 1 is greater than or equal to theta 2, greater than or equal to theta n plus 1, and it is a very, very natural ordering, because you can see that because theta is at the mean, so that means that as the sample size, as you are increasing your stress level, you have this kind of a restrictions what you have. Okay, so I can have this one greater than or less than, doesn't really matter. Okay, this was first actually done by Bala and Kateri. They have first tackled this problem in 2009 in their paper, and they have used a very, very nice technique, which is the isotonic regression technique. They have used, but it's a very, very novel idea. But there is no explicit solution in that sense. Okay, and so we have done it in a slightly different way. And so instead of working with the theta 1, theta 2, theta n plus 1, we have reparameterized them. And so I have this theta is equal to theta 1 and theta 2 is equal to beta 1 theta, and so on. So that's the way it has been done. So and where there is a restrictions on the beta i's. Okay, so basically the reparameterizations from theta 1, theta 2, theta n plus 1. Now the set of parameters are theta, beta 1, beta 2, beta m, where theta is 0 to infinity. There is no restrictions on the beta i's. Only thing is that they are bounded. They're independent. The beta 1, beta 2, beta m. There is relation between the beta i's, but they're all between 0 to 1. So under these restrictions, it is possible to obtain the maximum likelihood estimators. Okay, based on this, and so it should be possible to use the same idea, the same technique here also. That the scale parameters, we can put a restrictions on that, or we can put a restriction on the shape parameter also, and we can do these things, this inferential procedure. So one of the advantage of using this reparameterization is that even the Bayesian analysis also we can do it quite easily, because we can put a restrictions on the betas, or we can put a prior on the betas as maybe the beta prior. Okay, so those are the priors we can put it, or the uniform prior between 0 to 1. I mean, things like that. So those are the things we can easily put that one. And so the Bayesian analysis also can be performed in a quite convenient manner, not too much of a problem. Okay, and that's what it is. And I think that's what I have. So yeah, any questions or any comments? Yes, I'll just
Congratulations, Professor Kundu, for having completed your presentation within time. May I request Professor Balakrishnan sir is on the line. May I request Professor Balakrishnan to make some comments on this talk and presentation? Professor Balakrishnan.
Oh, you mean me?
Oh, yeah, yes, sir, exactly.
Oh, I thought you meant Balakrishna from KUSAT.
I pronounced it clearly.
You don't have much escape, Bala, even if you have...
You're listening so carefully.
No, I think Debashish has outlined this problem. The usual estimation methods in such models become complex, particularly as the number of stress levels increases, the dimensionality becomes a problem. So the factorization there in the likelihood function to model in individual pieces, and you maximize individual pieces, seems like a good approach to take. And it's a nice way to proceed, because otherwise if I have 3 stress levels, I could end up with a 6-dimensional optimization, and it could be complex. That's the problem. I have one question though. You know that if we go back to our work originally, the MLEs there are conditional on the number of failures that are observed in the first stress level, and we need the number of failures observed in the stress level to be at least 1, because we were dealing with exponential. So do you have a similar condition here, and do you need at least 2 parameters, because at least 2 values in each stress level, 2 failures?
Yes, absolutely. I mean, definitely, yes. If you are working with the exponential, I mean, we definitely need at least 1 failure in each stress level. And
Right.
if you have any other which has so many parameters they have, at least we need that many data points in each stress level. That is one part. But let me come back to this one. But on the other hand, if we put these order restrictions, I mean, say for example, I mean, if I go back to this exponential one, and suppose you have an order restriction, so actually then we do not need the failure at each stress level. Only thing what we need the failures, at least 1 failure at the lower one, and at least 1 failure at the upper one. Okay, and even if we do not have failures in between in some of the stress level, but still, because of the order restrictions, those estimates can be estimated. Okay, so that is one of the advantage about the order restrictions if you put the order restrictions. But of course, if you do not have the order restrictions, we have to have at least 1 failure in case of the exponential, or if you more than that, depending on the number of parameters of the distribution capital F. Absolutely, yes.
If I am not mistaken, maybe I have to work it out. If I am not mistaken, in the model, if there are no failures, let us say you have 1 failure at the first stress level, then you go to the second stress level. If there are no failures, then what I can do is to set the estimate of the parameter theta to be 0 at that level, then PAVA, the pool adjusted violators algorithm, will automatically adjust and make them to be equal. Am I right?
That's what it happens actually. That's what it happens. That actually maximizes the likelihood. That you have shown. That you have,
exactly.
Yes.
Yeah.
That is going to happen actually. See,
so the
it is like this. Exactly. So suppose it is like this. Suppose at the second stress level, suppose we do not have any failure. Okay, I have a failure at the first stress level and the third stress level. Okay, and so that means let's look at a very simple case, the exponential one, say theta 1, theta 2, theta 3. Okay, so what is going to happen? This theta 2, of course, if you do not have any restrictions, I won't be able to estimate theta 2. Okay, but if we have the restrictions, then actually this theta 2 will be either theta 1 or theta 3. Okay, the estimates of that one, what we said, I mean exactly what I had said, and that we can show this one that it maximizes the likelihood function actually. Yes, exactly. That's what it is. Intuitively also makes sense actually. Intuitively also that makes sense. Yes. It is.
Thank you, Professor Balakrishnan. Due to time restrictions, we can allow one quick question because we are given with 40 minutes. Already we have crossed 2 more minutes. We can allow one quick question. So, no question. There's no question from the participants. Of course, without question, there shall not be any presentation. Of course, it is a fundamental doubt that you have worked with type 2 censored data, and you have shown nicely that log likelihood function was expressed as a sum of two pieces. Will it happen in the case of progressive censoring?
Yeah. This breakup is going to happen. That should not be any problem. Breakup is going to happen. That will be. I mean, well, we have not to work it out, but my feeling is that it should actually. It should.
Well, participants, are there any questions? I think if there are no questions, let me conclude this session. Thank you, Professor Debasis Kundu, for making a very nice presentation and giving an exposure to the existing problems in connected with this topic. And I thank the organizers for giving me this opportunity. And I hand over the session to the organizers, Professor Satish Kumar.
Thank you. Thank you very much. Yeah. Thank you.
Thank you.
Thank you, Professor. Thank you, Professor Debasis Kundu, and thank you, Professor Nagarajan. In fact, both, yeah, we had a nice session. Now let us move to the next section because of we are running late, but we can cut off our lunch break time so that the time do not restrict any time short to our special session on count time series organized by Professor N. Balakrishna of Cochin University of Science and Technology, and he and his team they are ready to handle the next session. And in fact, this session is chaired by Professor Parveshwar V. Pandit. But Pandit informed me he will join little bit late because of some urgent meeting, so that all of you know Professor Pandit even then, so that I hope the co-chair will handle the initial part of the session. In fact, before going to the session, just Professor Pandit, some of may not aware probably, I shall give, is a professor of the Department of Statistics of Bangalore University. He's also a very active researcher. He has more than 30 years of research and teaching experience and more than 80 research publications, and also more than 10 PhD scholars, PhD doctoral degrees under his supervision awarded. And he is an expert in the several areas, including non-parametric inference, etc. Inference on reliability, parametric inference, etc. And so I invite this occasion to introduce Dr. Krishna Kumar. He's a very young researcher, and in fact he did his postgraduate degree as well as PhD from Madras IIT, and he is an expert in the area of spectral theory, operator theory, etc. Very young researcher and energetic researcher. He joined our Department of Mathematics of University of Kerala, and he has several publications of international repute. I invite Dr. Krishna Kumar to carry over the session, to initiate a session, and you adjust with the Professor Pandit to manage the session. Please carry on.
Thank you, Professor Sadish sir. Can you hear me?
Yeah, we can hear. Yeah,
okay.
Professor.
Happy Statistics Day to all. Actually, I am from the mathematics community. I'm a little bit tensed about knowing the subject. I don't know. Maybe I will try to understand my best and try to cope up with the session. And I thank Professor Sadish sir and Dr. Riaz and Department of Statistics for giving me the opportunity. To such an opportunity, it is a great feeling, and it's a great privilege for me to chair a session with these eminent statisticians across the world, and it's a great privilege for me. I'm a small researcher in mathematics. So I will get into my duty. Today we will be having our session title is Count Time Series, and we have 4 lectures today, and we will be having our lectures by Dr. Suili Mukhopadhyay from IIT Bombay, and Professor N. Balakrishna, and Professor Dr. Manik Awale, and Dr. Arindam Chakravarti.
Yeah.
Arindam Chakravarti. Professor Dr. Suili Mukhopadhyay is online. She's online. IIT Bombay.
Yes, I am online.
Okay. So, Professor, welcome to the session, and I will give a brief introduction about Suili Mukhopadhyay. She's a faculty of IIT Bombay, working in the Department of Mathematics, and she completed her PhD from Department of Statistics, University of Florida. And her current research areas are design of experiments, mixed model analysis, predictive maintenance, and disease modeling. And she is having several postdoctoral as well as PhD students. And Professor, you can continue with your lecture.
So should I start presenting?
Yes, Professor.
Okay.
Yeah, Professor Balakrishna, whether you have to give any introduction to the session?
No, I think let us proceed with the schedule.
Yeah, okay.
You can all see my screen?
Yeah, it's coming.
It is visible. Coming.
Yeah.
It's fine now.
Okay. So should I start?
Sure, please.
Yeah. Thank you, Dr. Krishna Kumar, for the introduction. First, I would like to really thank the conference organizers, Professor N. Balakrishna from Cochin University and Dr. Satish Kumar for inviting me to give this talk in this webinar. So today I'll be speaking on ARMA models, and these models are for zero inflated count time series. And why we are talking about this zero inflated count time series? Because we are interested in modeling dengue in Bombay. Unfortunately, I can't give you COVID, but dengue and malaria once upon a time before the pandemic was quite interesting. So this is a joint work with my PhD student, Satish, and my postdoctoral student, Rashmi Tiwari. So a brief overview, we'll be talking about vector-borne diseases modeling, and the vector-borne disease which I choose here is dengue in Mumbai city. And so we are going to look at disease data over time, and we will see that there are many complexities in this disease data, which needs new thinking and new modeling. So we will look at our proposed model and the different properties of the models, then inference. And at the end, we will analyze the dengue data and see how well the proposed model fits it. Also, we'll be comparing the new model and the new technique with some of the existing technique already in time series analysis. And we'll see if our model, if our proposed model does better or not. Okay, so let's start. So since I am on full screen, I can't see any one of you. So if you have any questions, then please do interrupt me. Okay, so now we are looking at the Mumbai city map, the Brihan Mumbai map, the Mumbai and its suburbs. And so these divisions are nothing but the wards or the administrative regions in which Mumbai is divided in. So this division has been done by the municipality corporation. And we know about these wards now because the Mumbai model for COVID has become very famous. So, this is, we are going to look at dengue counts from these wards, and we will look at only one ward. And these are going to be weekly dengue counts. Now, these vector-borne diseases like malaria, chikungunya, and dengue, we have seen that these depend on weather. Okay, now this has not only been studied, in India, but all over the world. Vector-borne diseases have shown to depend on temperature, maximum, minimum temperature, humidity, rainfall, because they are, these things are transmitted through mosquitoes. So this, how mosquitoes breed and all these things, and how many mosquitoes there are, those things depend on the weather. Okay, so the timeline we consider is from 2013, the beginning, till November 2015. So in Mumbai city, we looked at some of the wards, and we saw that when we are looking at their dengue counts, then some of the wards report a lot of zeros. So we are actually going to look at Ward A, which has 44% of zeros in its dengue counts. So let's see where Ward A is located. So Ward A is the richest part of Mumbai, the Kolaba part. And so the thing is that it's highly populated, and we see that there are a lot of zeros. So there is a suspicion that there is a lot of underreporting of data. Why? Because the public hospitals are at this region, this G and F ward region. So maybe people just don't come and report or get tested from some private hospitals. And this, since this is a municipality data, so the number of zeros are too many over here. So because there is underreporting due to the distance from the public hospitals. Okay, so there are other wards also with a lot of zeros, but we just picked the Ward A. Now, we have not looked at all the wards together because that will become a multivariate model, and that's difficult because it's going to be a spatio-temporal multivariate model, and then with zero inflation. So we are looking into it, but not here. So if we look at the dengue counts in Ward A, we see that there are a lot of zeros. The zeros are colored with red. Hopefully you can see it. And we also look at the histogram here, and we see that at zero, there is a huge number of zero counts. So the data does seem to be inflated with zeros. So what are the complexities in this disease data or on this dengue data? That is, it's a count type data. So it's not continuous in nature. So it's the number of disease counts in each week. Okay, so that's like integer valued. And also there are too many zeros, 44.29% of the data is zeros. And we also saw over dispersion. And we also detected non-stationarity. So we look at the ACF and PACF of the raw disease counts, the dengue counts, and we see that we detect non-stationarity. And later we'll show that we saw that there was an increasing trend in the disease counts, and also there was seasonality. So let's go into the modeling part. Now we need a model which is going to account for zero inflation and also over dispersion when we have count data. So we can't just do with a Poisson model with its mean lambda depending on time. We need the W, where W is the part which is accounting for the over dispersion. And since we have zero inflation, so the probability with which the Poisson distribution gives zero counts, that's not enough. We have more zeros than that. So we need a mixture distribution. So it looks like this, the conditional distribution of Y. Now what's Y? Y is the response at time t. The response here is dengue counts at time t. T is the different weeks, the weeks from January 2013 to November 2015. Okay, so there are like 150 weeks. And what's HT? HT, now these are dengue counts. These are over time. So since it's over time, so the response is not independent. So it's correlated over time. That we know happens in time series. So what we do is we condition it on HT. And what's HT? HT is the information available on responses which we have till time t minus 1. Not only that, it also depends on the covariates. So we will see that the covariates we take over here are the weather covariates, and those are also dependent on time. Now this W or omega, I'm not sure what is it. I think it's W. So this W, this accounts for the excess variation which the sole Poisson distribution cannot take into account. And we model this W using a gamma distribution that is popularly done in the literature, statistical literature, to account for over dispersion. So if we write down the conditional distribution of YT given HT without the W, then we will see that it has a negative binomial distribution with probability 1 minus pi t, and it's degenerate at 0 with probability pi t because of the zero inflation. So so it's a mixture probability mass function, and it can be written as this: YT given HT takes value 0 with probability so, and M, where M goes from 1 to infinity with this probability. So if you find the mean and the variance, the conditional mean and the variance, then it's we denote it by the big lambda, the mean, and the variance we denote it by the big psi. So so now we introduce the ARMA mean models. So we are we have two parameters. We have two unknowns. One is this lambda, which is the mean of the Poisson distribution, and we also have this pi, which is the mean of the Bernoulli distribution. So if we just think back to GLMs, then we know that if we are using canonical link functions, then for the lambda we are going to use the log link, and for the pi we are going to use the logit link. That's all we do here. We can of course try other links, but the fit was quite good with this canonical links, so we just stopped there. So lambda t, we write it using the log link as e to the power wt. Wt is the linear predictor, and the linear predictor we write as xt transpose beta. So this xt is the covariate part. In the covariate you can have intercept, you can have trends, you can have seasonality using this sine and cos terms, and also you can have stationary covariates like this weather covariates. Now what ZT? So the ZT gives us the ARMA part. So the first part is a AR with AR of P1 degree and MA of degree Q1. And the parameters of this ARMA part are phi and theta. So we have parameters from the lambda model, beta, all the phis, the P1 phis, and the Q1 thetas. So we do a similar thing to the pi, and now we use the logit link, and we do the same thing. So MT is again the linear predictor, and MT is written as UT delta plus VT. UT is again the covariates. So this Bernoulli probability may also be affected by trend, by seasonality, by weather covariates. So that part is taken into account in this UT, and the VT part is the ARMA model. So again, we fit another ARMA model, and so the first AR part is of degree P2 and MA part is degree Q2. So it's a big model with many parameters. Beta, it's a vector, lot of phi's, Q1 thetas, then there's a big delta, a vector delta, then alphas, and then these gammas. So a lot of parameters to estimate. Now, we introduce a E here to write down the ARMA model, and this E we take as the standardized error. Now, what do I mean by the standardized error? This is YT. YT is the dengue counts or the disease counts at time t, the weekly counts, minus the expectation of YT given HT divided by root over its variance. And so this big theta represents all the model parameters, and XT, UT are the covariates. So we have this model. So now we are going into estimation. So the simple way to do is use a maximum likelihood. So you can write down a partial log likelihood. Why don't we call it just the log likelihood? Because we have YT given the HTs. So that's why we call it partial. So this has come from a lot of papers written by Fockianos, Kedem and Fockiano. So these log likelihoods are called the partial log likelihoods. So the score functions are these. They are very complicated. If you are interested in this estimation part, I can give you the archive link and you can look at them. So you can use a Newton-Raphson algorithm. Of course, it's not so easy to solve, so you have to use some approximating algorithm to get the estimates, the MLE estimates of big theta. Another way to do it, of course, is using the EM algorithm. The EM algorithm has been proposed to estimate zero inflated models completely from the beginning. So you can think of a Bernoulli variate, ST, which takes value 1 when YT is from the perfect zero state and equal to 0 when YT is from the negative binomial state. Of course, you don't know when it's from the perfect zero state and when it's from the negative binomial state. And that probability is pi t, and you can take another distribution of the count given this Bernoulli variate and the information HT, and that you can model as a negative binomial with over dispersion and everything. So if you write down the log likelihood with complete data, then it can be defined, it is represented by this PLC, the C for the complete. And then, of course, when you are doing an EM algorithm, so you need the E step and the M step. So you write that down, and then you maximize the Q, and you get the values of theta. So that can be done. And if anyone's interested to look at the programs, also we have it. My PhD student is here in this call, so he can always talk with you and share with you all these tools. Okay, so in between, we have looked at asymptotical behavior of the parameter estimates of the model, but we don't show it here. It's too much for a webinar. If anyone's interested to look at those asymptotic results, then again, you can look at the archive link. So one main thing over here, remember, is that it's a non-stationary model we are talking about. The non-stationary is coming from that covariate part, XT, okay? And then we have the ARMA, that's the stationary part, but we are looking at asymptotic properties of a non-stationary, zero inflated, over dispersed count model. So of course that a lot of details which we don't put here. So we just assume that the estimates are asymptotically normal, and we go on and write down the hypothesis, and we can use a wall type statistic, and we can also use a likelihood ratio test depending on the deviances. And if we have two different models with fitted parameters, number of parameters MP1 and MP2, then we can look at the differences of their deviations, and that follows a chi-square under H0. So to evaluate models, we also use mean square error, AIC, and BIC. Okay. So now let's go to the dengue data. So I will show you that we will have increasing trend. So we detected increasing trend in the dengue data, and also seasonality was detected. Weather covariates, there was a dependence of weather covariates of the dengue counts on the weather covariates. They were found to be significant in the log model. Remember, we have two models. One is for lambda t and the other one is for pi t. So in the log model, we saw that the weather covariates are significant, while in the logit model, the weather covariates were not found to be significant. Then we tried fitting different ARMA models by varying the values of P1, Q1, P2, Q2. And this is a comparison of the different models which we looked at. So if you look here, so over here we are looking at for the lambda t, we are looking at a model which has only a MA5 component, okay, because AR P1 is 0. And for pi t, we are looking we are not taking an ARMA model at all. We saw that it's no use taking an ARMA model. None of them are significant for pi t. And both models have the covariates of the average temperature, the humidity represented by HMD, and the rainfall. So over here in this model, the degrees of freedom was 16 and the mean square error was 9.0676 and so on, and the AIC and the BIC. So in this way, we fitted different models, but the model which we saw was giving good results in terms of chi-square, in terms of AIC, BIC, and deviance was this model. So what is this model? So this is the model. So WT is the linear predictor corresponding to the Poisson part of the model, the negative binomial part of the model. So we have the covariate. What are the covariates? We have a trend component. We saw that it's an increasing trend. And then we have the the seasonality. And then we saw that dengue depends on humidity, not on the temperature, not on the average temperature or rainfall, but on the humidity. This has been found before also in the literature for both malaria and dengue. Now for the other model, the logit part of the model, we saw that UT, the covariate is very simple. It just has the intercept and the seasonality part and nothing else. It doesn't have the trend part. So for W2, we have the covariate, and also we have no AR terms. The best model came out when we have a MA1 and a MA3. And the model for the binary probability, it only consisted of the covariates. It didn't have a ARMA part. So we fitted, so this is our result for the fitted versus the observed dengue counts. So I don't know if you can see it very clearly, but the fitted ones are not solid circles, and the dengue counts are the stars. And we see that there is the fit is not bad. It quite well fits the data. Okay, it more or less covers the way that the dengue counts fluctuate over this 150 weeks in this 3-year time. We also looked at the randomized quantile residuals. Why randomized quantile? Because the residuals themselves are not normally distributed. So we took the randomized quantile form of them and plotted them, and we see that most of the values are between plus and minus 3. And the quantiles also, we see that they are quite on the line of the standard normal quantiles. So we were happy with the fit. Now, we need to do a comparative study because this is a new model which we have introduced.
Excuse me. Yes. So you talked about the randomized quantile. Is it the same as that, what is that, quantile residuals kind of things?
So we are not looking at the direct residuals. We looked at some transformation of them so that we get the normality.
I see. Okay. Yeah, it's something like, I think it's
Yes.
quantile residuals interpretation.
Maybe it has another name. Yes.
Okay.
We didn't look at the residuals directly because of the problem of them may not be normal, no, because this is a negative binomial.
You can't expect a direct normality here.
Yes. Yeah, that's why.
Yeah. Thank you.
Yeah. I'll just go back to the full screen. Just a minute. Yeah, so we can't just like leave it without comparing other models. So in the literature, people have worked with zero inflated models, but quite simple zero inflated negative binomial models with only the AR part, no MA terms, and also AR of low orders. So mostly of one order. So we looked at an alternative model. So this is alternative model. That's why they are all AMs. And we have 4 alternative models. So we looked at a zero inflated negative binomial with AR1 terms. We looked at a negative binomial without zero inflation for AR1 with AR1 terms. We also looked at the ARIMA and the SARIMA models because that's what mostly people do when they just get a data instead of thinking about count, time series, and all those things. The problem with using a ARIMA and a SARIMA is we are forgetting that it is a count data. And we compared them using AIC, BIC, MSC. And we see that the selected model which we have, that MA1, MA3 for lambda t, that is giving us better results than all the other alternative models. So we were happy with our model fit. We, as is the style of today, we also looked at a neural network model. So I am not very sure about this. My students have done this part. So a neural network. And for that also, we got a lower value for the model which we proposed. So the MSE of the neural network was 16.47 and the deviation was 4.05. And you can see over here, this is much lower, 12.85, and the absolute deviation is 1.52. So our model seemed to have done the best for all. And we have also proposed, use this model on a very highly used zero inflated count data, which is the syphilis data. And over there also we saw that when we added MA terms, AR and MA terms, then the results were coming much better. Of course, we don't show it here. And at this point, what we are doing is trying to work with not one word data, but trying to take more words and work with all the words simultaneously. So we are thinking of a Copula approach, but we are still working on that. And so that's more or less the work. So thank you.
Okay, thank you, Suyalu Mukhopadhyay.
Thank you.
Nice presentation. I think there is time for a couple of questions.
Hello.
Hello.
Sir, I have a question. It's not a question, it's a clarification.
Okay.
Madam, you said that the data is over dispersed. Is it not due to the inflated zeros? Too many zeros has led to the over dispersion in the data, I suppose.
So we tried fitting just a Poisson model without accounting for the over dispersion, a zero inflated Poisson model, but then also we were not getting good results. So the best results we got is when we took both zero inflation and over dispersion. So we have tried out all types of models, just a Poisson model, zero inflated Poisson model with Poisson lambda t. And so I'll show you now, just a minute. So the best one which came out was this. So over here, as you are saying, so over here, we get rid of the W and we just have Poisson lambda t and we have the zero inflated part. But then also we were not getting good results in terms of the model summary statistics.
Okay, thank you. And there is one more question. Can you go on to slide number 17?
Yes, just a minute.
Where you have brought in covariates into the, into the study.
This one?
Yeah, this slide.
Yes.
And you said that the temperature and rainfall doesn't influence, they are not significantly influencing WT.
Yeah. So I will say why. So this has been studied widely.
Humidity, no, let me complete this. But
yes,
humidity, rainfall, and temperature, are they not all interrelated?
Yeah, so I will tell you. So we are looking at Bombay. So this is very confusing because we always, we always see so much mosquitoes in Bombay in the rainfall. But the thing is that, see, humidity is different. Humidity, the amount of humidity every day or every week is changing. Okay, but rainfall, when it rains in Bombay, so in Calcutta, I have seen that it rains for quite some time in the year. Okay, but Bombay, it's completely concentrated June end to September. That's it. And then it never rains. So, and then when it rains, the rain pattern doesn't change also. So that's why the dependence on rainfall never comes out. One is that. And now the temperature again doesn't vary much. There is not a lot of difference and over here we have taken average temperature also. So we had tried minimum and maximum temperature for malaria. And I think over there we found the temperature, the maximum temperature, I think to be dependent, the humidity. So the humidity, everyone, like in Vietnam and all the South Asian countries, everyone has found humidity to be affecting these vector-borne diseases, but not rainfall. Rainfall pattern is for Bombay, maybe for Calcutta, or maybe somewhere in the south, if we take where rainfall actually varies, then maybe we can get a dependence on rainfall, but not for Bombay.
No, okay, thank you.
But you, if you are, if you don't like this, then you can always at least think that, but we did find a seasonality pattern. So that seasonality is still there. So it's still fine. Yeah.
Yeah. Thank you.
Yeah.
I think. Just a minute. Okay.
Yes, sure.
I think we can discuss afterwards. We are running out of time. I once again thank Mukhopadhyaya for a nice presentation and discussion. I call upon the next speaker.
Thank you.
Professor N. Balakrishna. Okay. He is talking on zero modified count time series with Markovian intensities. I think over to Balakrishna.
Okay, can you see my screen?
Yeah, you can see your screen.
I'm also audible, right?
Yeah, you're audible. You're audible.
Okay. So I cannot see any of you now. So
no
now you can. I think it full speed.
That's okay. I think yeah. So that I won't become nervous by looking at the people, right? Okay. So thanks to Professor Satish for giving me an opportunity to organize this session. Also, I take this opportunity to thank the other speakers who joined this group. Dr. Sivilu Mukhopadhyaya from IIT Mumbai, Dr. Manik Avle from University of Pune, and Dr. Arindam Chakraborty from Vishwabharati University. So in fact, Sholi's talk gives me a good starting point to give my talk actually. This is on zero modified count time series with the Markovian intensities. It's a joint work with one of my former PhD students, Dr. Anwar, and also Professor Boas Abraham from University of Waterloo. Okay. So this is a brief outline of my talk, just a brief introduction. I think most of the introduction is been covered under Sholi's talk, models for some count time series. Then the major difference here is the kind of model which I am proposing for count time series, which is slightly different from what she has introduced in the previous talk. Okay, and then the other problems follow, estimation and data analysis. Okay, this part I think doesn't need much of introduction now. because as she has already mentioned, the classical ARMA model structure doesn't take care of the counting nature of the data. If you want to focus on count time series, because the linear or multiplicative model structure do not retain the integer nature of the data. Okay, so but alternative models were introduced to study the count time series by introducing a notation like the random thinning. For example, McKinsey has introduced several linear-looking time series models for modeling the negative binomial data and the Poisson data. Okay, they were all using this sort of star operation by meaning it's a thinning operation. But when you take the conditional expectations, the conditional mean structure remains similar to those in the case of linear ARMA models. Now, so instead of specifying the model in terms of the random variables, one can also specify the model in terms of the intensity functions. You know that in the count process, intensity functions, the intensity functions characterize the process. Okay, so just to introduce the terminologies and the model, let YT be a count time series, and my FT is the information available up to time point t minus 1. The basic structure which is assumed in my talk is that conditional on the past observations YT, we are assuming that this follows a discrete distribution with its mean function lambda t, mean or intensity function lambda t. Okay, it could be a function of past observations as well as some covariates. This is exactly what Sheely has introduced earlier. Okay, and what she has discussed is mainly the observation-driven models. That means the intensity functions are some specific functions of the previous observation and covariates. Okay, and there are several models available in literature with the conditional distributions, negative binomial, Poisson, geometric, and so on. Now, these are actually the parameter-driven models where, and for a recent survey, one can look at the edited volume by Davis and others, which was published in 2016, and also a recent textbook by Weiss in 2018. Okay, but what we focus in this talk is mainly the parameter-driven model, where the conditional distributions are Poisson or negative or whatever, with the intensity functions are generated by some Markov models. Okay. That means the conditional distribution of YT, given the past information and covariates, follows some distribution like Poisson or negative binomial, but the intensity functions are generated by some latent structured Markov models. So that is the major difference between the observation-driven model and the parameter-driven models. So this is where I am focusing now. Okay. Now, as she has already introduced the zero inflated case, she has mainly focused on zero inflation. That means the data may contain a lot of zeros. And similarly, we may also have situations where the zeros are less compared to the zeros contained in the distributions. That means in certain situations, such as modeling the number of individuals affected by disease, spreading of rumor, number of financial transactions during a specific interval, etc., may happen that there may be too many zeros or sometimes too few zeros. Okay, the empirical probability of zeros in such cases may be too large or too small compared to the probability of zero in any standard probability distribution. Okay, the standard distribution may not be able to explain all zeros in the data set. Okay. The case of too many zeros is referred to as zero inflation, and the case of too few zeros is referred to as zero deflation. The theoretical development of these two cases are more or less similar. Okay, and in this talk, I focus on zero inflated case only, mainly to suit whatever Philly was described earlier. Okay, and other details are given in our paper, which I will give the details later. Now, zero inflated count time series. Okay, I mean, these are already described. Okay, and now I will just introduce the nature of the intensity function we are dealing with. Okay. So conditional on ft minus 1, that is the information up to time point t minus 1, the random variable yt follows a zero inflated discrete distribution with mean function lambda t. And in this case, we assume that lambda t is a stationary non-negative Markov sequence. And this structure actually resembles that of the stochastic conditional duration models in finance. So we refer the resulting model as the zero inflated stochastic conditional duration models. Now, some more details about this or the basic structure of this. Suppose that conditional on ft minus 1, random variable follows a zero inflated with the stochastic intensity lambda t. Lambda t is a stationary Markov sequence, and one of the basic properties in the observation-driven models is that covariance between yt given ft and ys given fs equals 0 for s not equal to t. So this is one of the things that helps in our inference problem. Just these are some notation like for mean, variance, and autocovariance function of the processes. And just one good reference here is Zhu in 2012 studied the details of the zero inflated models for observation-driven models. That means the intensity functions are following a kind of Garch structure. Now, the model which we are going to consider in detail is the zero inflated Poisson model, which with some notation difference. This is what Shivali has already introduced in the earlier talk. Okay, and the major one thing which you are which you are stressing here is that the yt given ft is independent of ys given fs for t less than s. And these are the moments, conditional and unconditional moments of the model. I think these things will follow similar to the previous thing. And the one thing which I am going to stress here is the nature of the autocorrelation function. Okay, the unconditional autocorrelation function of the yt process is given by this expression, which is some scaled version of the ACF of the intensity function. That is, rho lambda k is the ACF of the Markov sequence, the intensity function lambda t. Okay. And the behavior as they are similar, which is clear from the following graph. That is the ACF of the original process as well as this one, or that zero intensity inflation case. And the similar computations can be carried out for different, if you assume that different Markov sequence for lambda t or even different distribution for the conditional random variable. We can also repeat everything for negative ML case also. Now, you may be wondering how to get this Markov dependent cases sequences for lambda t. So, Shivali introduced lambda t as a gamma sequence or the constant multiple of gamma random variables. I am proposing a Markov dependent stationary gamma sequence for lambda t here, which is defined by a model as gamma autoregression model introduced by Gower and Lewis in 1980. But of course, it has some complicated structure for its innovation distribution, but still it gives a stationary gamma sequence, Markov dependent gamma sequence. One can also consider other models which are available in the literature. Okay. Now we have, now what I'm focusing on zero inflated Poisson count series with the intensity function lambda t, and lambda t is a gamma Markov sequence. Let me specify everything what we are going to do next. Now, of course, if you want to verify this for any data set, like whatever she has described earlier, that is dengue data or malaria data, we have to have a well-defined inference procedure for the models which you are going to introduce. So I'm going to discuss that next. The main difficulty here compared to earlier discussion is that the model involves unobservable latent random variable lambda t. That means the ordinary least, this one, method of maximum likelihood is not very straightforward. Of course, theoretically one can introduce maximum likelihood method in terms of latent variables and then integrating out the latent variables later on. This involves a lot of computational things, and people have handled this using the Bayesian analysis and using Markov chain Monte Carlo technique. Okay. And here I am going to propose a method of estimative function which is computed, which is slightly easier compared to this MCMC algorithm, etc. Okay, so I'll propose Godam-based estimative function method for estimation. However, the involvement of lambda t's again create problems, and to circumvent these difficulties, what we do is we propose or we write the model in terms of generalized state space form, and then use Kalman filtering to extract the information for the lambda t, and then use that for estimating the parameters involved in the distribution of lambda t. So that is what we are going to do now. Okay. Okay. So you first of all write the model in the form of this one, that generalized state space form, using the idea of Zen width introduced in 1988, and then use generalized Kalman filtering algorithm. Okay. Now these are the lambda t is used to denote the filtered values. Now using Zenwirth paper's idea, we are writing or rewriting the Kalman filtering algorithm in terms of our notations here. Okay, where this KT is the Kalman gain, and all these are exactly parallel to what is available in Zenwirth paper, and we simply rewritten that to suit our requirement. Okay, and the above generalized Kalman filter algorithm remains same for any zero inflated stochastic conditional duration model with the Markov intensities, except that the way expression for Vt is only different, which depends on the conditional distribution of Yt given Ft minus 1. So we have simplified this for Poisson in the presentation. We also done it for negative binomial, which is available in the paper. Okay, for the zero inflated Poisson stochastic conditional duration model, our expression for V bar t is given here, this one, where sigma square and mu are the variance and the mean of the intensity process lambda t. Okay. And in particular, for the zero inflated Poisson SCD model, we can simplify the recursive relation for filtering lambda t using this relation. Now let us introduce briefly the estimative functions for those who are not familiar with that. In brief, or broadly speaking, so we consider a function of both parameter theta and observation, and denoted g of y theta. An estimate is obtained as a solution of g of y theta equals 0, known as estimating equation. Okay, and there are several optimality criteria available, which estimator becomes optimum when you solve this one. All these things are there. It's just the whole theory was developed by Professor Godambe, and later again Godambe and Thomson generalized the idea of estimative functions to stochastic process. Just to link my talk to the estimative function, I will just describe this. If Yt is a realization of a discrete time stochastic process whose finite dimensional distribution is indexed by a vector of parameter theta, and let ht equal to is a function of both observation as well as theta. Okay, it could be a two-dimensional martingale. Now, this is just the form of the class of estimative functions which we are dealing with. There are only this finite linear combination of this ht and some coefficient ATs. These ATs are determined using some optimality criteria, okay, which is common in the literature on estimative functions. Okay, and I come back to my problem here. The parameters to be estimated are the omega, mu lambda, rho, and sigma lambda square. This is the omega is the mixing parameter or the inflation parameter. Mu lambda is the mean of the intensity function. Rho is the autocollinear function of the Y series, that is the zero inflated series, and this is the variance of the intensity function. For notation sake, I will denote them as theta 1, theta 2, theta 3, theta 4. And I propose two estimative functions here. This is the first one, which is given here. Using this estimative function, we estimate the parameters omega, mu lambda, and rho. And using these estimators, we compute the residuals based on the data, and then use the residual mean sum of square to estimate the sigma lambda square. For that, I propose another estimative function that is given here, this H2T. Okay, and the remaining are all some the analytical properties, differentiation, and getting the solution, etc. I am skipping all those details. Okay. Now, based on this theory of estimative functions and the properties of zero inflated count process, we are proposing a computation algorithm for this particular model. That is, I'm focusing on zero inflated Poisson conditional stochastic conditional duration model with the intensities are generated by gamma auto-recursive process. Okay. This is the algorithm which is used for computations. Okay. And of course, this is specifically for Poisson and gamma. And with this slight modification, as I mentioned earlier, by changing the expression for V bar, we can use this for other class of models as well. Okay. Now, because every algorithm requires some initial values, we use this this one, factorial moments for finding the initial values for the unknown parameters. And this is just a table of simulated values. I hope it is visible. By specifying different values of rho, omega, beta, and p. Beta is the parameter of the lambda distribution. And these are the, and the means when the sample size increases, the mean square decreases. But still, you may see that for some parametric combinations, estimators are not doing very well. Okay, when it comes to the applications, I've just illustrated this using data analysis. Shivli mentioned this data, that is syphilis data, which is available in R package, Zim package. And we have, just for illustration, we have used this data. Okay, these are the basic property or basic structure of the model, like time series data, its histogram, and the ACF and PACF of the original data. These are the summary statistics. Just our focus is that see the number of zeros. The sample size is 209, and the number of zeros is 59 in this day. And the mean is 3.4 and variance is 9.7. That is actually variance inflation is there. Now observe that the variance is larger than mean, implying that the presence of over dispersion, which we have been discussing, and the plots of ACF and PACF of the data exhibit the presence of ACF, mean correlation among the observations. Okay. And that is also verified using Jung box test statistic. Okay, so these are the estimators we want to obtain to initiate the algorithm, the initial values. Okay, now these are the final estimates obtained using the algorithm which we have proposed earlier. The last column gives the standard errors. Now these are the properties of the residuals, and see the upper panel gives the histogram of the filtered lambda values, and the continuous line is the corresponding density function obtained using the estimated parameters. And the second graph gives the data, and the thick lines are actually the filtered values of lambda. And now, because we have only to estimate the fourth parameter, we have to compute the residuals. To do that, because we do not have an explicit structure for the model, so we cannot use we compute the residuals as a model structure here. For that, we followed the method proposed by Ziegler in 1998. Okay. So what we did is we have simulated a sample of size 209 number of observations from zero inflated Poisson Gar model using the estimated parameters. Okay, and then compute the new estimated iteratively for different stages, and repeat this about 1,000 times. Okay, it's taken as a then the repeated 1,000 times, and the empirical standard deviation is taken as the standard error of the estimates. Now then use because we have already data this y given observation, and these things can be obtained from the simulated case, and then using this relation you can compute the residuals. Okay. Now these are the residual plots obtained, and because this ACF and PSF show that there is almost zero correlation among the residuals, and these are the estimated and the empirical probabilities. So the dark line gives the observed probabilities, or the proportion of zeros observed in the data, and the light lines are giving the proportion which are estimated using our model and the estimation procedure. Now this is the sort of comparison between the actual probabilities and the estimated probabilities. Okay, with that I think I'm done with most of my presentation, and now some conclusions. We propose zero inflated count time series with the Markov dependent intensities to analyze the situation with excess zeros. It is demonstrated that the method of estimating function performs well in filtering the unobserved intensities and then estimating model parameters. Once the suitable initial estimates were obtained, the estimating function method provides feasible estimates for both positive and negative binomial models. But negative binomial I have not presented here, it is there in our paper. Simulation and data analysis were also carried out to demonstrate the consequence of zero deflated also, but again for the shortage of time I am not presenting that, but it is available. The details may be found in the paper which was submitted recently. And these are some of the main major references. And thank you for your patience.
Okay, thank you, Professor Balakrishna, for a nice talk. Now we have some time for some couple of questions. I think, am I audible?
Yeah. I mean, I can hear you.
Okay. Now there is time for some couple of questions.
Yeah, Sudhish has some questions?
Yeah. Actually, sir, for zero deflated model, is there any work similar to the previous work?
Oh yeah, I think there are papers available recently. Yeah, in fact, they call it as zero modified, so that they will take care of both inflation as well as deflation.
Okay. Something similar to history work.
Yeah.
So, sir, I have clarification, sir.
Yeah, sure.
Sir, how about this for initial estimates? You said that you have used the factorial moments.
Yeah.
Is there any other, approach or method that can be used? Why only factorial methods?
No.
Is there any specific reason behind?
No, this is just a method. That's all.
That's okay, sir.
Yeah.
Thank you.
You can use
Is there any specific reason for using factorial itself? Factorial moment?
Because no, in the Poisson distribution and all, so evaluating the factorial moments are easier, right?
Easier, because they deal with integer valued.
Right.
Yeah. So that may be the reason.
That's the reason. I mean, there is no other reason.
Okay, sir. Thank you, sir. That's it.
Okay. Hi, I have a question. This is
Yeah,
Shuli.
please.
Yeah. So that factorial moment thing I liked. Yeah,
Okay.
that was a good thing.
Okay.
Yeah. So one thing, and these residuals you have just plotted the original residuals. This is the raw ones, no?
The residual means, it's not easy to compute the residuals, original residuals using them, because we don't have model structure like in your case.
Yes.
Yeah, here we are specifying everything in terms of conditional distribution. So for that, Ziegler has proposed a method by compute the residuals by simulation. It's sort of kind of bootstrap residuals kind of thing.
Okay. So that you have used.
Yeah, that is what we have used.
Okay, and this paper is on an archive link?
Not archive. If you want, I can send you a copy.
Okay. Yeah,
I have not put in archive. It's just recently submitted.
Okay. Yeah. Thank you.
Yeah.
So if there are no questions, let us thank Professor Balakrishna for the presentation and discussion.
Okay, thank you.
Let us move on to the next speaker. So the next speaker is Dr. Manik Avade. His topic is forecasting INAR count time series. I request Manik to give the talk. So go to Manik. So you are not audible.
Manik, please put on, unmute your mic. Okay, now speak. Now still you are not audible.
Yeah, you are not
Now
audible.
I must be.
Yeah, now you are fine. Yeah.
So, is this screen?
Not yet.
Not yet. Yeah.
Yeah, you share your screen.
Is it now?
No. Yeah, it's coming.
No, it's coming now.
Okay, good.
Can you see it?
Yeah.
Yes, it is.
Yeah, it's
Is it moving?
Yeah,
it's
it's
moving. It's moving. Yeah.
Okay,
Yeah, it's
thank
started moving. Yeah. Okay.
Okay, so now I can't see you. So thank you, Professor Balakrishna, for inviting me for this session, and a very happy National Statistics Day. So our department, our programming is also going on for National Statistics Day, and so I'm coming here for the time being. Okay, so I'll not take much of time. So I'll be talking about the forecasting in our term time series, and it's it's coherent forecasting, and this would be the outline of my presentation. Initially, we will see the data, that is, what is the motivation for this problem to take up, and what are the possible models and why we chose this and its probabilistic properties. Then some simulation for forecast accuracy, and then coherent forecasting. So this is the first data, that is soap cell data, which has been analyzed by Leo and others 2018 in Communications and Statistics. And what they did, they tried to fit a INAR-PL1 model. So INAR-PL means INAR model with Poisson-Lindley innovation, and the auto-regression of order 1. And this data was available at this site. Of course, it is a over-dispersed data, and they compared the then models with their model, and then they showed that the INAR-PL appears to be better for this data. So this was the marginal plot. We can say these marginal probabilities. Okay, this is frequency now. I didn't convert into probability. So this is somehow asymmetric and near to a negative binomial. And this was a time series. It's autocorrelation plot and PSF. So it has a first order of dependence. Now this is what the marginal calibration plot. So we tried 4 models, marginal distributions. So which one is better for this data? So what we saw, so we this black solid line is negative binomial, marginal, and this red one is geometric, negative binomial. Then red is Poisson, dotted blue is geometric, and this violet is Poisson-Lindley marginal. So among all this, we thought that okay, this negative binomial appears to be better and much better than the others. So we tried with this. So this was a market data, or you can say this non-epidemiological data. So I mostly worked on epidemiological data. And now, so there is one data set, tuberculosis, and this data is weekly cases of tuberculosis for 522 weeks from its German data, and that is easily available from the Robert Koch Institute. So it has a mean of 21 and 21, 22, and variance is 44.70. So it implies this over dispersion. Now, why we, so one of the aspect of this modeling is it has over dispersion, and this is for over dispersed. So this also has this is the marginal distribution. this is the time series. So there is no zero inflation or what, and it has kind of year one structure. Again, we tried a marginal calibration plot for this data, and among these four competitors, this negative binomial appears to be better than the others. Okay, so this black line, solid line, is a negative binomial, and it's quite close to zero. So it is like empirical CMF, and the theoretical CMF comparison. So the better the model, it should be fall along the zero line. So what are the possible models for such data? So Poisson INR1 is out because it is equidispersed. Then GINAR and NGINAR, these are models for with geometric marginal distribution, and they can cover the over-dispersion in the data. Okay, and this has been already analyzed. Now we have INR-PL, this INR with Poisson-Lindley, but it has less skewness and kurtosis as compared to this negative binomial. And then the last option we have is this NB-INR1. So NB-INR is a INR model with negative binomial marginal, and it is over-dispersed. It can consider the over-dispersed data as well as it has high skewness and kurtosis. Now, these are not the only models. There are zero inflated, 0-1 modified. There are so many models. So with these conditions, so these are the four possible. Now, Poisson is out, and geometric NGNR. So we have a comparison with it. And INR-PL, what happens? INR-PL fits better, but if we have only innovation distribution known, then it's difficult for coherent forecasting. So NBNR1 is the best choice. Now NBNR is proposed already in the heuristic and others. So how to do the coherent forecasting for such models? So that's what our main objective. Now, I have discussed two data sets, but I am not going to analyze both of them in later. So I am going to consider only one. So what we do, we have this bar plot, then we have time series plot, then we have marginal calibration plot. So we have used this another information criteria also, AIC, BIC, and among these also, so we compared with all these possible competitors, and NPNR seems to be better for this soap cell data. Okay. So what is this NBNR model? This is given by equation 1. This xt is alpha star xt minus 1 plus epsilon t. So this is thinning based model. Okay. So star is a negative binomial thinning operator here, and this, if we operate it, so alpha star x, some people say alpha composed x is summation. It's random sum actually, but in this case xt minus 1 is known as it is history, so it is x going to be fixed, and ws are the geometric random variables. Okay. Only constant here we have is this alpha do not take 0 to 1 value, so it takes only 0 to p upon 1 plus p. P 1 upon 1 plus p is the parameter of negative binomial, and it's given here. So once we know the marginal distribution of xt, we can derive the distribution of innovation, that epsilon t, and this can be given like this. So it is a bit crazy. Now there is a question, there was a question that if alpha is depending on p upon 1 plus p, whether it can take care of highly autocorrelated data or not. So to take care of highly autocorrelated data, so we thought that let us check for this various p values. So what we do, we plotted it for various p values, and see after 5 it can even consider the 0.8 correlation. Okay. So for p, and if you see this data with the second data, tuberculosis, it has average about 20. So p comes around 20 or similar, more than 10. So in that case, this process consider highly autocorrelated data. Now, how do we estimate the parameters of the model? So we have two approaches. So we are not considering Euler-Walker because Euler-Walker, both of them are already considered by heuristic and others. So this is the conditional maximum likelihood estimation and the conditional least squares, and these asymptotic properties are already established for them. So we are just using these estimators. Now this is the important, this is we can say transition probabilities of a TPM. So this is probability of xt given xt minus 1. And once we know this innovation distribution and the marginal distribution, we can find these transition probabilities. So these transition probabilities are used to find the maximum likelihood estimates of theta, p, and alpha. Okay, and for CLS we just need the first moment. Okay. Now for coherent forecasting, what we do, the usual forecast is in ARMA models. What we do is conditional mean is taken as the traditional forecast, but this conditional mean need not be integer always. So what we do, we can find the conditional k-step ahead forecast distribution and its median or mode. It depends on which loss function you consider. In some distribution, Poisson median seems to be better. In this negative binomial is 0-1 loss. It's better that you have mode. So for this mode, we have percentage of true prediction measure of the accuracy. So to find this coherent forecast, what we do, we find a conditional forecast distribution, k step ahead, the probability of xt plus k given xt. Okay, and once we have this k step ahead distribution, we can find this its median. Even we can find the mode. We can find even rounded mean also. Okay, and these are it's little complicated, but these are, I'm just giving this statement, and these are these values A, B, C, D, and P naught. Okay. So this conditional mean. So this is our traditional forecast. So once we estimate alpha, p, theta from either CML or CLS estimate method, we can just put it here, and we get this traditional forecast. And this is the variance of this process, xt, k-step ahead conditional variance. Now, some of referees asked us to whether it takes care of this asymmetry or is it highly skewed. So we tried, what we showed is for different parameter combination, it can take this, it can become highly skewed. And we just found out the skewness and kurtosis measures for various parameter combinations, and this blue line is actually kurtosis and red is skewness for various parameter combinations, fixing one parameter and varying another parameter. So you can see it can take care of highly skewed and kurtosis data. Now, how do you verify the performance of the forecast? So we have considered 3 measures to see the performance of this forecast. So first one is predictive root mean square error, that is PRMSE, and this has been verified for around 1,000 simulations. So we have estimate 1 step ahead, estimate 2nd step ahead, forecast 3rd step, and this has been repeated 1,000 times to find out these values. Then we have predictive mean absolute error, PMAE. So the initial 2 are the smaller, are the better. The last one is called PTP, percentage of true prediction. And percentage of true prediction means how many times our forecast hits the actual value. So it is a 0-1 loss. If it hits, it is 1. If it doesn't hit, it is 0. So the highest the value of PTP, better is your forecasting methodology. So these 3 need not be smaller or greater. So first 2 should be as small as possible, and the PTP should be as large as possible. But we have a problem when we have a large counts. Smaller counts, it is the best one. But if we have large count, it's like 100, 200, and if we estimate 201, whereas actual value is 200, then also it gives us 0. Okay, though our forecast is very near to the actual value. So this has the drawback for large counts. We have simulated the series 700 and 500 used for estimation, 200 for this verification. So this is PRMSE and PMAE when data are from NBNR1 model. So we have tried for both the data sets. We have computed these measures when data is from NBNR1, and they computed the measures when data is coming from NGNR1 model. Okay. So from this table we can see here this NBNR, PRMSE and PMME are the smaller, marginally at least small size for some combinations, and for most of the combination they are smaller than this NGNR1. Okay, it's like PME, this is smaller than all of them, and so on. For most of the combination, it's like that. Then, when we have data from NGNR1 model, still it performs better. So we can see here this for PRMSE for NBNR1 and PRMSE for NGNR1, and for all this combination except some few, this model the forecast beats the NGNR1 forecast. Now we have computed this percentage of true prediction, and if data is large count, this PTP always comes down, but for low counts it may go up to 70% or 80%. So see here for this PTP for NGNR1 is NBNR1 is higher for mode in all these combinations. Okay, and for NGNR1 it is smaller. NGNR1, what happens? NGNR1 is based on the geometric distribution, and in geometric this mode is, if it is not transmuted, the mode is 0. So hence it tends to estimate the lower values. And this is from the NBNR1 data. From here also we can see in most of the cases it's beating the NGNR1. It's like, see, so what we choose is the mode is our forecast. Though we have given for mean, rounded mean and median, mode is the best in this case as per the literature. So see here, except for some values it is uniformly better than this NGNR1. Okay. So this is what we did in this forecasting for the over dispersed data, and this is for soap cell data. We can see this sample SAF for Pearson residuals, and we can see that this Pearson, there is no spike, significant spikes. So residuals are quite independent, and this model fits better. And so we have used another probability integral transform from knitting and Shadow, and Fockianus also used this. So this should be as uniform as possible for this if your forecast distribution and actual data follows the same distribution, and it's nearly uniform. It's not far away from the uniform. So what we can say that this model fits better to this data. So I have not added. So similar analysis has been done for this tuberculosis data, and ACF for this Pearson residuals and PIT also behaves similar. So I have not added. So that's these are the point forecasts for the soap cell data. So we have these last 5 values are forecasted using this, and this is using mean. It's not rounded. It's mode, median, and this is the HPP interval. So HPP is the highest predictive probability interval, and it is of size 90. So 90% HPP. So these are the forecasts using our methodology, and yeah, that's it. In this, these are some of the references. Thank you.
Okay, thank you, Dr. Man. So there is now it is time for discussion. So, if there are no questions, is there any question?
Yeah, just one comment. So you have shown that PIT last, right? Probability integral transform.
Yes.
So does it give a good indication of uniformity?
Yeah, it's little bit away from uniformity, but it's not far away also.
Now, what are the other residual analysis you have performed for this?
So I did this ACF for Pearson residuals.
The ACF. You don't go for any statistical test for testing.
So yeah, I didn't go because in these models, people have used PIT, Pearson residuals mostly, and PRMSE, PMAE, forecast residuals, forecast errors.
Yeah, PIT is
So
okay
we are
if it
going with
gives you
majority.
good uniformity.
Yeah, so we are trying to, if we are lacking in capturing some more information.
Achha, okay.
But in some of the published also, this PIT behaves similar. It's not exactly uniform because for real data, it's difficult to have exact uniformity.
Oh, okay, thank you.
So, sir, can you shed more light on that HPP concept? HPP, highest probability. What is that?
Highest predictive probability region. It's like your HPD in Bayesian.
Okay.
So it's similar for this discrete distribution.
Okay, sir. Yeah, thank you, sir.
Okay, let us thank Dr. Manik for the nice presentation. So now I invite Dr. Arindam Chakrabarti, who will be talking on assessment of impacts of non-prognostical interventions in curbing COVID-19 spread using renewal theory. So over to Arindam Chakrabarti. Sir, please.
Yeah, please unmute your mic, Arindam.
Yeah, I did. Is it visible right now?
Yeah, it's visible and audible also.
Okay. Thanks a lot. I would like to thank Professor Balakrishnan for inviting me for this session. I think after 2012, I am seeing him after such a long time. So I would like to thank Professor Satish Kumar also for giving me the chance to present our work. So this is something not very similar to the topics that has already been discussed in this session. It's a bit more like applied, and it is on something which we know every day nowadays for last 2 years, and we are fighting with it. So it's about modeling the spread of COVID-19, and in this work we try to assess the impacts of some non-pharmaceutical interventions. So one thing I want to say at the very beginning, that this work was done in last year. So it is the data, now we have enough data, we have more data right now, and we have second wave. But when we did this work, it was only the first wave which was coming. During that time we did this. And now we had some anticipations that something will happen to the virus and it will go by its own, then probably we won't have to do any work further. But now we found that it's not going very easily. So lots of work will be done and has been done and we are also doing a part of it. So I thought that this is something which we did last year, and now we want to do something from here. So this was a joint modern work with Professor Kolanda. She was my supervisor, is now in IIT Bombay, and Professor Kashina Chatterjee, who is now associated with Augusta University. So this is something that you just assume that you are in 2020. It's not 2020.
Professor Arindam, you can make it full screen.
Just a minute. Just a minute. I'm trying to make it PPT.
Yeah, in the bottom there is that symbol to make it full screen. Or
yeah. Just a minute.
I think Control L.
Yeah. I'm trying to do that, but
or otherwise in the bottom, there is a small near to that percentage of the 65 something.
Yeah, I'm just but while I was trying to do that, something went wrong, and okay. So I have to wait for maybe a few seconds. Yeah, it is. So I will increase the size. Probably that will do.
Yeah, that's enough. No problem.
Is it okay?
It's okay.
Okay. So actually, this is when we are talking about this. We're doing this job. There is no effective vaccine was there. So effective still is under a big question mark. No vaccine was there. So when people come with this, will come across this virus, then the first thing is that that came into our mind and everybody's mind, how to stop the spread, because it's highly contagious. So the absence of vaccine put us in a disadvantageous position. So what are the non-pharmaceutical interventions that could be possible, or that could have been taken by the different countries over different point of times to curb the spread of this virus? So what are the NPIs they have considered, like closing of educational institutions, ban on travel, maintaining physical distances at different point of time. But these were not sufficient enough to tackle the spread. So all these countries, they were compelled to go for this lockdown. And we know that how fatal this lockdown can be for any economy. But since the spread was like a fire in a forest, so lockdown was inevitable. But still, after announcing lockdown, throughout the world, this could not be contained. So, like for us, it was worse compared to the other European countries, where there was some sort of I should say restraint was there, but for us it was not there. So infection spread throughout the country. So lockdown, we had to apply for the lockdown. Then there is a question that what sort of lockdown will it be? Will it be complete lockdown? It will be partial, or there won't be any lockdown? So then there is a trade-off, because if I do for the complete lockdown, then I have to sacrifice the economy. But if I don't go for it, then I have to sacrifice human lives. So this is something that we were really in a stick that what we should do. We don't know what we are trying to do. So it is something that you have an enemy, and which is completely unknown, and you want to predict about the behavior of that enemy. So it was a challenge for the epidemiologists to predict the progress of this infection caused by any unknown virus. And I was a part of Bombay IIT MHRD group, where we were trying to model or try to predict the nature of the infection, the number of infections or deaths for any state, or if we go to any micro sector like district or even for subdivision. That depends on the available data. So people were using some model ACR, ACIR, modified, adaptive ACIR. So lots of work was going on. And to be very frank, most of the works were not being able to predict the situation correctly. There was because the thing is that the virus was unknown, and we had very little information about the virus. So we have to borrow information from the other infections like SARS or MERS that has happened already. So we got some idea from that how a virus goes. But the problem is that every virus, they are different in their nature. So the virus which is causing SARS is not, the behavior is not same as the virus which is causing SARS-CoV-2, because the mutations are different. So a lot of mutations are happening in SARS-CoV-2. So that makes this virus more unpredictable. The only we tried to model this we had is the Wuhan data, and we got some idea about the spread of this, how it is going from one human to another. Now this knowing, so it is imperative that we have to use some Bayesian technique, because we don't have much data. So even if this Bayesian technique is not sufficient, because the fatality or the attack rate depends on several factors like genetic profile, particular mutation of the virus, and many confounding factors. So as I mentioned, that we had to borrow information from other viruses too. But these sort of assumptions always put any prediction model under severe threat of reliability. And it was in 2020, Luo published one paper where it was claimed that 90% of the active cases would have been solved by May 27, 2020. So which received strong criticism. So that is the problem when we are dealing with an unknown virus. We don't have much idea about the virus, and we had to borrow information from the other virus and to predict. So it was a really challenging thing. And this spread of this virus is controlled by a number where it is called R number. We refer to this as the reproduction number. So R refers to an infectious disease capacity to spread. So it actually signifies the average number of people that one infected person will pass the virus to. So R number, it is not constant, so it changes over time. So if the place is densely populated, then it is highly likely that this R value will be large, because more people will be affected and they will spread the virus in no time. And there are two R numbers that are concerning us or till date. So the first one is called R naught. R naught is the average number of secondary infections. So we call this as basic reproduction number. So it is something that where everyone is susceptible or is not immune to that disease, which happens at the beginning of an epidemic or pandemic. So this R naught will be computed at the beginning of this pandemic. So if, for example, R naught is 5, the simplest interpretation is that means that each infected person will infect at least 5 other people, and they will infect another 5 each. So it will go like branch. So in no time, we'll have lots of people get infected. So this R naught is affected by the rate of contacts in the population, the probability of infection being transmitted, and the duration of infectiousness. So these 3 things are there. So rate of contacts, probability of infection, and duration of this infectiousness. So what is expected that if we do lockdown or any sort of NPIs, we want to brought down R naught to be less than 1. Because we know that if it is more than 1, that means it will grow exponentially. And countries like India, where we have a dense population, the situation will go out of our hands, which ultimately did. The other R number that is important is called effective reproduction number, that is called RT, which is time dependent. So it is at any point time t that we want to see how this reproduction number is behaving. And regular and frequent computation of RT is needed to take some administrative decisions, that whether to impose lockdown, partial lockdown, containment zone, or something like that. So it will depend on this RT value. So this computation of RT value at different time points will be necessary for implementation of different administrative decisions. So this is a very important parameter to evaluate the effectiveness of current public health interventions and plan additional interventions as required. To model any virus or the prediction of any virus, we need this concept of serial interval. What is this? Basically, it's in layman's knowledge language. If I say that this is the time for which the infector and infected shows the symptoms. That is the time interval between onset of symptoms in the primary, we call this as infector, and secondary case, it's called infectee. So this consists of an incubation period, because when you get the virus, the symptoms will not come in 1 or 2 days. It will take, say, 5 to 7 days before coming to the infections. And this is called incubation period. And you have this infectious period from exposure to infection. This is sometimes we call referred as germination time, which is defined by as the average time taken for the secondary cases to be infected by a primary case. Now, how to find or how to estimate this serial interval? And it is very hard, because we don't have any data, right? When we try to do this, so we have to use some meta-analysis data. On mostly people use this meta-analysis to find estimate of the data based on the previous studies, which has been done, like in case of SARS or MERS or those virus affected diseases. So serial interval is one important issue. Now there are 3 simultaneous models that will be there to model this spread of this virus. The first one is you need to model RST. I put S for the particular space because place for here. I will show that we have taken the two states, Gujarat and Maharashtra, and we got district level data. So RSS means the asset district at time point T. And this the second is the modeling number of new infections, IST, and then modeling number of new deaths. So these 3 models will be done simultaneously. Okay. So first we want to model the number of infections at any day. So this is the number of infections in infected cases at any day can be predicted using a reproduction number and the weighted average of the previous day's affected figures with discretized serial intervals. So this theory has a strong statistical support. So you can see the papers of Fraser, Cody on Novelate. So they did this. So if your GT is your serial interval distribution, then the interval for the infection for any place S at time point T can be expressed as RST times tau from 0 to T minus 1. So this is the, when I'm talking about the number of infections at time T, so I'll go up to T minus 1, and this is the contribution from the previous infections. So this is how we model IT. Now we need to discretize the serial interval, and this serial interval is discretized as GU is integration U minus 0.5 to U plus 0.5, and G tau, where U ranges from 2, 3, 4, and G1 because it's non-negative. So G1 we compute it separately from 0 to 1.5, and this is we got this from the past experience that GT is usually takes a form of gamma distribution with mean 6.5. So this number mean 6.5 and 0.62. This we got, or we took this from this set and the paper that was published in Nature into 2020 itself, and they use some previous knowledge of SARS and other viruses, and they have come up with this particular form of this gamma distribution, that mean will be 6.5 and variance will be 0.62. So this is how we discretize the serial interval. Now the daily death, which we call about DST, this daily death DST are modeled using a positive real valued function, small dst, which is the expected value or expected number of deaths attributed to COVID-19. And it follows a negative binomial distribution. We assume that this follows a negative binomial distribution with parameter dst, and this is the scale parameter dst plus d square st over chi, where chi follows a half normal distribution. Once again, this model was, we got this model from the reference I have just talked about. It was published in Nature last year. Now we need to link them. So how to link them? So to mechanistically link our functions for death to infectious diseases, we use a previously estimated COVID-19 infection fatality ratio. We call this IFR, together with a distribution of times from infection to death. This time from infections to death, I'll come to my next slide, where we'll once again just divide this into two different random variables. The IFR is derived from the estimates assuming homogeneous attack rates across age groups. However, this to consider because we know that the severity is not same for all the age groups, so age specific IFR will be computed, and they will be that will be using the particular number of affected individual within that age group. So this will be age group specific for sure. Now, as I mentioned that the estimated epidemiological information from previous studies, we assume that the distribution of the time between infection and death is the sum of two independent random timings. One is the incubation period, because once the virus enters our body, it will stay there for some time. Then the time between onset symptoms and death. So symptoms will be there, and finally there will unfortunately death. So this will be if we add these two independent random timings, then we'll get this distribution of this pi. So clearly it shows it has two parts, and pi is modeled as a mixture of two gamma distribution. The first part corresponds to the incubation period, and the second part corresponds to the time between onsets of symptoms to death. So if I consider these two random events together, I will get the distribution. Now under this setup, the expected number of death, the ST is defined as IFR into sum over IST pi t minus pi. So IST is the number of new infections on day tau in place S. So as you can see that the death will come from the number of infectees only. And pi is once again discretized. And so the number of deaths today is the sum of the past infections weighted by their probability of death, where the probability of death depends on number of days since infection and the infection fatality ratio. Now, till this point, we have not come across to accommodate the NPAs, the situation where these non-pharmaceutical interventions could be, the effect of the NPAs could be studied. So what we did while we modeling RT, we tried to consider this as covariate. So RST is defined as, I will come to the first part, this is some adjustment factor. and RS naught is, as you see, is 0 T 0. That means the baseline, and RS is for the S place. Then we have some 2 into phi inverse minus alpha star delta, where delta is the indicates the level of lockdown. So for example, if I say there is no lockdown, delta to be 0. If partial lockdown, delta is taken to be 1, and if it's a complete lockdown, it will taken to be 2. So 0, 1, 2, these are which we give, but if someone says that they want to give 0, 1.5, 2.3, so these are merely indicators. These numbers are merely indicators. So we want to show that if your delta is 2, that means that there is much more stringent lockdown is there. So it is expected that RST will be less. The first part of this expression of this RST corresponds to this is the correction factor, that if something happens like herd immunity, or all the individuals are already got affected, then RST will not increase, going to go anymore. So to consider that feature, we have introduced this correction factor. And this is delta is used as a level of lockdown. So this is here we can introduce more covariates. So just like that, if we want to say that lockdown is one covariate, but we want to introduce some other interventions also, we can do this in this modeling. So what will happen that instead of alpha, there will be alpha 1, alpha 2, alpha 3 like this. And the quantifying partial lockdown is another subjective thing, and it will be decided by the policymakers. By policymakers, I mean the government or the local administration. Then when they will consider what is partial and what is not. And this model has the flexibility that it can incorporate, or it can take care of more covariates. So this is the setup we have. So we can write down the likelihood, and then we'll go for the Bayesian inference. So these are the priors that has been taken, and we had used STAN software, which is very stable. And for the posterior distribution, to generate the posterior distributions, we use this. And this is the data that we got from COVID-19.org website. We use that data, and when we did this work, it was 83 data points were there. We had to exclude a few districts where a number of deaths or very few cases were there, and we tried to predict for 15 days. So if here we predict it for more than 1 month, but what we have started that this 1 month prediction, or if the window exceeds more than 1 week, then the estimates were not that reliable. But since we had data till 23rd May, and we want to see what is the situation till 30th June. So we try to figure out, or to try to predict 3 situations. One is that what would be the value of the RT, and what will be the number of infected cases, and what will be the number of deaths. And this will do for each of the districts under these 3 conditions: that suppose there is no lockdown, there is partial lockdown, and there is full lockdown. And after we go this, after the application, this is I don't think it's very clear. I'll just try to mention you what these 4 figures are. If you see the left one, the top left, so it is the baseline reproduction number for Maharashtra. So in the y-axis, these are the district names like Nagpur, Ahmednagar, Thane, or something like this. And if you see the baseline reproduction numbers, all are more than 1. So when we started the work, we found that this is more than 1. It's more than 1.3. Then we try to predict RT on 30th June under no lockdown situation. So if no lockdown happens, then what will happen? So we'll find that for most of the districts, that this RT value, they got increased. And when we have this situation that partial lockdown will be there, these values are less compared to the no lockdown situation. And when we have complete lockdown, then as expected, the RT values are not very small. I should say that they are less, not by the big margin or like that. So if you were, say, for example, it was 1.11, then it got reduced to 1.09 or something like that. So till situation was in 13 June 2020, when we were talking about, situation was already out of our hands. Then we tried to figure out that what will happen to the number of infections. and we predict this for like districts like Mumbai, Nagpur, Pune, Thane, or something. So you can see the pictures. They are showing the equal. They are showing equal pattern, that if there is no lockdown, we have steep curve. But when we have some partial lockdown, then it's still increasing, but not that amount. But and if we expected that if a complete lockdown was observed properly, then we could have seen a flattened curve. But unfortunately, we didn't see that when we try to validate our data next, because we realized that the lockdown was not imposed or followed properly. Probably then that is the reason when we have this sort of situation happen that doesn't meet our expectation. So we did this for all the states, all the districts for Maharashtra. We did this for the number of deaths also. So what will be the number of deaths during that time? Number of death was not that big, or that was not that huge. That's why for most of the districts, the prediction were not good, and because we had very little data, just like unlike Mumbai and Pune, where we have during that time also we have a good number of deaths there. So, but when we talk about a second wave, we have seen a lot of deaths last year, with the last 1 year. So now the situation would have been different if we perform this thing which we were doing. So we replicate this thing for the state Gujarat, and for the state Gujarat we did this for each of the districts where we have sufficient data. We predicted this thing, and like the district like Ahmedabad, Vadodara, and Surat, we see the drastical changes where they were expected if complete lockdown could have been followed. But this, as I told you at the very beginning, this is work that we did last year. Now we want to revise this model in terms of modeling strategy and incorporating more information. Like since now we don't have any restriction to move inter-district, and we know that if the spatio-temporal model will come handy in this situation, so we'll try to incorporate the spatio-temporal part, spatial model in our model. Nowadays we have more data points, because when we started it was only 83 data points were there. Now it's almost 1 year, so you have more than 440 data points. Currently we are trying to figure out the genetic information, and we'll try to see that how these mutations are performing. So we have started the work in this direction. We have identified those statistically significant mutations for each of these states. Like for Punjab, we have done this, and we could find that there were 13 mutations which we found using some GLM sort of thing, that we found that 13 of these mutations are statistically they are significant. And we are trying to figure out for each of these states, and then we'll try to see what is the whole picture for our country. In the entire thing, we didn't consider the asymptomatic cases, because this is a lack of, you will say this is a lacuna of this model. But asymptomatic data, getting asymptomatic data is another difficult thing, and you can easily understand that getting good quality data is a challenge, is the biggest challenge probably to model this sort of things. So a lot of work. This area deserves, I think, more proper attention. If you consider the last 1 year or last 2 years, we have numerous paper published in ABCD journals, but not most of them are of a significant. They don't have any significant contribution. So we think that now time has come to try to get some ensemble model or some super model thing, so that this sort of predictions could be made in much more meaningful way. So that much, that's what I had to say. And happy National Statistics Day. Stay safe. Thank you.
Thank you, Dr. Arindam Chakrabarty, for the good presentation and on a recent topic of interest you have spoken. So this is time for a discussion.
So I have a question. This is Shuli. Yeah. Hi, Arindam.
Hi.
So this work you have done in last year's COVID data. Yeah. So one thing we saw is that, I mean, from that website where you took the data, I know that time to death was not there. So what we saw, so we looked at a lot of municipality data because these municipalities we were working with, Pune municipality particularly. So we saw the time to death at that time was very small, not 17 days. In India, almost immediately people were dying if they got the infection. So in 5 days or so. So I don't know if that will change anything. So if you want, maybe I can, I can give you some more information from that data because we have patient level data. So yeah, so that's what one thing we saw, and that IFR, so that thing, if it will work now, I am not sure. No, for the second wave, it's very different. There may be other.
Right.
Yeah. So for India, those all those time to death and everything seems to be very different from the Western countries. So.
Yeah, now we are planning to incorporate genetic information because mutation is something which controls RT.
Yes,
so,
yes.
My PhD scholar is doing that in that area. So she has already identified for Punjab 13. She gave me the data, and we could find the 13 mutations that we found that then they're very statistically significant. Then we'll try to incorporate that as covariate, and we'll try to see
Okay.
the
Okay. Yeah. Okay. Thank you.
Okay. I think there was in the chat box, there was a question.
Yeah,
so they wanted references.
Yeah. Is this visible?
Yeah, visible.
Yeah. So if anybody is interested in modeling section, then the paper of Flaxman and Mishra in 2020 Nature is important. And if you go to their website, they have more than, I think, 100 publications regarding this COVID situation. So you can get an idea about this.
Okay. If there are no questions, I thank Chakrabarti for good discussion and presentation. And I would like to take this opportunity to thank the organizer, Professor Balakrishna, and also Professor Satish Kumar, and apologize Professor Satish Kumar for being late for this session because of my other preoccupied engagement. So I'm sorry for that. So I give it over to the organizer, or Satish Kumar.
Thank you. In fact, thank you, Professor Pandit, for chairing this session in a nice way, and Professor Balakrishna organized a very nice session in a very good manner. All are very potential, very good speakers, and I utilize this occasion to extend our gratitude to each one of you, the speakers of this session, and on behalf of the Department of Statistics and ISPS and KSA. Once again, thank you all. Give a big clap to each one of you.
Okay, thank you, Suli, Arindam, and Manik.
Thank you
all.
Very much.
Yeah, thank you.
Okay, thank you.
We would like to get your association in future also. Each of course. Speakers.
Thanks to Parameshwar Pandit also.
Thank you.
And the afternoon session will start at 1:45 itself. We have the short of the time in the lunch break time. Okay. Okay. Let us meet at 1.
I will for 1 hour, 2 to 3. I will join my statistics department celebration.
Yeah. Okay, Professor. Okay. Yeah, please.
Okay. Bye.
At that time, also you please join with us.
Yeah.
Again for your this opportunity.
Thank you, Professor.
Thank you all for your support. Let us join at 1:45. Thank you.
Thank you, sir. Thank you, Satish Kumar, sir.
Thank you. Thank you all.
Hello. Hello.
Good afternoon.
Hello, sir. Good afternoon, sir. Good afternoon.
Good afternoon, sir. Good afternoon. Good afternoon. Professor Shamir here. Yeah.
Good afternoon.
Good afternoon. Good afternoon. Good afternoon, sir. Good afternoon. Good afternoon.
Murli, sir. Good afternoon.
Yeah. Good afternoon. Good afternoon.
Okay.
Yes.
Good afternoon. Yeah. Baiju, sir. Baiju. Dr. Baiju.
Yes, sir. Yes, sir. I'm here.
Okay. Yeah.
Okay. Good afternoon.
No. I think let us start the session because this is the right time, and others will join in the meantime. Dr. Baiju is presently working as a faculty in Government College, Trivandrum, and he is a very active researcher and is a good teacher. He has several credentials. I'm not detailing more for the time being because I think Baiju will introduce our chair and initiate the session.
Okay, thank you, sir. Good evening, all. Happy National Statistics Day. And we are in the post-lunch session of our fifth edition of Wsta 2021. And it is organized by our Professor Sadish sir and the Department of Statistics, University of Kerala. And it is the technical session number 4. And it is a special invited section. And we have an eminent agriculture statistician as well as a biometrician, which is none other than Professor J. Srikumar sir of Indian Council for Agriculture Research, and he is now working as a principal scientist in CTCRI Srikaryam campus, and with his huge contribution to the field of agriculture statistics, he is known as a data analyst and also a data scientist rather, and he is with us to chair this estimated session of Wsta 2021. And I also express my pleasure and thanks to Professor Sadish sir to co-chair this important session of this webinar, and Professor J. Srikumar sir, and it is your turn to address the audience. Please take over the session.
So good afternoon to all. Am I audible to all?
Yes, sir.
Yeah, bro.
Okay. So this is the technical session number 4, and we are having 2 lecturers here. And first of all, let me welcome everybody to this particular session. And we are having 2 speakers in this session. And Dr. P.G. Shankaran sir is presenting about the non-parametric inference for panel count data with competing risk. And Dr. S.A.B. on some new classes of couples and their applications. And you all know Dr. P.G. Shankaran. He is the professor. I think there is no need to introduce by myself to all the participants. He is the professor and pro vice chancellor of Department of Statistics, Cochin University of Science and Technology, and he has many positions held, like VC, Professor, Reader, Director, Center for Population Studies, Cochin University of Science and Technology, and many positions he has, and he got many visits and fellowships to different countries. and he have memberships in professional academies and bodies in many professional academics and bodies. And let me welcome Professor P.G. Shankaran for the first lecture. Thanks.
Good afternoon. Thanks for nice words, Dr. Srikumar.
Yes,
Okay, at the outset, I thank Dr. Sadish and his team for inviting me to deliver some of the recent research on panel count data. This is a joint work with Dr. Sridevi. She has done this work last year, and this work is already published in Journal of Applied Statistics. Dr. Sridevi completed her PhD under my supervision 4 years back, and we have been working on different aspects of recurrent event data. This is one of the special type of recurrent event data, and the outline of the presentation is in the following way. A small introduction and motivation of the problem, then methodologies and inference procedure, followed by simulation studies to assess the performance of the estimation theory, and a real-life data analytical problem is carried out, followed by conclusions. In many lifetime studies, we may not be able to obtain complete information on the event of interest through various reasons. There's maybe generally referred as censoring, and for example, consider the situation where interest is on the occurrence of an event which can repeat many times. If the subjects in the study are monitored continuously, it provides the information on the time of occurrences of all events, and we obtain recurrent event data. One can refer Cook and Lawless 2007. In some cases, study subject can be examined only at a discrete time point, as the continuous observation is too expensive or impossible. For example, if you want to know the recurrence of certain diseases, what we do is we have a set of subjects or set of individuals suffering due to that particular disease, and we may follow these individuals and note the number of recurrences and the time at which the occurrence of a particular event happened. In certain cases, we may fix the number of the time at which the occurrence of disease happens. So instead of a continuous time, we have some discrete time point at which the subjects are examined. As a result, only the number of occurrences of the events between subsequent observation times are available, where the exact occurrence of the events will be unknown. That is, in such a context, for example, continuous observation is impossible or it's not too expensive. We have data on number of occurrence of particular events instead of time at which that event occurs. The data obtained in such a situation is generally referred as panel count data. One can refer the initial idea on this panel count data in Kalfish and Lawless, but a recent one, later one is Sahu and Han. Then panel count data is also referred as interval count data or interval censored recurrent event data, which was studied by Lawless and Sang 1998 and Tal and Latin 1988. If each subject is observed only once, a special case of panel count data occurs, which is commonly referred to as current status data. So in current status data, instead of measuring or observing events at different time points, we observe only one time point So the observation of each subject at a single time point is available. An extensive review of the panel count data is given in Sang and Sahu 2013, a book, which is a book. The standard method in the analysis of panel count data is focused on mean function or rate function of the underlying recurrent event process. In all recurrent event process, we are interested in two aspects: either rate at which the recurrence occurs or mean number of recurrence during a time point. So mean function and rate function are two important quantities. And now we have a data. Consider the data from the study of nuclear power plants given in Sun and Sahu 13. Study consists of observation time and the corresponding number of losses of feed water of 30 nuclear plants. Since only one observation taken for each subject, we actually have a special type of panel count data, that is a current status data. So we have a plant 1, we have observed ones at a time point t equal to 15 years, then the number of recurrences is 4. If you take the plant 2, the time at which this observation is 12 years and 40 recurrence. So these are the 30 values corresponding to 30 plants. Now consider a recurrent event study that involves an independent subject from a homogeneous population and in which each case gives rise to a counting process, NAT. So NAT means number of occurrences or recurrences before time t, corresponding to an ith individual. Suppose that only panel count data are available for NATs, then observation times are TI1, TI2, etc., TIMI for subject I, and M is the representing nothing but M is the number of times at which ith subject is observed. So it can be varied. For first subject, you can observe 2 times, and second time object you can observe 3 times, like that. It need not be equal. NIP is the NITIP, that is the observed value of NIT at the time TIP. That is, for each individual, then subject I is observed MI times, we have a vector, observed data vector, that is MI, number of time at which each individual is observed, TIP, time at which the observation is carried out, NIP is the number of observed recurrences. Then expectation of NAT is the capital lambda t is the mean function of the process, and our goal is to estimate this expectation of lambda t. That is the usual procedure. Assume that we have a simple situation where all study subjects have same observation time points, but the number of observation may be different. That is, TIP is same observation time SP for all P and I. Then we have only S1P, S2, S1, S2, etc. SM. They are the distinct observed times corresponding to all individual. Then a natural generalization of the estimate of this mean function is something like the weighted mean that is given by this quantity. This is the sample mean of observed NIP from the subject still under study. Now, in general situation, we consider where the subject may not have the identical observation times. So the above estimator cannot directly be used in this estimation because it will always underestimate. Then we define. We can still define the sample mean at each time point SP based on available observation, but the estimator that does not share the non-decreasing property of lambda t. As time increases, actually the mean should increase because number of recurrence should increase, time increases. To fix this, we have IRE estimation procedure, isotonic regression theory is introduced, which is calculated using pooling Violators algorithm. Pooling Violators algorithm. That is define L1, L2, etc. Lm and N1 bar, N2 bar, etc. Nm are the number and mean values of observation made at SP. Then the isotonic regression theory, it follows that the IRE estimate of the mean function is calculated by the formula capital lambda evaluated ST is maximum of that quantity. This is a maximum formula. This under the assumption that number of events of the recurrences are non-homogeneous Poisson process, a non-parametric maximal likelihood estimator and non-parametric maximum pseudo-likelihood estimator for the mean function is proposed by Wellner and Sang, and these estimators are coincide with this IRE estimator. Then Tal and Latchin 1988 and Lawless and Sang 1998 considered the analysis of parent count data using rate functions. A gamma frailty model for the non-parametric estimation of the panel count data is proposed by Sago and Tom. Then some of the recent developments in the analysis of panel count data include the works of Su and Chiu 2018 and 19. So this is about the review of the literature on this panel count data. We have a slightly different problem where the recurrence can be occurred due to various reasons or various causes. So in medical or industrial research, competing risk data arise when patients are exposed to the risk of failure due to more than one cause of failure. Panel count data with the competing risk originate in a study where when each individual is exposed to risk of multiple events which are observed at discrete time points. So we obtain such data naturally from survival studies where the interest is focused on occurrence of competing events which can be observed only at discrete time points. Even though panel count data is studied by different researchers, to the best of our knowledge, competing risk panel count data is not explored in literature. This motivates us to study the features of panel count data in a complex problem. We developed an isotonic regression estimator for the cause-specific mean function of the underlying recurrent process of the panel count data with the competing risk and study substitutory properties. And as a second step, we have considered a testing problem where we try to test whether the effect of different causes on the lifetime are identical or not. In the case of right-censored data, many researchers investigated this testing problem, including these papers. Comparison of various results is not addressed by researchers in the context of panel count data. This fact ensures the significance of our study. Now, our method. Consider a recurrent event study on n individuals from a homogeneous population where each subject is exposed to the risk of failure due to k causes. That is, suppose we have a set of patients who are suffering due to a particular who are admitted to hospitalization. Then when you look at this patient, the reason for admission to the hospital may be different. So we have a situation where the reasons for the hospital admission is different. So this is one example of competing risk data with the recurrences. So suppose the subject can be observed only at a discrete time point, so that only number of recurrence of the events due to different causes between the observation times are available. Now each subject gives rise to a counting process NIJT. NIJT is the number of occurrences or recurrences of the particular event before time t due to cos j equal to 1 to k. Then we have distinct observation times ti1, ti2, etc. tim corresponding to ith individual, and nijp denote the number of observation time on ith individual due to cos j at time tip. That data is on the form mi as before, but we have tip, that is the time at which observation is carried out. Then we have nijp, j equal to 1 to k. Then we have capital lambda jt, that is expectation of nijt, which is referred as cause-specific mean function. That is the mean function corresponding to nijt. Then we have ordered distinct observation times S1, S2, etc. Sm. They are nothing but they are basically the ordered values of Ti1, Ti2, etc. Tip. Then LPJ and NPJ bar denote the number and mean values respectively of the observation made at SP due to various causes. Then then lambda Pj, that is a notation of lambda JSP, be the cause-specific mean function of the process at NJT. Due to the order decision, we have these mean functions should be non-decreasing. Now, using max-mini formula given in Robertson 1988, we can obtain the IRE estimator of the mean function, cause-specific mean function, which is basically given in equation 1. When j equal to 1, automatically this reduces to earlier situation where we do not have committing risk, we have a single cause of failure or recurrence. Under certain conditions, the estimator capital lambda j t is strongly consistent to lambda jt, and further this converges to a maximum point of a two-sided Brownian motion, which is formally known as Chernow distribution. I'm not going to discuss these asymptotic properties of this estimator in detail. Now, coming to the testing problem. So, our objective is to test whether the failure mean functions corresponding to two causes are equal or not. Basically, the equality of mean functions can be tested using that capital lambda pj, that is h0 is lambda jt equal to lambda j prime t for all t j not equal to j prime, against they are not equal for at least one t on j. Then the testing problem can be rewritten as lambda j t is lambda of sp. Lambda j sp is lambda of sp divided by k, where lambda sp is nothing but summation of lambda j sp. So then lambda h0 becomes lambda j sp equal to lambda sp divided by k against lambda j sp not equal to lambda sp, because total expectation of njt, that is lambda jt, then if you take j equal to 1 to k, expectation of njt summation j equal to 1 to k will be, give lambda t, that is expectation of nit, that is idea. Then to test h0 against h1, we use a IRE estimator of the cause-specific mean function lambda j. So basically what we do is we take the difference of difference between lambda j sp and lambda sp by k, or departure of h0, that is idea. Let np and np had denote the number of and mean values of the observation made at sp, then we can have the estimator of lambda hat p, that is again the same situation, that is IRE estimator. So then the procedure, similar procedure of estimating overall cumulative distribution function by ignoring cause of failure information is used in series paper in the current status data. Then to develop a test statistic, what we consider is we consider the departure function, and then you add a weight function and define a quantity vjt. VJT is integral 0 T WU into that departure value. Then W, that is a weight function, is a appropriate data dependent weight function, which is used to compensate the effect of censoring and to set it remaining asymptotically distribution free. Then this is similar to the one proposed by Pepe and Mori in 1993 and Lin in 1997. And then you have under H0, what happens is this lambda j hat minus lambda hat by k, that will be very small, and this should be almost equal to 0. So when H0 is small, this quantity will be different, so the VJT will be larger. That is the idea. So to test the hypothesis, we have this VJT for different j, and we have a vector V tau, and the matrix sigma tau, which is nothing but variance covariance matrix of VJT. That is the sigma tau. Then the estimate of sigma tau will be sigma hat tau. So we construct a quantity Z tau, that is V prime tau, that is the vector transpose of the vector, V sigma hat tau inverse V tau. Then we can prove that these VJTs are, as proved earlier, this is approximately a Brownian process, and at a fixed T, it will be a Chernow distribution, which can be approximated by normal distribution. Therefore, this VT is asymptotically a k-variate normal distribution. V tau, V or VT will be asymptotically a k-variate normal distribution with zero mean vector and variance covariance matrix sigma. Therefore, this quadratic form given in 6, that is Z tau, is nothing but it is a chi-square random variable. That is the basic idea. With the then reject H0 if Z T greater than or equal to this value, which is the alternate value of this. So expression for sigma tau is complex, hence estimation of sigma tau generally requires smoothing. So one can also use bootstrap resampling technique to estimate variance covariance matrix sigma tau, which we have done in our data analysis. So basic idea to construct a departure measure, and we proved that this measure follows a normal distribution. They construct a quadratic form, then this quadratic form follows a chi-square distribution. That is the idea. So we have solved two problems. One is the estimation problem of the cause-specific mean function. Next is the comparison of various risk due to occurrences. Various risk in the recurrence problem. So we developed a test statistic. Then simulation studies. Consider the situation with two competing risks, J equal to 1 and 2. Generate a panel count data. To generate this panel count data, we first generate MI from uniform distribution. Then, which is a maximum number is restricted to 5. Once MI is generated, then TIP is generated from another uniform distribution. Then we number of recurrences due to cause 1 and those 2 are generated from bivariate causes because there are two causes, NA1 and NA2. Then each random variable follows Poisson distribution, and this marginally this follows Poisson distribution. Then expectation of x equal to theta1 plus theta2, expectation of y equal to theta2 plus theta3. The covariance between x and y is theta3, which gives the measure of dependence. This procedure was earlier used to generate random samples in recurrent event data by Balakrishnan and Soho. We have used 3 different weight functions for testing problem. WT equal to 1, WT is equal to n, WT is the mean function estimator. Then we have calculated absolute bias and MSE of the estimates. For that, we take 1,000 resamples and calculate bias and MSE, and various combinations of theta1, theta2, theta3 are considered, and absolute bias and MSE of the estimates for the particular for the parameter combinations are given in table 1. Similar results are obtained for various other combinations. We have not presented all the results here. When theta1 equal to theta2, then one minute. Before that, I will consider the estimator of the mean function. Two mean function. There are two causes, mean function. This is a bias and MSE. Okay. Both the bias and MSE decrease with increase in sample size. The absolute bias and MSE values decrease for large observation time and reach at a peak value around middle observation time. If we set a θ1 equal to θ2 and non-zero value for θ3, it indicates a situation where two cos mean functions are same, hence H0 will be true. That is, expectation of x is θ1 plus θ2, θ1 plus θ3, expectation of y equal to θ2 plus θ3, therefore θ1 equal to θ2 reduces to identical cos-specific mean functions. As θ1 and θ2 are far apart, two mean functions will differ much, which results in a situation where null hypothesis is false. Thus, the situation with the θ1 equal to θ2 gives type 1 error, and all other situations give power of the proposed test. These are this θ1 equal to θ2, this case, θ1 equal to θ2 case, that is the significance level, around 5% level. The second one is at around 1% level. But much more here, when sample size increases, it close to the actual value 1. So this is you can see here also 1 and 5.53, 0.9. This is WNT. What we could see is that type 1 of the test approaches the chosen level when θ1 equal to θ2. Test has a very good power interval which increases as the number difference between θ1 and θ2 increases. As the value of θ3 increases, the power of the test decreases slightly. Among three weight function, W equal to capital lambda hat gives a better power. These observations are same in all combinations of θ1, θ3. Now, the proposed estimation procedure is illustrated using a real-life data set from the cancer studies given in Sun and Sahu 2013. Data was discussed, studied by Lee also 2008 and Lee in 1997. Primary objective of this study was to evaluate effectiveness of drug DFMO in reducing new skin cancers in a population with a history of non-melanoma skin cancers, basal cell carcinoma, and squamous cell carcinoma. Data consists of 290 patients with a history of non-melanoma skin cancers, and they were supposed to be assessed and observed every 6 months. The data include the number of recurrences of the two types of recurrent event. We treat these two types of cancers as two competency data. In the data set, the number of observations on an individual varies from 1 to 17, and time of observation varies from 12 to 176. This is the data set. You can see that. Time varies and number varies. 1 to. Here the data set is continuing. Just a few observations. Then what? Since the original data consists of excess number of zeros, to avoid zeros as number of recurrences at each observation time, we omitted certain observation times, and the cumulative number of recurrences up to selected observation time is calculated. With these modifications, we obtain a panel count computing this data. Then the isotonic regression estimates of the mean functions are calculated, and they are presented in figure 2. These are the two IRA estimator. The solid line represents the mean function of the number of recurrences due to this basal cell carcinoma, and dotted line represents the mean function due to squamous cell carcinoma. It is clearly that the first one is dominated by second one. So the proposal test is employed to compare the two risk of failure, and we have used 3 different weight functions, and we have calculated a statistic and p-value. All the cases it is clear that mean function due to basal carcinoma and squamous cell carcinoma are entirely different. One is dominated by others clearly. The mean recurrence time of basal cell carcinoma is greater than average recurrence time due to the other one. So in this study, we have developed some non-parametric inference procedure for the analysis of panel count data with the committing risk. We developed an isotonic regression-based estimator, and we also consider a testing problem to compare the effect of different causes on recurrence times. The finite sample properties of the estimators and test statistics are examined through extensive simulation study. The importance of the model or practical applicability of the model was illustrated using a real data on cancer research. The future work, the non-parametric MLE and non-parametric MLE of the cause-specific mean function of a panel count data committing risk are not developed yet. The cause-specific rate function is in the same situation, is also studied, but recently we have studied this problem. The paper is just appeared in Journal of Indian Statistical Association. Then further in modeling committing risk data, the nature of dependence between time to failure and cause of failure is an important problem. Even though the problem is studied well in right-hand-side data, it is unexplored for the panel count data. The regression for panel count committing risk data is not a study, but we have completed this study and we have submitted the paper for publication, the last problem. This is the proof for those asymptotic properties. Thank you.
Thank you very much. Thank you very much, sir. Sir, thank you very much for your excellent presentation on the non-parametric inference procedure for panel count, analysis of panel count data with the competing risk. You have presented the different development of estimator for isotonic regression estimator and developed the test statistics, and have done some simulation studies and applied the procedure in this real-time data also. So the topic is open for discussion. So, sir, after discussion, after the two presentation, we will go for discussion or now itself?
No, any discussion, you can ask question right now because I have a meeting.
Okay, sir. Okay, sir. Then some quick questions, some 1 or 2 quick questions, please.
Yeah.
If it is.
Yeah. This paper is already published in Journal of Applied Statistics, last issue in 2020, and one can refer the one. The second one related to this on rate functions is also published in Journal of Indian Statistical Association.
Yes, sir. So then, shall we move to the next?
Yeah.
So in this session, we have time up to 2:55. We have one more speaker, Professor Dr. S. Devi. He will be speaking about some new classes of copula and their applications. He is the professor of Statistics, Department of Studies in Statistics, University of Mysore, and he got postdoctoral fellow from Rotterdam, the Netherlands, and he has more than 20 years of teaching experience, and since March 2010 he is the professor of statistics at the university, and he has got many academic honor and fellowships in his credit, and a member in many professional bodies, and more than 43 publications in the peer-reviewed journals, and more than 15 books and book chapters in his credit. And he has guided more than 3 MPhil students and 8 PhD students. And on behalf of the organizers, let me welcome Dr. Devi sir for this lecture.
Thank you, Dr. Srikumar. Am I audible?
Yes, sir. Yes, sir.
Thank you. Thank you for the kind introduction, and it's my pleasure to thank Dr. Satish Kumar and the organizers for this opportunity to share some work which I did some time ago with Dr. Deepesh Bhati. So I will share my screen. So I thank Dr. Satish Kumar and the other organizers for giving me this opportunity to share our work here. So is the screen visible?
Yes, sir. This time.
Yeah, I'm going full screen, so you can stop if you have any problem. So, I mean, I congratulate Dr. Satish Kumar on organizing this, and I wish all the audience a very happy Statistics Day. And I also thank them for coming at this time of the day, soon after lunch, or maybe having lunch now. And this is a joint work with Dr. Deepesh Bhati. I'm sure Dr. Deepesh Bhati is around. So this was part of Dr. Deepesh Bhati's PhD thesis. And here we introduce a method to generate 2 new classes of copulas. And we study tail dependence and extremal properties of the new families. And we also do some data analysis. I won't be discussing the data analysis part in detail. The graphs and all I will not be showing. But I'm sure if you want to access, you have Dr. Deepesh Bhati's thesis online somewhere in Vidyanidhi project. And those interested can access that. And unfortunately, we are still publishing this. We have not published this. Okay, so families of copulas are objects which are frequently used in modeling multivariate dependence. So you can think of this copula as a generalization of the probability integral transform for the univariate case. So if you have a random variable x with distribution function capital F, and then if you define y equal to capital F of x, then we know if x is continuous, then y has uniform 0-1 distribution. Then you can ask what is the generalization of this in the bivariate case or in the multivariate case, and you will see that copulas are the natural analogs of this property in the univariate case. So before going to define copulas, I'll just give a few statements about where these are used and so on. So they are applied in many disciplines such as actuarial science, finance, hydrology, etc. And Nelson defines copulas as link functions that join or couple multivariate distribution functions to their one-dimensional marginal distribution functions. So it's basically, so if you have a multivariate distribution function, then you know the one-dimensional marginal distribution functions. So how do we relate the multivariate distribution functions with its one-dimensional marginal distribution functions? This was done by Nelson and using copulas. Hence, they possess properties which are analogous to those of a joint distribution function in the multivariate case. Since copulas enable to separate the marginal behavior and dependent structure, they are widely used to model dependence whenever it is possible to define copulas with explicit inverse functions and so on. A bivariate copula, so here I'll be concentrating on the bivariate copula, is a function C which is defined on the Cartesian product of the closed interval 0,1 cross 0,1 or 0,1 square and takes values in the closed interval 0,1, and it satisfies three properties. The first one being for every u and v in the closed interval 0,1, C of u0, I'm looking at bivariate copula, therefore C of u0 equal to C of 0v equal to 0. Excuse me. And for every uv in 0,1, closed interval 0,1, C of u1 equal to u and C of 1v equal to v. And these are the excuse me again. These are the marginals. And the third one is the rectangular property of a bivariate distribution function. For every u1 less than or equal to u2 and v1 less than or equal to v2, c of u2 v2 minus c. So this is essentially the measure in the rectangle. It should be greater or equal to 0. Conditions 1 and 2 imply that the marginal distributions are uniform 0, 1. And condition 3 is known as the rectangular inequality. And if f is a continuous bivariate distribution functions with univariate marginal distribution functions f1 and f2, and quantile functions f1 inverse and f2 inverse, then you define y1 as f1 inverse of u1, and has, of course, then this we know that this has df f1, and y2, which is f2 inverse of u2, has df f2. The same as saying that f1 of u1 has uniform 0, 1 distribution, and f2 of y2 has uniform 0, 1 distribution. u1 and u2 are uniform 0, 1 random variables. Hence, if you make the transformation small y1 is equal to f1 inverse of u1, small u1, and small y2 is equal to f1 inverse of, I think it should be f2 inverse. There is a typo here. f2 inverse of u2, then you can see that f of y1, y2 is f inverse of u1, because y1 is this, and y2 is f2 inverse of u2. But we know that this is nothing but probability, u1 less than or equal to u1 and u2 less than or equal to u2, typo again, which you call it as C of u1, u2, is the unique copula associated with the df. So copulas are the distribution function f. So if you have a bivariate continuous distribution function f, then you have a copula which is unique, and every copula you can get a bivariate distribution function provided you know the univariate marginals. So in a sense, copula captures the dependence between the components of the distribution of the components of a random vector in higher dimensions. Modeling dependent structure between two or more dependent variables has attracted researchers working in many fields such as risk management. One can refer to Embrus et al. In econometrics, you can refer to Pattern, and hydrology, Genest and Favre, etc. And copulas are frequently used because they involve known marginal distributions and the dependent structure. So if you know the dependent structure and know the univariate marginal distribution functions, then you can go for copula modeling. Various methods such as inversion method, geometric weighting method, and algebraic method have been used to construct new classes of copulas. Of course, question comes as to why do we need new classes? New classes are needed to model different data sets and see whether you get better fit with these new classes when you fit these copulas to actual data sets. So that is one reason why people or researchers are in search of new methods to construct new classes. And so motivated by the method of Marshall and Olkin, 1997, I'll show the references at the end. Zhang et al. 2016 proposed a new class of copulas which generalizes an existing copula. They generated the new class called geometric copulas by considering copula of the bivariate random vector xnn, ynn with n following geometric distribution, where xnn is the order statistic from a random sample of size capital N from the first marginal, and ynn is the nth order statistic from a random sample with random number of observations from the second marginal. And this I have already said. xnn is the maximum order statistics from a random sample, and so on. Ashorwa applied the same procedure by considering, of course, if they did for n geometric, then obviously you ask what happens to negative binomial and other such discrete random variables. Ashorwa applied the same procedure by considering n to be shifted geometric, and shifted Poisson and truncated Poisson. Because of introduction of an additional parameter theta through the random variable capital N, the new copula has more flexibility in modeling real-world data sets. That's what this is what has been observed by these researchers. Ruzigar and Nadaraja in 2017 generalized these ideas by assuming power series distribution for N. And introduction to the new method. The new method proposed to generate new classes of of copulas is based on transformation. So suppose that you have F as an absolutely continuous distribution function with support in 0, 1. We need support in 0, 1 as you will see because of our definition. And G is any other distribution function. Then you can define h of x as f of g of x. And then you see that this is a distribution function. And taking f to be the beta distribution, beta AB distribution, Jones 2004 discusses the properties of such distribution functions H, which are one can call as composite distribution functions, a distribution function of another distribution function. We employ this idea and consider two DFs having support 0, 1 to generate the new classes of copulas. So genesis of the new families of copulas. And Genest and Rivest discussed the method of transformation to generate a new class of copulas as follows. This is the theorem by Genest and Rivest. Let psi be a function from the closed interval 0, 1 to the closed interval 0, 1 be continuous and strictly increasing with psi of 0, 0 and psi of 1, 1. And let psi inverse denote the inverse of psi. Then if you have an arbitrary copula C, define C psi by this formula 1. What is C psi? C psi of U1, U2 is equal to psi inverse of C of psi U1 comma psi U2. So psi is a 0, 1 valued function defined on 0, 1 again. So you consider C of the copula evaluated at psi of U1 comma psi of U2 and take psi inverse of that, and where C is an arbitrary copula, and this you get new copulas C psi for every such psi which you have, and with the condition that psi 0 should be 0 and psi 1 should be 1, and psi is continuous and strictly increasing, therefore there is a unique inverse. Then C psi is a copula if and only if psi is concave. Along with these conditions, the necessary and sufficient condition for C psi to be a copula is that psi should be concave, and this is necessary and sufficient. We discuss an alternative approach to generate classes of copulas whose functional form is the same as that in the earlier. So let G be the distribution function of x1, x2 with marginal distribution functions G1 and G2, and kappa be the copula between x1 and x2. Then by class theorem, what is class theorem? G is the distribution function of the random vector x1, x2, and the marginals we have denoted by G1 and G2, and kappa is the copula between x1 and 2. Then by class theorem, G, this should be, this is just to denote that G is the distribution function of the pair x1, x2, is kappa evaluated at G1 of x1 and G2 of x2. Let F be an absolutely continuous univariate DF with support 0, 1, that's what we said, PDF F, and G be some absolutely continuous bivariate DF. We define the bivariate DF. So here we are discussing, we are defining the distribution function. What is the bivariate DF? So h of x1, x2 is defined as integral 0 to g of x1, x2, ft dt, and this is nothing but f of g of x1, x2. This is the idea which I showed you earlier of composing two distribution functions, but this time it's a bivariate distribution. So f of g of x1, x2 in R2. Then we get h of x1, x2 is equal to f of, but we saw just in a few, I think this slide in 2, the G of x1, x2 is kappa of G1, x1, G1, G2, x2. Therefore, we get h of x1, x2 as f of, in place of G of x1, x2, we have kappa of G1 of x1, G2 of x2. Then you can find the marginal of h. The marginality of h1 is then given by h1 of x1 is this with tending this the variable in G2 to infinity, and then you get this as 1, and so this is f of G1 of x1. Note that f is a univariate distribution function, so therefore h1 of x1 is f of G1 of x1, and similarly h2 of x2 is f of G2 of x2. Also, if you look at hi inverse of ui, you want to find the inverse function of this. So hi inverse of xi or ui is gi inverse of f inverse of ui. I is 1. Replacing u1, u2 by h inverse of u1 and h2 in h1 inverse of u1 and h2 inverse of u2, we define the new copula as follows. So definition, we call this as the fk copula. Recall, f is any absolutely continuous distribution with support in 0, 1. And kappa is the copula coming out from the bivariate distribution function g. So f kappa copula is defined as this. C of u1, u2 is f of kappa of f inverse of u1, f inverse of u2. And then you can have several copulas like this. So first this is the Gumbel copula. The Gumbel copula with the dependence parameter gamma greater or equal to 1 is given by this. So we denote it as, so we now what we do is for the kappa we choose different copulas, and then you get different families of copulas. And the kappa copula for Gumbel from Gumbel distribution is this. It is e to the minus the inverse minus log u1 power gamma into e to the minus log u2 power gamma. Sorry, because this is whole power 1 by gamma is inside, so I cannot separate it out. So e to the minus log u1 power gamma plus minus log u2 power gamma whole power 1 by gamma. And so these are known, these are from the literature. And the Frank copula with the dependence parameter gamma not equal to 0 is of the form minus 1 by gamma log of 1 plus e to the minus gamma u1 minus 1 times e to the minus gamma u2 minus 1 divided by e to the minus gamma minus 1. And the Joe copula with dependence parameter gamma is given by this 1 minus the entire thing power 1 by gamma. What is it? 1 minus u1 power gamma plus 1 minus u2 power gamma minus the product of these two. 1 minus u1 power gamma into 1 minus. So the new family is, let f be a univariate df. So we actually give the f, what the f is. So you take this density alpha power t log alpha by alpha minus 1, where alpha is bigger than 1 and t lies between 0 and 1. And for some absolutely continuous bivariate dfg, define h of x1 x2 is alpha power g of x1 x2 minus 1 divided by alpha minus 1, and the new copula c1 is defined like this. c1 u1 u2 is 1 by alpha minus 1 alpha power kappa of log to the base alpha 1 plus alpha minus 1 u1 and log 1 plus alpha minus 1 u2 minus 1. And the density, so you differentiate this and then twice, and then you get the density. The density looks like this, where S1, S2 are these quantities. And then the FK2 copula is, this time we choose F to be the univariate df with PDF this, and we can generate new classes of copulas. And then just like earlier, for some absolutely continuous bivariate DFG, it can be anything. You define h of x1, x2 as this. Then the new copula C2 of u1, u2 is this. 10. And then one can find the copula density. And so here one should note that as alpha tends to 1, so here, for example, what is alpha here? Alpha is bigger than 1. So as alpha tends to 1, the C1 tends to the kappa, and as lambda tends to 0, C2 tends to kappa. And kappa can be any copula, as we have shown, the Gumbel, Frank, or Joe, or anything, any copula. Extremal property, we have studied the extremal property. Let the bivariate distribution function G belong to the max domain of attraction of a bivariate extreme value D of K. So that for some norming constants an and bn, cn, dn, an, cn positive and bn, dn real, this happens. That means g power n anx plus bn, cny plus dn converges to k of xy. Or equivalently, you can take logarithm on both sides and justify that. This is equivalent to this limit n going to infinity, n times 1 minus g of this quantity, anx plus bn, cny plus dn is equal to minus log kxy. Xy says that kxy should be positive. Then the bivariate distribution function h, h is defined using g and kappa, belongs to the max domain of attraction of k with the same norming constants, with h defined where h is defined with f equal to f1 or f2. So what are the f1, f2? F1, f2, just to recall, I'll just go back. Yeah, this is f2 and this is f1. Yeah, this is f1. So these are the new families because these are not in the literature. And we have also looked at some properties, and the extremal property is satisfied. H also belongs to this max domain of attraction of the same k for both f1 and f2. Tail dependence coefficient is frequently used as a measure for tail correlation separately for upper and lower tail. For a bivariate copula Q, the upper tail dependence coefficient is defined like this. So the upper tail dependence coefficient TD of U is 1 minus 2 beta plus Q beta beta by 1 minus beta as beta goes to 1, limit as beta goes to 1. So the lower tail dependence coefficient is Q beta beta by beta. So the upper is this, Q beta by beta is the lower one, whenever the limits exist. Then we have a result. The upper and lower tail dependence coefficients of C1, C2 are same as those of kappa. Then some data analysis. How much time I have?
5 minutes more, sir.
Oh, thank you. So we have done some data analysis, so I'll quickly go through this. So choosing kappa as Gumbel, Frank, and Joe copulas, we generated random numbers using copulas C1, C2, which we have defined. To generate sample from the kappa copula, we use the following procedure described in Nelson, based on the conditional distribution of a random vector U1, U2 having uniform 0, 1 marginals. So kappa U1 of U2 is the conditional distribution, and these generated pairs U1, U2 from copula K are used in the algorithms below. Generate X1, X2 from kappa copula as shown, step 1. For fixed alpha, compute G I power C1 of X1, which is this, alpha power Xi minus 1 by alpha minus 1. Set U1 as equal to this one and U2 as this. Yes, okay. So I'm looking at only C1 copula, and then repeat steps 1 to 3 n times to get a sample from C1 copula. And similarly for C2, I'll skip. Step 2 is the only change, otherwise it's the same. And we generated samples of size 2000 from copulas C1 and C2. No particular reason for 2000, just computational purpose, using the algorithms above, with kappa copula as Gumbel, Frank, and Joe, and got the scatter and contour plots for different values of the parameters. I am unable to show those things here. I'm just stating from what we did. We discussed the estimation of the parameters alpha, lambda in C1, C2, and gamma in kappa by using maximum likelihood method. For estimation of parameters, Joe discussed a method known as inference function for margins, IFM, which is based on the assumption that the marginals are known. This method has two steps in which the parameters of the marginal diffs are estimated first, and then the copula parameters are obtained by maximizing the likelihood function of the copula with the marginal parameters replaced by estimators obtained in the previous step. Kim proved that this method is not robust against misspecification of the marginals. Kim showed that the pseudo maximum likelihood method introduced by Oakes performs better than the IFM. This consists of two steps. The first step is to estimate the distribution functions of marginals non-parametrically. That means use the empirical DF, and then the copula parameters are estimated by maximizing the pseudo log likelihood function. Yeah, more specifically, Kim used sample empirical DFs specified as these for the marginals and maximize the pseudo log likelihood function, which is this, where U1i is this coming from this and U2i is this. Okay, for C1, the log likelihood function we have found out. I mean, it's a big expression. There's nothing much to see here. And similarly, for C2, the pseudo log likelihood function is this. And we maximize to get the estimators. Then we have discussed the applicability of the new copulas using two real data sets from insurance. In both the applications, we consider Gumbel, Frank, Joe families for kappa and employ C1, C2. Estimate parameters for these families using the procedure discussed earlier, and then comparisons among these 6 families are made using AIC, and the lowest AIC value is preferred. And so I'll just hint at what we got. Yeah, the workers' compensation insurance data set is available. It comprises of losses due to permanent and partial disability claims, and the original data set had 847. Out of which 69 were censored. So we considered 778 uncensored observations, and the variables of interest are the same as those considered in Zhang, x equal to log payroll and y equal to log PP. I don't remember what PP is now. Zhang considered 5 families of copulas: geometric Gumbel, geometric Gaussian, geometric T Gaussian, and T copulas to model this data set. We estimate the parameters by maximizing the log pseudo likelihood function for these total 9 models in all. And what we found was that for C1 copula with kappa copula as Frank, AIC is the least, and that is the best for this when compared to the other 8 models. And the new copulas also have lesser AIC values than the 3 kappa copulas. Then we also discussed the Danish fire claims data set. So maybe I think I'll skip this. Okay, the conclusions are 2 new classes were proposed, and these generalize some of the existing models. Extremal properties have been studied, and applicability of the new models are illustrated for 2 real data sets. These are the references: Genest and Favre, 2007, and Genest and Rivest, 2001 in SPL. And I think something is missing there. Hashorva in Scandinavian Actuarial Journal, 2017. And Joe, of course, that's a book. I think there is another book, a recent one. And Nelson, where he introduces the copulas. And Zhang is what we compared our models with the models in Zhang 2016. And thanks to Professor Satish Kumar, convener, and all of you for your patient.
Thank you, sir. Thank you so much for the excellent presentation.
Thank you.
We are left with some two minutes. So any quick queries, if anybody has, can have. So let me congratulate both the speakers in this session.
Thank you
for your excellent presentation.
Thank you.
And I also thank the organizers for giving me an opportunity to chair this session. Thank you, Satish sir. And thank you all those who are attending this session. Thank you.
Thank you.
Thank you. Thank you all speakers of the session, as well as both the speakers, Professor Sangaran and Professor Ravi, as well as Dr. Srikumar for chairing this session, and Dr. Baiju to supporting as co-chair of the session.
I also thank Dr. Baiju as co-chair.
Okay.
Thank you.
Thank you.
I also thank Dr. Baiju for co-chairing this session.
Thank you. Thank you all. Thank you.
And also congratulate the chair for concluding the session in time. Now let us move to the next session. Next session, in fact, also has two speakers, and this chair, the chair of this session is Professor K.R. Muralidharan Nair, and Dr. Krishnamar.
Yes, sir. I'm here.
Yeah, Dr. Krishnamar is also here to support Muralidharan sir. Professor Muralidharan sir is well known in the in our area. Is an expert, especially in distribution theory, reliability theory, and several areas. And in fact, I think Krishnamar may include something more. Please, without wasting time, I hand over the mic to Krishnamar. Please introduce Muralidharan sir and invite him to chair the session. Dr. Krishnamar.
Yes. Yes, sir.
Yeah.
Yes. I once again, it's a great privilege to introduce Professor K. Muralidharan Nair sir. We have a great or good statistician to chair the session. He's a professor in the Department of Statistics, Cochin University of Science and Technology. His area of research are characterization of probability distributions, reliability modeling, information theory. He has around 37 years of teaching and 23 years of research experience. He was also head as well as professor of the department. He has supervised around 4 students. He was a member of various academic activities and professional bodies. As far as my knowledge, he has around 20 publications and
several publications.
But in his, in his web page, I was only able to see only 20 publications. I don't know.
It is
only around up to 2008 only. I think he has put. Okay. Anyway, and he has participated and organized various conferences, workshops around, and he has visited various places. And the session will hand over the session to Professor Muralidharan Nair sir. Sir, over to you, sir.
So, good afternoon to all. Thank you, Satish and Krishna Kumar, for the nice words spoken about me.
Just one moment. Can you please close the presentation?
Professor Ravi, please close the stop the presentation. Professor Ravi.
Yeah.
I'll do that. Sure.
It's not there, no? Okay.
It's still there.
It's okay?
Second.
No.
One second.
No, sir. No, it is here all.
I don't know, it is not going.
Just stop. There's a click on the stop presentation.
Stop.
Yeah, but.
Sir,
oh yes, please.
I think Professor Senegal can
now it is okay.
I have done. Yeah, sorry about that. Thank you.
It's okay now.
Yeah.
Okay. So we are on the eve of the second plenary sessions. There are two speakers in this session, namely Professor David Hanegal and Professor K. Muralidharan. The first speaker is Professor David Hanegal, and he will be speaking on shared inverse Gaussian Freighty models based on additive hazard. Professor Hanegal needs no introduction to this distinguished audience. He was with the SP Pune University for more than 30 years, and as I understand, after retirement, he shifted to Vishwakarma University, Pune. He has over 40 years of teaching experience in statistics and has published more than 120 papers with a large number of citations, in addition to 2 books. His major areas of interest includes statistical inference, distribution theory, reliability analysis, survival analysis, and Freighty models. My acquaintance with Professor Hanegal started about 25 years ago when he visited the Cochin University in connection with a conference. Let us all jointly welcome Professor Hanegal for the plenary talk. The time allotted is 40 minutes, and we shall use the last 5 minutes for interaction with the audience. Now, over to Professor Hanegal, please.
Okay, thank you for the nice introduction, Professor Muralidharan. I also thank Satish Kumar and his team and the organizing committee for giving an opportunity to share my ideas during this conference. Okay. Can you, am I audible?
Yeah, audible, boss.
Audible. Can you see the screen?
Yeah, now you can see the screen, some of your folder, the computer folders.
Folder you can see only.
Yeah, not files are there.
Presentation?
Not presentation. You can click on that presentation. You are on the position, you have to double click probably. P3 seminar, is it your name of the presentation?
Okay, correlated positive. I changed the topic. Okay, somehow the correlated positive stable probability model based on reverse hazard rate. Is it visible?
No, sir, you have not opened the presentation.
I'm not open to the presentation.
Or otherwise, you have to move to that slides.
Okay, I'll just see it again. Okay, I'll just close it again.
We can see some in your PC. You can see the research papers. P3, the folder containing those
P3
papers.
You can see P3.
Yeah.
Professor Hanegal, I think you have shared your entire screen, so you just need to open it and start presenting.
Okay, I'll just stop the sharing.
Now it's on the way. Yeah,
I'll stop the sharing. Then again do again. Okay, window, research papers. Okay, research papers. I'll just stop it. Okay, let's do it again. Okay, I can do it now. Windows. Okay, can you able to see it now?
You didn't share it yet. You have to share it. Yeah, now it's okay. Now it's coming.
Now it's coming, no?
Yeah, now it's coming.
That's okay. Full screen. Can I do this full screen? Is it full screen now?
Yeah, it's perfect.
Yeah.
All right. Okay. Thank you very much. Okay, I'll start this presentation. Okay, the title is slightly changed as it is shown in the brochure. It's a correlated. The earlier title was somewhat the old paper. It was now this paper is completely new. That's why I want to present this one. This is based on the correlated positive stable probability model based on reverse hazard rate. I have some correlated positive variety models earlier also. There is a correlated gamma and correlated inverse Gaussian models based on reverse hazard and usual hazard rates. Okay, this is a new variety model, correlated positive stable variety model. Now, before going to variety models, I want to give some introduction on the survival analysis, time to event data, and there are censored samples, and there are various types of censoring involved, type 1, type 2, and censored samples. I'm basically doing the random censoring, right censored. In this, it's actually left censored. It's a reverse hazard. In the case of reverse hazard, we have to use the left censoring observations. Now I start with the review of the basics. You know the Cox proportional hazard rate, that is function is ht given x. Ht given s is a hazard rate. Given x is a covariate. This is equal to h naught t, that is a baseline hazard, and exponential x prime beta. This includes the covariates and regression coefficients. Okay, explanatory variables is a x and beta is a regression coefficients. Okay. Now in this, there is a, if the data is homogeneous, then you can use this Cox model. If there is a heterogeneity involved in the data, maybe in the patients or due to genetic factor or some hospital centers and other things, then there will be some heterogeneity involved in the data. In order to solve this heterogeneity problem, we have to modify this hazard function into taking heterogeneity factor. That is called variety. That is the introduction of variety. Now, why you need to use variety? See, if there are so many covariates involved in this model, in the data, in that case, it is very difficult to take all the covariates. You have to take some important covariates, and sometimes you will get puzzled which covariates you have to consider. In that case, sometimes you miss some important covariates, okay, which are really affecting the lifetime. Sometimes the covariates may not be known. Okay, that is not possible to observe or not possible to measure. For example, genetic factor or environmental factors. In that case, we miss the important covariates which is not known to us. In that case, we have to use the heterogeneity, that is variety. Okay, now I introduce some random quantity in the Cox model. See, if you take only this one, ht, that is h naught t e raised to x prime 2, that will be Cox model. I am adding this term. This is unknown to us. This is a unobserved covariate. Beta is corresponding to that regression parameter corresponding to unobserved covariate. Okay. Now this factor, e raised to this factor, that I can put it as a z, that is here. Z equal to this one. Now we can obtain the conditional survival function just to integrate over this z. Now u is from minus infinity to plus infinity, and z is 0 to infinity. Okay, this is a positive random variable. Now I have to integrate this with respect to z. Before that, I just take the conditional survival function, then you integrate about. Now, if you take the relation between survival function and cumulative hazard, H0T is a cumulative hazard function. Okay, just take the integration of this. You will get the integration over this over the T. You will get the cumulative hazard and multiply by Z. Then this is the integrated hazard. Then take integrate over Z. You will get this term in this case. That is the Laplace transform of Z, and this is the argument. Okay? That is the quantity. Now, if you take two component, instead of H0T, it will be H0T plus H0T2. Okay, that is the term. Okay, this is the bivariate survival function. Now, if I consider reverse hazard, here earlier this is a usual hazard H0, and now I am taking reverse hazard. Okay. There is a paper by Shaked and Shantikumar, Block. They have defined reverse hazard rate as this way. That is an instantaneous failure given the probability T is less than or equal to T. Okay, that is Ft divided by Ft. Ft is a distribution function. If you take divided by survival function, that will be usual hazard. Then it will be, in this case, it is a reverse hazard. Okay, T. This is taking the value 0 to infinity. Okay, that is the term. I am just denoting this as MT. Okay. Now this is used in the left censored. When the data is left censored or right truncated, in that case you can use the reverse hazard rate. That gives the better modeling when the data is left censored and right truncated. There are different authors have given, Lisa, Anderson, Lawless, Shankaran has also done a lot of work on the reverse hazard rate. Okay. Now consider the covariates along with this. I'm just taking the covariates, different covariates. This is beta naught and beta s. Okay. Beta naught is the common covariate for both x1 and x2, that is T1, T2. I'm considering two lifetimes, T1, T2. It's beta naught is common and beta 1 corresponding to only the lifetime T1 and beta 2 for the lifetime T2. That is the way. Now, the conditional reverse hazard is given by this one. I'm just denoting this covariates and the regression in terms of eta naught. Okay, for simplification. Now I can write the distribution function. There is a relation between distribution function and reverse hazard rate. That is this. This is the form. E raised to minus cumulative reverse hazard rate. Okay, E raised to this one. That gives the relation between distribution function and cumulative reverse hazard. And if you could take integrating over Z. Okay. Okay, this actually Fraternity term which modifies hazard function of an individual or related individual. Clayton was the first person to introduce this. Then later on, Weipel and his author in 1979. Okay. Okay, this effect or Fraternity is not directly estimated from the data, but instead it is assumed to have unit mean and finite variance. There is a problem of non-identifiability when you take Fraternity. In that case, in order to solve this, we have to assume unit mean for the Fraternity random variable and finite variance. That is a condition. Okay. Now, what is going to happen if we ignore the Fraternity? Okay. When Fraternity is ignored, the estimates of regression coefficients will underestimate or overestimate. And the model selection criteria, AIC, BIC, DIC, that will be more compared to the model with Fraternity. This will increase, but we need AIC-DIC to be minimum. Okay, this is based on the model without Fraternity. Will go wrong. That will be inappropriate. Ignoring Fraternity effect with finite mean may result negative bias in the estimated time dependence. That means the heterogeneity will go into the error term, and this will of course lead to increase in the variability of the response. That is the effect of ignoring Fraternity. We have different Fraternity models: inverse gamma Fraternity, inverse Gaussian, positive stable, power variance, compound Poisson, negative binomial, compound negative binomial, piecewise gamma, correlated Fraternity, additive Fraternity. And we have some papers on these different Fraternity models. Today I'll be mainly concentrating on correlated Fraternity. Now, before that, I'll just explain what is positive stable Fraternity. This was given by Howard in 1986 in his paper, and there are different authors also discussed positive stable Fraternity. The only thing is, it's a stable distribution. It don't have probability density function on the real line. Okay, that is a problem. But one can obtain Laplace transform of positive Fraternity. Only we need to know the Laplace transform in order to solve the Fraternity model. Okay, this is the density of positive stable Fraternity model, and the Laplace transform is this one. And in order to solve the non-identity problem, we restrict the parameter this one, alpha equal to delta equal to theta. That means instead of two parameters, we'll have only one parameter that I will denote it as theta. Okay. Now this is a positive stable Fraternity model with restriction, only single parameter, that is a density, and this is a Laplace transform. Okay. When theta equal to 1, then it will be degenerate. It will be just same to equal to the without Fraternity when theta equal to 1. Okay, that is a thing. When theta equal to 1, this will be equivalent to the bivariate survival function in this case. That is a thing. Okay. Now just take the Weibull distribution. This is a stable Weibull. When you apply the positive stable Fraternity model, then it will be like this. Okay? And if C1 equal to T2, then minimum of T1, T2 is again a Weibull distribution in that case. Okay? Then the form of the distribution is again a Weibull. Even though the Fraternity is introduced with Fraternity and without Fraternity, the distribution is unaltered. That is Weibull distribution in both cases when C1 equal to C2 in that case. That is the thing. That is called stable Weibull model. Now, what is the cross ratio function? The cross ratio function given by Clayton 1978 is this formula, and that is equal to this one. This is a decreasing function of T1. This is a decreasing function of T1, T2. Okay. Now one can obtain the copula also based on the bivariate. The formula for the definition is this one. F1 and F2 are the distribution function. This is a copula C and survival copula. That is given by this formula. Okay. You can write in terms of survival copula and also distribution and survival function. Okay, this is a form of survival copula. In the case of positive stable Fraternity model, the form of this one is this one. Now let's go to the correlated Fraternity. So far we have seen only shared variety. The correlated is there are two lifetimes, T1, T2 corresponding to, say, for example, two paired organs or twins or maybe any eyes or kidneys or any type of paired organ one can take. Now what I'm doing here is I'm taking a variety Z1 for lifetime T1 and variety Z2 for T2. And these Z1, Z2 are correlated. That's why it is called correlated variety. That is it. The form is this one. Here Z1, Z2 are correlated. Therefore, this distribution function is correlated. Okay, T1, T2 are correlated because of this reason. Okay, that is the reason. Okay, this is a bivariate variety. Now consider the correlated positive stable. Correlated positive stable, there is a formula. One can obtain the bivariate Laplace from the univariate Laplace. Okay, this is a univariate raised to 1 minus rho. Rho is between 0 and 1. Okay, here. Maybe minus 1 to plus 1, but in this case it will be 0 and 1 in this case. And this takes into account both T1, T2. This is take into account T1, this is T2. Then the entire factor is bivariate Laplace. The S1 and S2 are the arguments. The correlation between Z1 and Z2 is rho. That is greater than 0. If rho equal to 1, then need to reduce this to shared variety model. This term will be 1 and this term is just shared variety model. Rho equal to 1, this is the only term remaining and that is equivalent to shared variety model. That is the term. Okay. One can extend it to multivariate variety models, S1, S2, Xk, K terms, and this is the term. Okay. Here also rho equal to 1 leads to shared variety. Rho equal to 0 means Z1, Z2, Zk are mutually independent. That is the thing. Okay. Only thing is this will be 1 and when rho equal to 0, this or multiplication of all this. That means Z1, Z2 are independent. Okay. Now, if you take L SI theta, single Laplace transform, that is equal to this one. Just substitute in this formula in the bivariate Laplace. Using this, we get this term. Okay. I'm just using the Laplace transform of positive stable. Okay. Now, this is a bivariate. Okay. Now, after substituting S1, S2 here, you get this one. S1 is cumulative reverse hazard, that is here. S2 is here. And this is here. Okay. I'm just substituting. This is a bivariate distribution. This is in terms of all Laplace transform. Once you have Laplace transform, then you can obtain bivariate distributions. Okay. All right. Now, this is without variety. In the absence of variety, this can be written this way. That means for the variety variable is dz, right? Now, I am taking some, this completely parametric approach. One can also have non-parametric distributions as a baseline. Then you get semi-parametric distributions. This is, the first one is modified inverse Weibull. Okay, that is given by this formula, distribution function. MT is a reverse hazard rate and capital MT is a cumulative reverse hazard rate. This reduces to inverse Weibull when gamma equal to 0. Okay, there are some sub-models involved in this. So one of the baseline. The second one is generalized law logistic. Okay. That is here. This was given by Bennett, Cox, Mitchell, and this. Also different authors. What I'm doing is I'm just making a generalization of the log logistic. There are two types. This is for one. Okay. I can write this as type 1, distribution function raised to alpha. one can have, or survival function raised to alpha. Then you can have MT and small mt. Reverse hazard rate, cumulative reverse hazard rate. The second one is this one. Okay, that is here. Okay, in all, there are three baselines. First one is a modified, generalized modified even, generalized log logic type 1 and type 2. Now, I can have total 3 models based on the Fraternity, correlated Fraternity, and 3 models without Fraternity. That means in all 6 models. Okay. This is 2829. Belongs to the law logist, okay. Modified inverse viable with and without, with using the correlated positive stable. 3031 is for the type 1, baseline is type 1, logistic, generalized logistics type 1, using the correlated positive priority model and without priority model, 3031. And similarly for the third baseline model, that is generalized log logistic type 2, with priority, without priority, 32 and 33. In all, there are 6 models. Okay, already explained about these models. Now we can analyze. I'm using the Bayesian estimation. One can also have classical estimation based on the MLEs. There are so many parameters involved in sensoring is involved, and sometimes it is very difficult to get iterating processors by Newton-Raphson procedure. Okay, the better way is to go for Bayesian estimation. You can get the computation will be too much, but one can obtain the estimates, the closed form. Okay, the likelihood will be written in this form, divided into 4 reasons, and with the different reasons. Both are observed, both failures. One is censored, one is observed. Here the second one is observed, first one is censored. Both are uncensored. The corresponding F1, F2, F3. When both lifetimes fail, then differentiate the T1, T2. Only T1 here, T2, and this is just like this one. Simulation study. I did simulation study for the Friday model in order to check the performance of the estimates. Okay. All right. I'll just give the 3 tables expected in this for the simulation model 1. See, the parameters I have taken is this one. These are the true values and estimates. They are close to the true values. The standard errors of the estimate, lower credible limit, upper credible limit, okay. GVK values, E values, Geller values. E values are very close to 0.5 because the GVK values are very close to 0. That's why this is very close to 0.5. Gelman-Rubin values are close to 1 in this case. This is for the model 1 simulation, and for the model 1, okay, for the model 3 and model 5. This is for the baseline log logistic distribution type 1, generalized logistic type 1. Okay. The third one is for the generalized logistics type 2, model 5. That means model 1, 3 and 5. These are the Fraternity models, correlated positive Fraternity models. Other 3 models are not taken simulation because they are not involved the correlated positive Fraternity, that is without Fraternity. Okay. One can do for that also. Okay. Now analysis, data analysis. Australian twin data I am using. Okay. There are different types of twin data models. 6 models are there in all. All these 6 models are there. And I'm just applying these models to Australian twin data. Okay, there are 6 zygotes. I'm taking only one zygote. That is category 4. Data consists of male gender only and consists of 350 pairs of twins. 9 and 11 are censored in the twin 1 and twin 2, left censoring. Okay, and the observations, 350 observations. Okay. T1, T2, and one covariate is there for T1, T2, the presence and absence. Okay, that is it. Okay, I'm just doing the goodness of fit test, case statistic, and p-values. The p-values are given for model 1, 3, and 5. There are somewhat high values. Then we assume that the model fits the data. Okay. The data fits the model. All the 3 models. Now take the model 1. That is a correlated positive variety model or the modified inverse people. Here the estimates of these parameters are given. What we see here is beta 1 is significant, not significant. They are not significant here. Beta naught is significant, lower and upper trend. Both are positive. Beta naught is significant. Okay, that is okay. What is beta naught? Okay. Covariate A's. That is, A's is significant. Okay. And other up and up to presence or the absence of up to 50, they are not significant. Because negative and positive, negative, positive. P values in this. That is for the model 1. Okay. Model 2 is without variety. Okay. Here also beta naught, A's factor is A's. A's is significant in this. But 2 are not significant. Model 3, A's is significant, beta 1 is also, both have negative values. Beta 1, presence and absence of appendix. That is there. Model 4, beta naught is significant. That is there. Model 5, again beta naught and beta 1, these 2 are significant. It's A in presence. Here only none of them are significant in the model 6. Now I am just taking the account of which model is better out of these models. Whatever, 6 models are studied. And also comparing the earlier model, gamma, correlated gamma variety model. Okay, I'm just doing the earlier model, that is this one. Okay, when you see the model 1, 51, this is model 3, 50, 31. See, model 5 is least. The value of AIC is least, that is 4933. And BIC is model 5 is least and BIC model 5 is least. That means positive stable, correlated positive stable with baseline generalized log logistic type 2 is better than all other models. Because all other models, the values are high as compared to these 3 values. Okay, then this model is better. This gamma model is considered in my earlier paper. I'm just taking the values of AIC, BIC, DIC. just to comparison. Here also it performs better as compared to correlated gamma. One can also have a comparison with correlated inverse Gaussian. There also this model 5 is better in that case also. I don't have the values of inverse Gaussian. Okay, now the base factor that is given here. Model 5 if you take, that is better always. Model 5 and model 5 with 6 and 3. 5 with 1. That means 5 with and 3 and 6. Okay. Everywhere you can see it is high comparison. The base factor. Okay. That means they are very strong. That means model 5 is better than all these remaining models. From here also we can conclude model 5 is better. And this is a...
Only 5 minutes left.
Okay, I'm almost done.
Yeah.
This is a summary of the plots for different T1, T2 in different. The first one is log losses type 1, type 2, and modified inverse for the T1, and this is for T2. This is for the correlated Fraternity model. Okay, when we use positive stable Fraternity model in that case, they are very close to the step function, that is a non-parametric and parametric. They are very close. That means it fits the model graphically also. That means. Okay, thank you. I'm done. Thank you for the...
it is time for interaction with the speaker.
Yeah.
If anybody wants to clarify anything, please come forward. Any clarification? Sir, one small question.
Yeah.
You are focusing your attention on continuous models only.
Okay.
Is there any work on discrete models in this of this type?
Discrete also it's possible. I think shared Fraternity model, there are some research papers. But correlated, I have not seen any paper on the discrete model. Shared Fraternity, there are some models are there. Okay, correlated this shared Fraternity model in the discrete case.
Okay.
The Fraternity is a discrete random variable that is there.
The discrete analog is there for the Gumbel distribution. So definitely,
yeah, that is possible in the shared Fraternity model.
Yeah,
that is possible. But there is a semi-parametric also. When the baseline is not completely non-parametrics, one can also have correlated shared Fraternity models. All things are possible. Even in the case of when the Fraternity random variable is stochastic variable, not stochastic random variable, stochastic process. When it is a process, then also it is possible to have Fraternity. Say gamma process, Weevil process, or some other process. When Z is some Z, instead of Z, you can take ZT. Some process. That is also possible.
Any other questions, please? If there is no further questions, let us congratulate Professor David Hanagel in the usual way. Thank you, sir. Thank you very much.
Thank you very much.
Hangar, please take out the presentation.
Okay, I'll just take
it. Yeah. I think we'll straight away go to the next talk. The next talk is by Professor Muralidharan. He is a very close friend of mine for so many years. We are together for several academic activities as well as several conferences. Professor Muralidharan took his master's degree from Calicut University in 1987, securing first rank, and PhD from Sardar Patel University. He had been with the MS University Baroda for more than 25 years. His areas of interest includes statistical inference, reliability modeling, and life testing statistics. He has published more than 130 research papers in national and international journals. He is the co-editor of several academic journals in addition to our popular ISPS journal. Recently, he has started to write some books. I have seen two of his books, one on quality management and one on sampling theory, I think. On behalf of all of you, let me welcome Professor Muralidharan to this conference and invite him to deliver his talk.
Thank you very much, sir.
Is 40 minutes.
Thank you very much, sir. After a long time, we are meeting online.
Yeah.
Right, sir? Yeah.
Yeah.
Thanks to Professor Satish Kumar also for his untiring effort in holding an international conference successfully for many years. I'm really appreciating his effort, his team. Now, regarding the talk, I am a bit apprehensive about my talk because this is an international conference. Most of the time it is going to be technical. I in fact discussed with Satish Kumar whether it is going to be a suitable talk for this conference. And he said there is no issue. I said there are a couple of reasons why I brought this concept, this particular talk here. You know, for a few years since I am working on quality related concepts. Yes, of course, I have written a few books also on that. So here is the one which is coming up very soon in the market. It's still under production. In another 2 weeks time, the proofreading, everything is over. So in 2 weeks time, this will be out in the market.
Published by Springer.
Springer, sir. So you can see the title also says it is on quality. My earlier book with Springer, I also published one more book with Springer. That's also on Six Sigma quality philosophy and all. So this is not exactly Six Sigma based, but a concept which I have conceived for many years as by publishing short articles in various magazines, bulletins, etc., etc. So it's actually a compilation actually. And there's another story, a small story behind this. Actually, I was asked by my university administration to introduce a topic, a course for foundation level undergraduate course. And I was told that it should be acceptable to all stream, anybody joining BSc program with A group, B group, AB group, any group should be able to, study, and that way it should be a popular kind of thing. So that is the reason where I started, writing this book. So finally, it is now in the book form, and very soon it will be going to be in the market. So this particular talk is partially based on this, and it's also based on partially on this particular book chapter as well. So you can see very recently with my student Neha, we have a chapter 17 in the book called Advances in Interdisciplinary Research in Engineering and Business Management, again published by Springer Nature, right? So the original chapter title is Quality Management Yesterday, Today, and Tomorrow. So what I did was I compiled some few things from these two references and brought this particular topic here only to make you, at least the upcoming students who are in the MSc program or maybe research scholars here and there, to have some soft corner towards quality movement in India and outside. So they can also contribute. I'm sure. So my purpose here is to expose what is happening in the market and how the quality has evolved over a period of time and what is happening in the business really. So that's my purpose. So I will run through some of the slides very quickly, and later on I will concentrate on a few concepts like Industry 4.0. And that's what is the buzzword nowadays. Okay, so we know business is changing. No doubt it's all for better. Okay, the business we have seen for years together. A lot of changes are happening these days. New generation business. People used to say new generation people, new generation products, new generation services. Many things are changing. Okay, it's fast and timely, on demand and customer friendly. This is how we look at the business these days. Expanded customer base and product service bases, improved profitability and reliability. Like there are many issues now happen. And overall, you can see data is also getting bigger and bigger every day. This is another challenge for us. You will come to know how quality is close to statisticians and statistics subject to this presentation. In fact, it is our job. It's the job of statisticians and data analysts to see that the future quality management will be exclusively residing with them. All the products and services are going to be automated. It's already started. You can see from 2000 onwards, the almost all products and services are automated. To some extent, human intervention is very less. Where there are human intervention, more definitely there will be a quality problem. But quality problem is still there. So that's what I am going to address here in this presentation. Okay, in the same way, the business is changing, the quality concept is also changing. Okay, now business is all about quality now. People talk about every aspect, people talk about quality now. How fast and quick the delivery is done, that is how quality means for many. Even new generation people, especially the new generation guys, if you ask them what is your the meaning of quality, they may say, I want everything fast. The delivery should be fast, that's all. Quick. They want the quick result, everything, fast food concept, we all know that. Okay, we want everything fast. How much environmentally friendly principles and features are incorporated in the product service, that is how some people see quality. This was not the situation some 2000 years, some years till 2000 or before. It was altogether a different issue. People want more in quantity. Now people are not, we want more also, at the same time we want quality also. How much of sustainable practices are built in the product or services? That is how people look at quality these days. How much automation is there in the business? Is it made through robotic machines or automatic machines or etc.? How it is made? So that quality is ensured. That's how people look at it. How much of real-time monitoring and surveillance? A very important issue where statisticians can contribute. And this is where we use SPC, SQC techniques. We learned many such techniques in our statistics course curriculum. Real-time monitoring and surveillance is everywhere. Surveillance, CCTV camera is everywhere. You can see how much improvement is taking place. In every aspect of our day-to-day life, improvement is taking place. Somewhere we need monitoring and surveillance as a continuous process. And the most important thing is how much lean, green, and clean aspects are used. This is what I addressed in my latest book, Lean, Green, and Clean Concepts all combined. You won't get, I'm sure that you won't get all these three concepts combined everywhere. Lean concepts are discussed in isolation. Green concepts to some extent are discussed in isolation. Green chemistry, green biology, green environment, etc., etc. Now quality concept is already almost changing altogether. There is a paradigm change taking place. So this is where I think the statisticians should contribute and we should take a note of it. Look at, for example, this is based on my own book. There is lean green concept of quality dimensions in every aspects. You talk about any products, for example, you talk about any service, for example, you talk about any items, for example. You can clearly identify what is the lean concept, lean dimensions, what are the green dimensions, what are the clean dimensions. If you are able to do this, you can very easily manage the quality. That is the importance of it. If you identify the lean dimensions, then you have a lot of lean principles applies there. If you can identify through green dimensions, you have a number of ways to manage quality there. Green quality is there. Similarly, clean quality is there. So you can see every product. So look at my book if you want to have more details. I have even identified some products, for example, drone, for example. It's a very good concept of, these days people are using in most of the cases, business activities and of course terrorist activities also, and it's very unfortunate. Last 2 days we have been hearing about drone activities happened in Jammu Kashmir. It's also used for that kind of activities also. It should not be, actually speaking. But anyways, that's the purpose. That's the extent of use of the instruments and the items. And so quality management is all together managing quality of services, products, designs, customers, etc., etc., etc. In every case, people expect some amount of excellence, some amount of quality. So how are you going to do it? Traditional method will not work, because we have progressed fast and we have progressed like anything. Technology is progressing like anything. Scientific innovations are progressing like anything. We cannot get along with the old traditional values every now and then. We need to change ourselves. We need to change our outlook altogether. Okay, so we need to have quality manuals for that. Yes, of course, we have quality manuals, standard operating procedures for each and every product. Okay, it's a collection of business process focused on consistently meeting customer requirements, consistently meeting customer requirements. Look at the online marketing platforms like Amazon, etc., etc. They are consistently providing business. They are retaining their customers based on their consistency in their services. So quality management is a purpose and it's a must. You cannot take it for granted. You cannot take any customer for granted. You cannot take any service for granted. It's aligned with the organization's purpose and strategic direction. So we want all those things. So the goals and objective is very clear now. Customer-focused products, satisfy the customer expectations. They can be ultimately, identified through identification, prediction, prevention. A lot of problems are there. You need immediate, real-time monitoring. That is where I told you the statistics comes there. We need a real-time monitoring to rectify the problems if it occurs frequently. Product and operational excellence improve customer satisfaction by ensuring the products meet customer requirements and they are available when and where they are required. That's also very important. We should have a product, we should have a service when and when it is required. If you get a credit card, the PIN number is not mailed to us, then what is the use of it? Generally, you see, you also might have experienced some few years ago. Okay, now it is very fast. The moment you get the credit card, you can have generate PIN through internet banking or online banking or through customer service call also you can have. So that's the requirement now. Quality management. Otherwise, people will see the service providers are many. Competition is so high, where you need to be very, very fast in executing the things. Otherwise, there is no meaning in the quality. Quality principles, it's a traditional way. If you look at, there are a lot of customer focus with the principles and products, and these things should be strong leadership, very, very important. Confidence building through engagement of people. This is very, very important thing. If you look at any service industries, banking, insurance, or any of these things, they engage people through a lot of ways, so that they retain their customers with them. This is what they're doing. They are giving offers, they are giving discount, they are giving all kinds of amenities to attract the customers. Okay, confidence building through engagement of people. This is where the quality management, the next generation quality management comes in. And process product approach, that is very common. And improvement in continuous process, make it a continuous process. And evidence-based decision making, and this is where statistics and data analytics and all those things comes in. Evidence-based decision making. You can use artificial intelligence techniques, augmented reality, virtual reality. There are a lot of techniques which is coming, evidence-based decision making. Okay, a lot of scope for statisticians to work on. And relationship management, good relationship, good business. And there are a lot of improvement tools which people are already used. And there are many new generation principles also coming up, like Six Sigma concepts, capability, maturity, model integration. They are very computer-based, computer-oriented techniques. Human intervention is nowhere going to be there, and in future, machines are going to interact with the products and services. No person in between, no person to intervene in the process. The correction also will be done by the machine. In case something goes wrong, correction will be done automatically. So this is the height of it. So we have total quality management, total protective maintenance, KAISEN. KAISEN stands for continuous improvement. 5S plus safety and security techniques. It's a Japanese technique. 5S stands for sort, set in order, office keeping procedure, that's all. Okay, sort your items, keep it in order, the products and service, whatever you want to say. sustain the product, the improvement, safe, keep everything safe and security. It's a common going to be in every product. 3M techniques, again a Japanese technique, Muda, Mura, Muri. Muda means waste. Waste control. How do you control it? Every product now you can see that it should not be contain a certain amount of waste. If that is the case, then the product will not be sanctioned or quality checked. Quality clearance will not be there. Okay, mistake proofing, setup reduction, just-in-time approach, Kanban, workplace management. Kanban stands for workplace management. Six Sigma concept, capability, maturity, model integration. This is another high-end level of quality. There are 5 stages of quality of assessment. Stage 1, stage 2, stage 3, stage 4, stage 5. Stage 4 is full of statistics, and stage 5 is simply statistical analysis and prediction, nothing else. This is what we are going. The qualities which is coming up, is going on. Now let us quickly go through the industrial revolution, how the quality has evolved through the industrial revolutions. As we all know that there are 4 revolutions as per on record. And the latest one is the Industry 4. That is how people signify. 4th Industrial Revolution is called Industry 4. They're very, very important thing. All are based on data. So what is common to all this is this technology, socio-economic condition, quality management system. That is common to all. Because we know first industrial revolution technology was not improved, was not up to that mark. Second industrial, slowly and gradually the technology started picking up. Third industrial revolution, we have fully, the automated machines also available, robotic machines are also available for production and services, everything. And 4th industrial revolution, you can imagine what is going to happen in future. Tremendous improvement, no human intervention. Many people are going to lose their job. That is what the current trend says. Socio-economic condition also changed according to the revolutions, industrial revolutions. People before, the 18th century, during 19th to 20th century, 20th and after 21st century, we are now. You can see the changes happened. Okay, so for the details and everything, please go through this. So it changes every value system, it changes the socio-economic system, and everything, every status of the life also changes because of the revolution. So let us see how the things have changed during each generation. Quality during the first generation was embodied in fitness for purpose. That time people used to see only whether it is okay or not, whether it is okay for consumption or not, fitness for use. That used to be one of the definitions for quality, fitness for use, fitness for purpose. Satisfaction, how much it satisfies the customer, etc. This used to be. So that's an old concept now. Trueness of material. People ask for more, that's all. That nothing more. People hardly bother about the quality actually. So quantity is what is more important. Quality management under such circumstances were largely left to the workers, supplemented by the product inspection by supervisors. That's all. There will be somebody to monitor a supervisor. We may call it a supervisor. Nothing. And defective products were either reworked or scrapped. That is what has happened during that revolution. So input output, we generally see demand and supply side and see whether the products which are supplied, the demand is equal to the supply and all those things. So that kind of equation is seen at that time. And second generation, slowly the electrification started, the whole thing started changing. So quality of product, service, and quantity of work increased with the speed and lesser operational adjustments and so on, and many others. And many factories released 30% increase in output just from shifting to electric power. That's the impact of electricity at that time. And mass production also started slowly. It started with exponential growth. And quality management during that generation was not a serious concern, but necessity of quality products and quality tools became a buzzword at that time. Slowly it started. Okay, quality is important. Quality movement is started working on. That's all. But by the time the third generation came, the full realization came. This concept started generally in manufacturing and the automobile sector. You can see maximum automobile cars and the automobile products started booming during that generation. So the quality concept was centered only on manufacturing. When it's manufacturing automobiles, definitely we need a lot of products and materials are produced and used in somewhere. So the quality becomes a very important issue there. And that's the time where many quality gurus, you can say, business gurus started, they came into prominence. To name Deming, for example, he is very famous for his PDCA rule, plan, do, check, act rule. Very important. Deming wheel, we are all familiar with. Many often in SQC, SPC classes, we were taught that yes, Deming wheel is a very important tool for improving quality, PDCA rule. Shewhart, of course, we all know that's very famous statistician, introduced control chart in the Bell laboratories. Then came Crosby, who introduced the concept called zero defect concept. Then Juran, quality trilogy principle. Taguchi came up with the quality engineering concept, robust designs, and so on. Orthogonal designs, factorial designs, etc. He brought a lot of things. So Taguchi was literally a statistician. All others are management guru, management and engineers. Taguchi was basically an engineer come statistician, and he had a lot of experience working with Indian scientists and statisticians in ISIs. So the contribution started booming up. Quality, the people have started started asking for quality in the real sense. Okay, the feeling of quality started during the third generation. So the quality during this generation was set into SPC, SQC techniques and all other new technique, newer generation techniques like Lean, TQM, Lean Six Sigma, supply chain concepts are started. So supply chain concept. And all this are talking about statistics, nothing else. That means quality management in future is definitely going to be through statistical principles and statisticians. It's going to be, and many literatures also says that in the future, quality management will be rested with statisticians only. Okay, and even during this time only, we have seen advancement of emails and e-commerce started in full swing. Just imagine after 1900 onwards, so all these emails, e-commerce started in full swing. So emails, and it's one of the best way of communication directly without paperwork and all those things. High awareness of quality in products, process, and services increased. High competition within the business world. Last 20 years have shown all the competitions in the market. The business have changed entirely, for entirety, you can say. And customer-focused products and services became the norm. Only customer-focused products. If the producer is not able to provide the things, then he is out in the market. There are many other people who are lined up to provide the products as per the customer's wish. So the competition is so high that according to that, quality also improved. Now you can see every products and every services, a certain amount of quality is already there. It is inbuilt. So in future technology especially is going to have the quality inbuilt. So that's where the techniques and the newer data science techniques works. Demand for Lean Six Sigma, green concept, supply chain also concept started. So for that, I think interestingly, the students should read this particular book, The Machine That Changed the World by Womack et al. So one of the best, wonderful book. You can see how the things have changed. Okay, the book is about actually the real, project execution done at Massachusetts Institute of Technology. 5 million 5-year study on future of automobile industry, and which later on came into the name Lean Production System. So please read if you have that book. Okay, so new generation perspective, this is what I'm now focusing on. So even through my own contribution also, I'm thinking of, contributing more on this. So what is happening now? Automation and connected devices will be the key players of future area. Everything is going to be connected with some machine or some instrument or some gadgets. And you know the amount of work a mobile can do now. We all have that feeling. Now imagine what is going to happen in future. Okay, we feel now that yes, everything is done, all innovation is done, all innovation is over. Not exactly. We are going to see many more innovations in the future because artificial intelligence techniques are going to integrate in every aspects of business. Self-managed systems will be able to collaborate with each other with transparent data sharing. Data sharing is another thing, interesting thing. Cloud computing concepts, you can see how that it is shared. One die concept, this a lot of storage concept, because data is getting bigger and bigger. We need data storage devices also. Big data concept itself is going to give a lot of challenge. It is challenging because analysis is not easy. So people are finding out new diagrams, new programs and softwares for that. Still, it is not realized. The industry will be in a position to run their functions without human intervention and dramatically increase productivity to that. And high quality products and transport services become very common. Now imagine, definitely we'll have to have extra additional cost for all this. If the quality is small, definitely there will be an additional cost is going to come. Okay, so this is going to be a norm for them. And people are ready to buy, to have that things. People have money and people are ready to pay for. If extra quality is going to come, definitely people will be there to pay more. So data will be the most powerful enabler of the 21st century. So 21st century data will be the most, and technocrats will be one of the most empowered groups of human race holding the power through data supremacy. So that means data scientists and statisticians, or the whoever comes under this particular umbrella, should have the benefit, or you can have the gain. So they are going to be responsible for the entire aspects of organizational business. So get ready for this. That's my request to all the youngsters who are coming up now. Okay, so without data, nothing is going to happen. If you want to talk about quality, you need data-based decision making, data-based or measurement-based decision making. This was not the case till a few years ago. All on by perception. People talk about quality in terms of perceptions. Now, perceptions will not work. You need evidence to say that yes, quality has improved, and that is possible only through data management. So, quality management is altogether is going to change in the near future. So the main attraction of new generation business is the Industry 4. So Industry 4 is nothing but the integrated industries, or smart manufacturing, or smart factories. This is how people used to say these days. In the business arena, people used to say this way. So smart factory is going to come. Everything is smart factory. Even you look at the education is also in business industry, you can say. Okay, we are offering a lot of courses. This was never been a case some few years ago. Okay, we have a traditional course. Okay, first group means physics, chemistry, mathematics. Second group means biology related. Third group means commerce, arts or related, etc. Now we have a lot of combinations coming up. We have a foundation level course, elective course, principal course. Even the new education policy 2020 also insists that it should be multidisciplinary and interdisciplinary. So what does that mean? We are going to have a lot of courses integrated in one particular discipline. So this is so it's going to be a factory altogether. It's ultimately going to be a factory. We are going to have construct factories in our educational institutions and educational campuses. So how are you going to be able to? So definitely quality management become a challenge. Okay, so quality definitely that should be assessed through data management or measurement based or data analytics based things. And one of the promise of Industry 4 is that digitalization of quality management. So digitalization, everything is digitalization. And we all know that. Transaction is done online. Almost all transaction, bank and insurance related transactions are done online. Okay, now we have every day improvement is taking place. Every day improvement is taking place. Okay, now the flexibility is increasing, the importance is increasing, everything is the, and people are also using the services. So digitalization anyway is going to be a part and parcel of our life. So mobile with a good, so in future this is going to happen. Mobile with all types of features will be integrated in that instrument, and you use that in your workplace, house, wherever you, even during travel you can do business. We have started doing that also. Okay, on travel people are doing business. And of course, because of Corona, we have been seeing for the last 1 year, work from home. Every business activities are now at, I don't know whether no physical mode, nothing. This is going to happen in education institution also. Okay, slowly and gradually, we are also going to face this problem. We may now say that yes, we don't have staff to teach. We don't have staff to teach. I'm sure in future we don't need staff, but the machine will take over. With the teaching activities, everything is going to be taken over by the machines. So that's where the advanced technology like artificial intelligence, virtual reality, augmented reality, AR, and machine learning, deep learning techniques they are using. They are automatically improving the quality of every function of the business. Okay, so it is guaranteed, and we are going to have, and we are going to feel it very soon. Okay, and this is based as per the paper, say Jan 2019, it's a very recent paper. It says this is based on few principles. For example, machines and devices that connect and communicate with each other freely. This is going to happen and started already. Okay, information transparency and virtualization of real world situation become frequent. Okay, that we already seen. Some houses you can see. Nexa is there is an Amazon instrument which actually interacts with the people. If you give the instruction, If you ask for the payment, it will give the payment. If you ask for sending the mail, it will pay. You will Google Talk. It's, even in your mobile, you can have that you can have interact with the machine. If you ask call so and so, it will call the person concerned, if provided that person's name is there in the contact list. That means it is so close. Now imagine what is going to happen in the near future. And whatever happenings now is very, very fast now again. All business activities, the innovations are taking place very fast, and it is very to the point. Information transparency, virtualization of real-world situations become frequent, and capacity of the system to take support humans in decision-making and solving problems will also be common in all digital platforms. So it's very, very important, and the challenge is also very, very high. And the ability of the cyber system to become autonomous and make simple decisions on its own will be the demand of time. So the time requires that. We are asking for, we have to go according to the time. If we left behind, things will be gone. If you are all working with the old traditional method of business, no way. Now many such companies are shut now. Nobody can come up with the new technology or new changes. They are unable to adapt. We know we had this problem few years ago. Many people were asked to retire from their service because those who are aged 50 or above, they could not manage with the technology. Computer, especially the computer language, I mean the computer, handling a computer system was very difficult for them. So things are going to happen in very near future. Many of maybe future generation people will definitely sustain. The people like us, or people slightly above, I mean, who are about to retire, on they will have a lot of problems in future, because accommodating the technology in their day-to-day life become very, very difficult. And major components of Industry 4 contains cyber physical systems, Internet of Things, IoT. It's very, very important. You know, it's all data-based. Smart factory, that's what we have already discussed. Internet of Services, IOS, robotics, big data, cloud computing. Tell me, it's all about data. So data quality is a very important challenge. Now, who will take will take this challenge? Who will be responsible for this challenge? That's my point of discussion here. I'm sure that definitely statistician has a say now. In future, statisticians are going to be, or data analysts are going to be responsible for this data quality. If they are working with a company, definitely company should see, or company will depend, company will ensure all their responsibility on the data scientists of their company. So data is at the core everywhere. Data is at the core. So get ready for it. And quality management industry for current situation. And currently what is there? New technology demands significant cost of investment in terms of learning and skill acquirement for quality maintenance. And this will together create a new working class with a significant knowledge of advanced technology. So this advanced technology underlined, it's a very, very important. So what is the advanced technology? Nothing else like artificial intelligence and data analysis techniques, nothing else. Whether you are science, pure science, zoology student, also need some amount of statistical analysis or quantitative analysis for your survival, maybe for your research publication, maybe for your research, maybe for your sustainability. You need some amount of quantitative analysis. So the future technology is going to be a part of your life. So adjusting with the technology, adjusting with the knowledge, penetration. So you need to have some amount or some expertise in some. You can see online courses these days offered. Most of the companies and most of the even NGOs have started imparting education in artificial intelligence techniques. Okay, many big companies are offering courses online, free also, paid also. Lot of courses are now offered only to make people understand the importance of newer technologies. Because adjusting with the future technology will become very, very serious issue. And monotonous, repetitive tasks done every now and then, same thing again and again, will be completely replaced by technology, and which will create a new group of 21st century unemployed people. That's what, according to Harari in 2008. Okay, so imagine what is going to happen now. Okay, we have already started feeling the effect of newer technology, the technological innovations and improvements happening in the science and technology, and that is not going to stop. It is going to have more and more. We cannot have any say now. We cannot have say that we don't want. Even in medical inspection, even a doctor's necessity is going to be reduced through machines. They are going to use virtual machines and augmented reality techniques to construct prototypes and to educate and training their fellow beings. And they are going to use that kind of instruments and machines and this thing, etc. You can experiment everything on, earlier it used to be on, the dead bodies, for example. If a surgery is to be performed, if surgery is to be trained, then the people used to have it on dead bodies. And we have now all compliances, government compliances, health-related compliances that you should not experiment anything on animals and anything on human beings. Everything should be on prototypes, which are going to be now a virtual reality in the future. That's what is going to happen. And that's where the surveillance and monitoring aspects also comes in. Okay, who is doing what is doing? Everything is monitored. You can see in Kerala itself, a lot of activities are going on, cyberspace related activities, monitoring, surveillance, CCTV cameras and all those things. Crime rate is increasing. So how are you going to have a service or transparent service? That means this is the only thing. Make surveillance and monitoring continuous activities. In every household, people are going to have CCTV camera installed in future, and this is when it's going to happen. It's already happening now, but it's going to happen in every houses. Especially the newly constructed house will definitely have a facility where CCTV camera can be installed. So that's going to happen.
5 minutes.
Yeah. Okay, sir. In 2 minutes, I will close. Is it okay? My time is over.
Yeah, 5 minutes.
Okay, sir. I will just do it. So there are new generation business models. Let's look at this. E-commerce, e-governance. That's what government is doing. Green statistics, lean green concept, which I am discussing here. Reverse logistics, benchmarking, reverse engineering concepts, simulation and process modeling, blockchain and Bitcoin concept. The latest in this bandwagon, blockchain and Bitcoin concepts. Okay, there's a few chapters on this kind of concepts in that book. Even we have quality assessment models. We have a lot of things. We are also familiar with ISO 9000 series and the environmental management system, etc., etc., etc. We are now going to have carbon monitoring, carbon auditing, emission auditing in every education institutions. Even new education policy also insists for that kind of auditing. So it's going to happen now. Climate model assessment, life cycle assessment, cleaner production assessment. Again, there is a full chapter on this in my book. So again, you can see different lean, green supply chain management systems and models and everything. So plan your activities, identify the problems, evaluate what is required, implement the solutions, verify the solution again, and sustain. This is how the whole thing is going to be. So the lean, green supply chain, when I talk about the complete quality management, you need to go for this kind of supply chain management. And that is what is next now. Thus, for adopting quality management in future, the company should realize to prioritize their quality areas. They don't have to go for every aspect of their business functions. They have to prioritize their quality areas. Then they will have to see where they need the quality, where they need to improve, where they need to bring the supply chain concept, where they need to have Six Sigma concept, where they need to have lean manufacturing, where they need to have various category improvement programs are now available, and use and apply the most suitable method as per context. We have to go for ultimate analysis over appropriate analysis. And whose responsibility it is? I think it is the responsibility of statisticians or data analysts to do this. Okay, use ultimate analysis or appropriate. We have been doing appropriate analysis. We have been in classroom, we have been teaching appropriateness based theories and tools and methods and this thing. Now, it's not going to stop there. We have to use ultimate analysis over appropriate analysis. And companies with a strong quality foundation can further advance their QM practices through adequate technological integration. And such technological advancement will help organizations to work with real-time data, which will help them to address quality issues in advance. And that's where the data science comes from. So the entire quality management is going to be a responsibility of data scientists. The data scientists, when I say it, includes statisticians as well, or mathematicians, information technology people, etc., etc., etc. Thank you very much.
Okay, now it is time for interaction with the speaker. If there are any questions or clarifications, you can come forward, please. Anybody?
Anybody? I know that in Kerala, people are not too much interested in these kind of concepts. They are very good at technical and this kind of, very hardcore probability theories and all those things. So the acceptance will be very, very less. Anyway, my objective was to introduce my book, the forthcoming book. So thank you very much for your patient here.
Professor Muralidharan has given an idea about the recent trends in quality management and the importance of quality improvement in the recent society. And the recent trends he has brought to our attention. We shall all thank him for the nice presentation in the usual way.
Thank you very much, sir.
Nice.
Thank you very much.
Now, let me express my sincere thanks to Professor Satish Kumar for inviting me to be a part of this auspicious event. Let me also thank the co-chair, Dr. Krishna Kumar, for the nice words spoken about me, even though he has quoted about me based on a past biodata. So thank you very much. Over to Professor Satish Kumar.
Thank you, sir.
Okay, thank you, Professor. In fact, Krishna Kumar is a new faculty of our Department of Mathematics.
Yeah.
And he is completed his MSc and PhD from Madras IIT. And
good.
Yeah, in the Department of Mathematics.
The new faculty I do not know.
Yeah, Professor. Yeah, that's right.
Yeah.
And he's very active and young.
Nice. An IIT product coming to our department. Your university is very nice.
Yeah. He's doing good works in spectral theory, operator theory, etc.
I don't know.
Sir, in CUSAD, I am collaborating with Dr. Kiran Kumar in mathematics department.
I know. Yes.
And his guide, Eminent Statisticians.
Yeah, sure.
My guide, Professor S.H. Kulkarni and Eminent Nambudiri.
Yeah, we were in one department earlier.
I know. And they were their guide, Professor B.V. Limai. You might also know him from IIT Bombay.
Okay.
So we are like a same group, same family, like whatever you guys are.
That is nice. Okay.
Thank you, Professor K. Muralidharan Nair sir and Dr. Krishna Kumar for chairing and co-chairing the session and completed the session in a nice way. And also our gratitude and thanks goes to the speakers, Dr. Hanagal, Professor Hanagal and Professor Muralidharan. In fact, very nice talks, nice session. Thank you each one of you. On behalf of the Department of Statistics, we extend our gratitude once again. Now, we are let us move to the next session. I think Professor Shankaran is here to chair that session. Whether Professor Shankaran joined or not. In fact, there is 5 minutes more. 5 or 7 minutes are 5 or 7 minutes are there because Professor Sadgupta is our next speaker, and let us wait a few minutes to Professor Shankaran. I shall call him. He will join together.
Yeah,
since he is the Pro-Vice Chancellor of the university.
He is always very busy.
Yeah, always busy. That is why even then he finds some time to associate with us in chairing and giving talks, all those things. Like, yeah, Murali sir also, we are very grateful to you, sir, for your support. let me to contact him. Yeah, he's here. Yeah. What about Vinish? Vinish is also a product from Cochin University of Science and Technology. He student of Shankaran sir or Murli sir, Unnikrishan sir. I think so. Vinish, we have given the co-chair to Vinish. So anyway, Professor Shankaran needs no introduction to the statistics fraternity, especially because, in fact, the morning session we have given some words about him, and he is very popular. I am not wasting time. Professor Sadgupta is waiting. Yeah, Professor Shankaran, please carry over the session.
Sorry. Hello? Hello?
So we can hear, sir. We can hear.
Okay. Good afternoon and good morning there, Professor Sadgupta. So,
very good afternoon.
Thank you, Dr. Girish, for giving me this opportunity. I'm really honored to chair the session given by Professor Sadgupta. Professor Sadgupta is very close to me, and he is a professor and head of the Department of Statistics, North Carolina University, and he visited our department also. He is the editor of Journal of Statistical Theory and Practice, and he has good number of publications, and he received many fellowships, awards, and he is a very active researcher in the area of mathematical statistics. On behalf of all of you, I request Professor Sadgupta to deliver a lecture which is very useful for young researchers. I request Professor Sadgupta.
In fact, we have dedicated this session to honor Professor P.V. Sugatmi. Professor Sadgupta is working in the area of...
Well, thank you very much, Professor Shankaran and Professor Satish and other, senior academics and other participants. It's a pleasure to be part of the conference. And Dr. Satish, thank you so much for inviting me. It's early morning here in the US, and I think late afternoon, evening in Trivandrum. I have fond memories of visiting both places, Trivandrum as well as Kochi. And thank you for hosting me in the past, and also thank you for hosting me virtually this time. And hopefully I'll make a visit again in person. So let me share my screen. I usually use Zoom, so I'm not sure if everything will go smoothly. But if there are hiccups, we'll have to find a way to deal with those. So let me share my screen. Can you see my screen?
No, Professor.
Let's see.
How to move You have to
Yeah.
go to that small arrow.
I did that. So let's see if I.
Entire screen. Click on that.
Yeah, I do that and then share your entire screen.
Then a pop-up menu comes. And click on that, so that share button will be active, isn't it? Yeah, now it is coming, Professor. It's coming.
Okay, and let's see if I can find my talk here somewhere.
Yeah.
I'm just struggling to find my talk.
So first, it is better to open the talk, that slides, and then do the.
Yeah, just one second. Can you see it now?
No, Professor. Once again, in fact, that presenting situation goes away. So once again, start presentation. Share the presentation. That click on that arrow and.
I did, and it brings this this screen for me. So let's say if I do a window.
Yeah.
Can you see it now?
Yeah, now it is coming, Professor. Now it is coming. Now it will be visible. Yeah. It is fine. Can make it full.
Okay. Yeah.
Now, yeah. Fine.
All right. Well, again, thank you so much, and I'm sorry for the little mix-up. As I said, I always use Zoom, and so this is a new sort of experience for me. In any case, let me get started. This talk is about randomized response technique, RRT. It's a survey technique which is used when the questions in the survey are very sensitive in nature. If you ask those questions directly, that have you done drugs, have you beaten your spouse, and things like that, people will not respond truthfully. They may not respond at all. They may give you wrong response, which is kind of a dangerous thing. So it's a RRT, is a survey technique where the respondent is allowed to give you a randomized response or a scrambled response. Now, when you do that, essentially you are adding some noise to your true response. And when you add your noise, that's where the privacy comes in. So the respondent is able to maintain some privacy around himself or herself. So more noise you add, there'll be more privacy. Less noise you add, there'll be less privacy. But then again, if you want to get more privacy, you need to add more noise. And when you add more noise, the data is that much unreliable. And therefore, the estimates will be inefficient. So there is this struggle between efficiency and privacy. Just like what you see in confidence intervals, you can make the confidence interval very large and gain a lot of confidence, but a large confidence interval is useless. So something similar is going on here. So that's one thing I wanted to mention. The other thing I would like to mention is the work I'm going to present today is largely work done by undergraduate students. I think, I don't know what the culture in India is today. In my time, people begin doing research when you become a PhD student. But in America, students begin doing research when they are undergraduate students, BA, BSc students, even high school students do research. There's a major national program. Actually, let me talk about this by stopping the share for a second. And I may run into the difficulty again. Can you still see my screen?
Sorry, Professor. Screen.
Can you see my screen?
No, Professor.
You cannot see?
Yeah, you cannot see. Once again, you start. I think so.
Well, so as I was talking about that thing while I have this break, let me mention that in the United States, undergraduate research is supported in a big way by many grants. Like National Science Foundation gives a lot of grants. And the talk I'm going to give today, pretty much the work is done by undergraduate students supported through that grant. So some of you may find that to be interesting, that undergraduate students can do nice work and publish nice papers in good journals. So I just wanted to bring that message out. We have been involved in these projects for a long time. And this work is funded by two recent grants, a 2018 grant and then also a 2020 grant, which will continue for 3 years. So just wanted to mention that. So let me go back with my presentation and see if I am going to be able to see that. Can you see my screen?
No, sir. No, sir.
So that's a struggle.
Earlier it was there.
So let's see, share the entire screen.
I think you have to do it once again, the earlier thing. Probably.
And you still cannot see it, right?
Yeah, Professor.
Okay, now I think it's starting.
Now it is coming, Professor. Now it is coming. Yeah. Now we can move to your slides.
Okay.
Alt tab. Yeah.
Can you see it now?
Now it is fine. Yeah. You can see.
Okay. All right.
Now we can move. Oh, yeah.
Okay. So just wanted to tell you the background of this work. And as I was telling you on the previous slide, RRT, it's a survey technique which is essentially needed when there is some doubt that the respondents may not respond accurately. There's a reason for them to lie. So that's when this technique is used. So why do you need RRT? Well, your survey may involve sensitive questions. Now, what's a sensitive question? A sensitive question is which you are not prepared to discuss in public. And it's a very private matter. So when you have questions like this, RRT is very useful. Social desirability is an important issue. And we all want to look good to others. And therefore, we don't admit to bad behavior. So SDB is an important issue. And if you don't take care of those things, then your response rate is going to be very poor because people will refuse to participate in the survey. And even worse, they may give you inaccurate responses. So this is a small outline of my presentation. I'll talk about RRT models, of course, and there are different kinds of RRT models. There are models called full RRT, partial RRT, optional RRT. You can also classify RRT models based on the nature of the response. You could have binary models, you could have quantitative model, right? You could have additive models, you could have multiplicative models. So there are many different ways you can classify RRT models. There are some alternatives to RRT. That is RRT the only option left to researchers when dealing with sensitive questions? And the answer is no. There are other options also. But my talk is about RRT. There is the issue of respondent privacy and data confidentiality. Before the survey is collected, you have to ensure that the respondents have enough privacy. Otherwise, they will not cooperate with you. Even after the data have been collected, sometimes you need to maintain confidentiality around the data. It is becoming very common, at least in the United States, that the funding agencies, they insist that researchers share their data with others. It's called public release of the data. But when you release your data publicly, you need to create some kind of confidentiality around your data. You cannot just release it just like that, because then you'll be violating some pledge that you made, that data will be kept confidential. So you can release the data after adding some confidentiality around your data. And then one of the highlights of this talk will be the issue of a combined measure, a unified measure of privacy and efficiency. As I told you, they go in opposite directions. If you create more privacy, estimates will be less efficient. If you have less privacy, estimates will be more efficient. So there is this issue of putting those two things together. I'll also talk about some very recent contributions we have made over the last 1 or 2 years. And I'll make some final remarks. In terms of the alternatives to RRT, there's one thing which is very popular with psychologists called BPL, bogus pipeline. And I'll talk about what it is briefly. Sociologists, they use the SDB scale, social desirability bias scale. I'll talk about that also a little bit. And there's the unmatched or item count technique. And again, a few words about that too. So bogus pipeline, it's a pseudo lie detector test. The respondent is tricked into believing that his or her responses are being recorded by the computer. And if you lie, the computer will know that you're lying. So it's all a trick. So you convince the respondent that please don't lie, just be truthful. And but the whole thing is bogus, and that's why the name bogus pipeline. You might think, mathematicians might think that how could something like this actually happen? But this is a big area of research in psychology. Social desirability scale basically is a pre-survey before the real survey. It's a pre-survey designed to find out the tendency in you to look good. Some people are very, very straightforward. They don't care what others think about them, but many people are very concerned about how they are perceived by society. So this pre-survey or a SDB scale is a 13-point scale which measures the tendency in you to look good. So there are 13 questions. On each question, there is a socially desirable answer and there is an honest answer. If you answer in a socially desirable direction, you get a score of 1. If you answer in an honest direction, you get a score of 0. And at the end of the survey, the highest you can score is 13, the lowest you can score is 0. Higher your score, more is the tendency in you to look good. For example, one of the questions on the survey is, I'm not jealous of success of others. I'm not jealous of success of others, true or false. Now, if you want to look good to society, you'll say, yeah, that's true for me. I'm not jealous. But I think there are occasions when we all feel that how did he or she get this and I didn't get this? So there is some feeling of jealousy. It's always there. So if you say that I'm never jealous, you get a score of 1. If you say that, yeah, sometime I'm jealous, you get a score of 0. So that's how the sociologists, they measure the tendency in you to look good and then use SDB score as a covariate in group comparisons. Unmatched count technique also is a kind of a mathematical technique. There's nothing bogus about it. You have a control group and you have an experimental group. And suppose there is a particular question that, have you ever hit your spouse? That's the question. So the control group is given a list of binary questions that does not include the spouse beating question. It includes a lot of other innocuous questions where the answer is yes or no. And the experimental group has all those same old questions, but also a question on, have you ever hit your spouse? And then look at the number of yes responses on the first one and number of yes responses on the second one. The respondent is not supposed to tell an answer yes or no to each question. You simply tell that out of these questions, how many yeses did you report? So the difference in the two groups clearly indicates the proportion or the prevalence of abuse of your spouse. So there are these other techniques also. As I also mentioned, respondent privacy, it's a front-end problem because if you don't offer respondent privacy, they will not cooperate with you. They will not give you responses. So you are in trouble. So you need to worry about it right up front before data collection even begins. But data confidentiality is a back-end problem. So data are already collected and you are getting ready to publicly release your data. Now, why would you release your data publicly? Well, because you are required to do so. So when you release your data publicly, you can add a layer of noise to your data. And I'm including this theta here. S is a scrambling variable. Theta is some constant that you choose. Higher the value of theta, more noise you are adding, right? Lesser the value of theta, less noise you are adding. So if you add more noise, there is more privacy, but the data quality is that much poorer. So that's a struggle that we have to go through. Now, there was a time when people thought that simply drop the name and ID of the person who provided the data and your data is pretty safe. And that's not true anymore. There's this famous study in 2002 by a MIT PhD student. She took hospital records from Massachusetts General Hospital and patient data, and she matched those patient data with the voting record data in Cambridge, Massachusetts. And by doing data linking, she was able to identify about 80% of the patients as to who is who, including the governor of Massachusetts. She was able to tell that this particular row belongs to the governor of Massachusetts. And therefore, simply changing or dropping the name and ID is not enough. So she floated this concept of K-anonymity. That is, if in your data set there is one person who is kind of unique, then it's very easy to find out who that person is. And K-anonymity means that there are at least K individuals who share a set of attributes. Now, if you try to look at a data set and you record it street-wise, the aggregation level is very low. If you increase it to a block-wise, if you increase it to a district level or a city level or a state level, if you increase the aggregate level, obviously the anonymity level increases. So Latanya Sweeney, she highlighted that concept that there should not, the level of aggregation should not be too low. The level of aggregation should be kept a little high so that anonymity can be maintained. RRT models have been used in many studies. There was a famous study in 2009 in Germany where the whole thesis was that more educated people are more tolerant of immigrants. Less educated people are less tolerant. And when the study was conducted without RRT, that is directly asking that question, 75% of the more educated people said that we don't have a problem with foreigners. And among the less educated, the number was 55%. Therefore, the direction of the thesis was correct. That is, more educated people are more tolerant. But when the same study was repeated using RRT, the 75% actually became 53%, and the 55% became about 23. So the direction is still correct, but the data were less glorified, meaning more educated people, yes, they are more tolerant, but the level was nowhere near like 75%. There was a paper in 2006 about illegal drug use by athletes, and without RRT, the prevalence of drug use by athletes was reported to be about 1%. With RRT, the prevalence was found to be about 8%. Some of my students have implemented RRT models on our campus, trying to find out kind of commonly present things among college students. Sexually transmitted disease is kind of a common thing that happens here. Typical response rate of people having STD is somewhere like around 15%. And Deep South, coming from Bible Belt area, I think people take these things a bit more seriously. On our campus, with RRT, without RRT, only about 2% of the students admitted that yes, they have been diagnosed with a sexually transmitted disease. And when the same thing was repeated anonymously, that is, you fill out a survey, drop in a box, and go away, I think the number was close to 6 or 7%. With RRT, we were able to estimate it at about 4%. So again, the point is that touchy questions, if you ask face-to-face, people don't admit to that bad behavior. But through RRT, you are able to recover quite a bit of the lost truth. Now, there are two different types of RRT that I talked about depending on the nature of the response. For example, I could ask a question, have you done drugs? Yes or no. how many times have you done drugs, that becomes a quantitative response. It could be 0, 1, 2, 3, whatever many. So that's one thing that we need to be aware of. Part of my talk will be on binary response. Part of my talk will be on quantitative response. The other classification of RRT models is you could call a model to be a full RRT or partial RRT or optional RRT. Now, the full RRT is where everybody gives you a scrambled response, and the original paper of Warren in 1965 and then the quantitative model of 71, they were all full RRT, and so was the Greenberg work. Partial RRT model is only some of the respondents provide a scrambled response, and it's done randomly. And it was a short paper by Mangathan Singh in 1990, and just the idea. But partial RRT models are not very popular, not very common. I'll show you at some stage in my presentation that the overall quality of partial RRT models is not all that great. Optional RRT models is something that we introduced in a 2002 paper, and we believe that optional RRT models are pretty efficient. And almost all of my PhD students have an element of optionality in their work, so I'll talk about that part also. Just to give you for those who are not familiar with RRT, so the Warner's original paper, 1965 paper, was that you ask questions by mixing direct and indirect version of the same question. For example, I can have a deck of cards, and I'm interested in cheating on taxes. So some of the questions, some of the cards in the deck are directly they're asking, have you cheated on the taxes? And some cards have the question that, were you honest on your taxes? So did you file an incorrect tax return or did you file a correct tax return? And again, the researcher doesn't know which card was received by the respondent. Only the respondent knows. So when the respondent says yes, we don't know whether the respondent is saying yes to this version or the respondent is saying yes to this version. So simply saying yes doesn't mean that you cheated. Maybe you are saying yes to the indirect version of the question, right? So this is how Warner worked. It's very easy to write down the probability of a yes response. If you got the direct card and you actually cheated on the taxes, well, that's one way you will say yes. Or you got the indirect card and you did not cheat. Even then, you're going to say yes. So probability of a yes response is given by this. So you don't know pi, but P is the proportion of the deck which contains the direct card. So you know P, you don't know pi. So you can figure out the estimate of pi from this. Proportion of yes responses is N1 over N. In a sample of size N, if N1 respondents said yes, well, that's your estimate of PY. So it's kind of a simple equation. Undergraduate probability courses will have Warner's model these days. After Warner's model in 1969, Greenberg came up with their model. And they did not use direct and indirect, but they used the direct version and then an unrelated question, completely unrelated. I think Greenberg's idea was that whether you ask a touchy question directly or indirectly, it's still a touchy question. People will be hesitant. They will not respond. They will not cooperate with you. So what Greenberg did was that they said that some of the people could be asked a question directly, but some could be asked a very unrelated question that, were you born in April? Now, why would anybody have any hesitancy in answering the question about April birth? So again, when somebody says yes, we don't know if the person is saying yes to beating the spouse or the person is saying yes to being born in April. So again, you can do it. I think one of the things that one of my students, an undergraduate student, Amber Young, she was from Purdue University, was doing research in our annual summer research program. And Ryan Park was a student at our university. So Amber, for the first time, she raised this concern that, Professor, you're believing that a RRT model, people have trust in it. What if people don't have trust in the RRT model? And this is a critical point, actually, in my presentation, not having trust in the RRT model. People may think that their identity could still be revealed. So what Amber did was she picked up the Greenberg model. Now, if you are getting a unrelated question, that is, were you born in April? Well, what's there to trust here? People will not lie. But if the question is, have you ever hit your spouse? Well, if you trust the RRT model with probability A, you will still say yes. But if you don't trust, you have hit your spouse, but you don't trust the model, you will flip your answer, right? And if your true answer on spouse beating was no, then there's no need for you to lie. The only problem is, the question is, have you ever hit your spouse? And the true answer is yes, right? That's where the trouble is. If you trust the model, you'll say yes. If you don't trust the model, you'll say no. Remember, this whole thing is happening in a scrambled way, and therefore the researcher doesn't know what your true story is. But it's a question of, do you believe in that theory, or you don't believe in that theory? If you believe, you be truthful. If you don't believe, you change your answer. So this was an idea thought by a undergraduate student, and the paper appeared in this journal Involve. I don't know how many of you know about this journal. It's a nice student-oriented journal. 1/3 of the authors have to be students, and it's published by the Mathematical Sciences Press at Berkeley, actually. So it's a nice journal. But look at the results these students found. Now, we ran the typical Greenberg model. If A is 1, that is, everybody trusts the model. And I started off with a true prevalence of 30%. Look at my estimate. It came out to be almost 30%. But if 10% people lie, my estimate is poor. If 20% people lie, my estimate is very bad. And look at the damage it's doing to your estimates. So you don't know that people are trusting the model or people are not trusting the model. If everybody trusts, great. If people don't trust the model, then there can be trouble. So it's an important issue to keep track of. Then last year, there was another group of students working under the same program funded by National Science Foundation. So this group of students, one was from University of Louisiana and one was from our own university. What they did was they looked at the issue of trust in the context of not just the Greenberg model like Amber had done. They wanted to look at in a kind of a mixture model. So they came up with this mixture of the binary model, Warner model, and Greenberg model. Remember, in the upper square is the Warner model, and there you have direct questions and you have indirect questions. But the lower box is Greenberg model, where you have direct questions and you have an unrelated question. So what this group of students did was that they had 3 choices in the deck of cards. Some students, some respondents are given the direct question, some are given the indirect question, and some are given the April birth question or some other unrelated question. So there are 3 options here. But then there's a layer of trust, whether the respondent trusts the model or the respondent does not trust the model. Now, if you are handed an unrelated question, there is no issue of trust. Were you born in April? Why would you lie? So the trust issue doesn't happen here. But the question of trust arises if the question is direct or if the question is indirect. If the question is direct and you indulged in that behavior, that's where there is a worry. If you believe in the model, you stay truthful. If you don't believe in the model, you flip your answer. If it's the indirect version, that is, did you cheat on the exam? Were you honest on the exam? This is if you were honest on the exam. Okay, that's the question. Now that happens with the probability 1 minus px. So if you are honest on the exam and you were honest, there's no reason to lie. But if the question was, were you honest on the exam, and the true answer is no, well, there is a reason for you to lie. So you can, if you trust the model, you'll still say no. If you don't trust the model, you'll flip your answer. So what this group of students last year did, and the paper has since appeared in Communications in Statistics, Simulation, and Computation this year, not only they merged binary models of Warner and Greenberg, they also added the layer of trust to their work. And now they have to estimate 2 things. Not only they have to estimate the proportion of people who trust the model, A, they have to estimate it. They also need to estimate pi x, that is, what's the proportion of people in the population who indulge in that kind of behavior. So as far as the trust part is concerned, that can be estimated by using question number 1 before the real survey. That is, do you trust this model or do you not trust this model, right? And it's done anonymously using RRT, Greenberg RRT, and you can estimate A using that. And then you also ask the question that have you hit your spouse? So do you have the sensitive trait? And you can again find out the probability of a yes response. And you can see how many branches go to yes. For example, here, the probability of a yes will be, well, there is a yes here, there is a yes here, and there is a yes here. So there are 3 different branches going into yes. So the probability of a yes response can be written like this, and you can estimate this. The problem now is that this A appears in the denominator and A is unknown, so I replace it by its estimate. But you can go through the usual Taylor's approximation, etc., and you can find out the properties of A hat and pi x hat, etc. So I can estimate both parameters pi x as well as A. And they also looked at the issue of privacy protection or privacy loss. Anytime you use RRT, the question is how much privacy are you offering to the respondents, or how much is the loss of privacy? And remember, as I said, if you add more noise, there is more privacy. If you add less noise, there is less privacy. In quantitative models, you estimate privacy slightly differently, but in binary models, this is how you do it. So the loss of privacy is maximum of eta 1, eta 2. Now, what is eta 1? What is eta 2? Eta 1 is that if the reported response is yes, what's the probability that the person actually has that behavior, that is hitting your spouse? So if the reported response is yes, what's the chance of S? If the reported response is no, what's the chance of S? That is, how easy is it to go from the reported response to the true characteristic of that person? So you find out these 2 probabilities, and the larger of the 2 is delta. That's the privacy loss. And these students, they proved this small little result that delta has to be at least pi x. It could be pi x or even more. So that's the privacy loss. And that leads to privacy protection, which is 1 minus delta. But they look at the privacy protection in relation to what is the max it could be. And so PP is their privacy protection. And again, the question is that there is the issue of privacy. There is the issue of efficiency and how do you merge the 2 things. And we had published a paper in 2018 where we gave this unified measure of privacy and efficiency. So these students last year, they came up with this unified measure. They essentially look at a ratio of the privacy protection and the efficiency, or the MSE. They raise it to power A and B simply because if somebody cares for privacy more than MSE, you can adjust your exponents A and B to put more weight on one, less weight on the other. And what these students did in their work, they kept both of them to be 1-1. And again, let me be clear that it doesn't have to be 1-1. You can decide how much weight do you want to put on privacy, how much weight do you want to put on MSE. Now, what value of M will be good for you? Will a large value M be good, or a small value of M will be good? And it turns out that you want privacy protection to be large and you want MSE to be small. So overall, a larger value of M will be better. And so that's the combined measure that the students proposed. Now, here are some simulation results. And the orange, the rose part or the red part is the Greenberg model, the blue part is the Warner model, and this no color model or the no color rose, these are the mixture model, right? And you will see a bunch of interesting things. Now, 1 and 2, these 2 suffixes, 1 means that the lack of trust has been accounted for, and 2, that suffix means that A is not accounted for. That is, the researcher was not even aware that some people may be lying. And so again, you don't want to go to suffix 2. Try to concentrate on suffix 1 because that's the correct one. That's where untruthfulness has been accounted for. So if you look at this, if the true response was 0.4. Now, what you see here is that all these estimates where trust or where the untruthfulness was accounted for, all these estimates are right around 4. But if you ignore it, then you can see that depending on the value of A, things could be very bad. So you need to stay with the suffix 1. Similarly, you can look at the MSE and the privacy protection and the unified measure. Now, note one thing, that when it comes to the efficiency, it turns out that the Greenberg model is the best because that's the smallest MSE. And Warner model had the largest MSE. The mixture model was somewhere in the middle. If you look at it in terms of privacy protection, Warner model had the highest privacy, mixture model was somewhere in the middle, and the Greenberg model was lowest privacy. So looking at it in terms of efficiency, it turns out that Greenberg model is best. Looking at it in terms of privacy, it turns out that Warner model is best. But when you look at this in terms of the combined measure, M1, then you can see that it's the mixture model that does better than both Greenberg as well as Warner. So the point is that if you look at these things only in terms of efficiency or only in terms of privacy, you get a distorted picture. But if you look at it in terms of a combined measure, you get a different kind of picture. Again, these students, they looked at it from a 3D graphics point of view. And look at this. The graph is actually measuring M. It's plotting M. And higher the value of M, better it is. And you can see that when A is accounted for, the lack of trust is accounted for, you can see that overall the graph is higher than this. So visually, you can see that it's good to account for that. Don't leave it hidden, because it does damage to your estimate. But the other thing is that this is the P direction, that is the direct question, and this is the Q direction, that is the indirect question. And you can see that the peak happens here, at least in this particular case. So this tells you that neither P is 0 or 1, nor Q is 0 or 1. And it suggests that a mixture model actually is going to be a better model to use rather than relying on the Greenberg model and the Warner model. Now, for many of you who are listening to this talk, you may think, well, okay, no big deal. This is simple enough. But think about it from the perspective of undergraduate students. They are the ones who are driving this research, and that's the important part here. Let me now start switching into quantitative models. Now, when you have quantitative situation, you can add a noise to the true data. You can multiply the noise, or you can use a combination of both, a multiplicative noise and additive noise. So there are different things you can do. It's very typical that you assume expected value of S to be 0. That is, on the aggregate, there is no noise. Here, you generally assume that expected value of S is 1. That means multiplicatively also, at the aggregate level, there is no noise. Individual level, there's a noise, but aggregate level, there is no noise. And this is something that uses both. There's a multiplicative noise and there's an additive noise. You will also notice that, if you take, the mean of T is 0, if you assume the variance also is 0, this becomes the additive model. Or if you assume the variance of S to be 0, it becomes the multiplicative model. I may also tell you that multiplicative models are not very common, not very much in fashion, because they do violate the person's anonymity. So, but this is a more comprehensive model. It has a additive noise to it. It has a multiplicative noise to it. Now, again, right here, many of you may already be thinking that, well, this model has more noise. Therefore, this model is going to offer more privacy. But then at the same time, the data quality will be poor, and therefore the efficiency will be poor. So again, you get into that discussion between a combination of the two. As I was saying, the multiplicative noise, we assume its mean is 1. Additive noise, its mean is 0. And you can find out the variance of Z based on this linear combination model. And if you calculate the variance, it comes out to be this. And you can see that as sigma t square goes up, this variance goes up. Therefore, things get worse as you add more and more multiplicative noise. Additive noise, this is the fact of life. The question is, what happens when you include this? Simply looking at it from the efficiency point of view, the message is don't do it. This term.
2 minutes. 2 minutes.
All right, thank you. I need to rush. So you can similarly calculate the privacy. And privacy is the distance between the reported response and the true response. And it turns out that the privacy gets better as sigma square t increases. So again, there is this struggle. I have to skip through a bunch of these things. Then there is a unified measure you can calculate. And it turns out that the value of delta goes down as sigma square t goes up. And therefore, again, the model gets better by including this multiplicative piece in this story. We also published a paper in 2018 where we talked about that overall the optional models are better than the full model, and the full RRT model is better than the partial RRT model. So we did that. Now, the batch of students who are working with me this year, one of them is from University of Washington, Seattle, and one of them is from St. Olaf College. They're looking at the same story in terms of quantitative models. And if you trust the model, you stay with less noise. If you don't trust the model, you can add more noise to the model. And again, the question is, when you do that, your privacy and your efficiency, they will take a hit. So these students, they calculate the efficiency under the two scenarios. They calculate the privacy also under the two scenarios. And it turns out that overall, adding that multiplicative noise is helpful. I'm sorry, I have to rush through this because of this whole disturbance at the beginning. Lost some time. But they came up with these simulation results. And again, based on the simulation results, where A has been accounted for. So for known values of A, you can look at one kind of a picture. If you look at it from the efficiency point of view, you get a different picture from the privacy point of view. And then you can look at it from the combined measure point of view, and you get a different picture. And different picture here means that including that multiplicative noise is a good idea. There are these basic things that it's a scientific approach. Don't get into bogus pipeline, etc. Use RRT. Dropping the name ID is not enough. You need to be careful. And respondent privacy is an important matter. You cannot disregard that. There are some of these references that we have used. And let me acknowledge my deep appreciation to the two NSF grants, a 2018 grant that led to the initial thought on lack of trust, and the ongoing grant where the students are involved in doing this work under RRT, under lack of trust models. Okay, so let me stop my talk and allow you to ask questions.
Okay. Thank you, Professor Satgupta, for giving a wonderful talk on RRT models. He has presented variations of RRT models and how to balance this privacy and efficiency in a survey, and how to measure this, the overall concept of this privacy and efficiency. So we have time for a couple of questions. Request the participants to interact with the Professor Satgupta.
I think, as I said during my presentation, what's the big deal about this talk? Big deal is not that somebody published a paper out of it and did this work. The big deal is that this is work generally headed by undergraduate students, BA, BSc students. They are the ones who are driving this work. I think that's the big deal about what I've shown you here today.
So when you consider this issue, privacy and efficiency, which one is more serious as per your thing?
I think they're both very serious. The problem is that people, at the end of the day, they are worried about the efficiency and less worried about the privacy. And the whole highlight of this talk is that if you ignore the privacy issue, your efficiency on paper may look like good efficiency, but nobody knows what the true efficiency is.
Yeah.
So we are trying to show that if privacy takes a hit, people don't trust the model. And if they don't trust the model, your estimates will be very bad. And therefore, it's important to keep a balance. It's just like when you prepare a dish at home, you need to add some salt, right?
Okay.
Now, you can add a little bit of salt or you can add a lot of salt. Now, both are bad. So I think it's just a question of having the right balance. So again, you cannot have too much privacy because then the data becomes so bad. So you need to have just enough privacy and then see how the results will come. It takes some effort. Like the very first survey you conduct may not be the best survey, but you learn from your experience and things get refined. But I cannot give you a number that this much privacy is perfect. Okay. It's kind of a subjective thing, depends on the nature of the problem. If you ask about smoking, you don't need too much privacy. If you are talking about sexual violence, you need a lot of privacy, right? So, topics which are, which have legal implications, you need more privacy. Topics which have only social implication, maybe less privacy also might work.
Okay. Any questions? If there are no questions, we thank Professor Sadgupta for his nice presentation. Okay, we will be looking to meet you here in Cochin. Okay, Professor Sadgupta.
Yes, I will definitely keep that in mind on my next visit. I may tell you that in my 35 years I've been here, this December was the first time I did not go back to India. Otherwise, every year we always go back. But because of the pandemic, we took a break this year. I hope things get better and we make a trip this next December. Well, again, thank you so much for giving me a chance to speak to your group. Bye-bye.
Thank you, Professor Sadgupta, for your excellent talk. It will be surely beneficial to our youngsters, our students, no doubt about that.
Thank you. Thank you.
I utilize this occasion to extend our gratitude to Professor Sadgupta for accepting our invitation and giving a nice talk. And also, thank you, Professor. Also, I thank Professor Sagaran for chairing this session. And when the Vinish is missing, let us move to the next session.
Okay, thank you.
Special invited session. I hope Professor Vittal and Professor Dr. Preeti Sarajot is in the group, isn't it? Yeah. Okay. Professor Dr. Preeti is a young researcher. She is very active. In fact, in the area of biostatistics, she is working in the Regional Cancer Center, Trivandrum, and her talk will also be there. And more about her will be announced in that occasion. I invite Preeti and Professor Vittal to carry over this session. Preeti, you introduce Professor Vittal and invite to hand over the to handle this session. Please.
Thank you, sir. Thank you very much.
Welcome.
Welcome, sir. Dr. Vittal, sir. Dr. P.R. Vittal was professor and head mathematics department, Vivekananda College, Chennai, and he was also a principal of Vivekananda College and visiting professor of Western California University. He studied his MSc degree course in mathematics, Chennai, during 1960 to 1961. He was awarded PhD from Math Science, Chennai, during 1976 to 1980 for his thesis on probability and statistics process. Presently, he is visiting faculty of various institutes such as Institute of Chartered Accounts of India, Institute of Financial Analysis, Chennai, Madras School of Management Science, Chennai, University of Madras, Chennai, in the Department of Statistics and Actuarial Science, also Chaitanya College, Hyderabad, etc. Presently, he is statistical analyst in a worldwide project on water and sanitation improvement project for Karnataka State, India. He has supervised many MPhil and PhD scholars and has published more than 20 papers in national and international journals. Presently, he is an advisor to a student for PhD at University of Madras Statistics Department. He has more than 20 books in his credit. He shared his research knowledge in many universities such as Stanford University, USA, Cornell University, USA, Florida University, USA, University of Georgia, University of Tennessee, West Carolina University, etc. Professor Dr. P.R. Vittal has extensive research contribution in the field of differential equation, probability and statistics, stochastic process, etc. I welcome you, sir, for this good evening for this.
Thank you very much. Now I have to chair the session, and Professor Loganathan is going to give the talk. Loganathan?
Good evening, sir.
Time. Yes, it's your time. You can start this.
How much time?
Mr. Loganathan is going to give the talk, I hope. Madam is introduced Professor Vittal. I introduced Professor Loganathan as I know. He is from Manoanmaniam University, a well-known statistician. I hope Loganathan, I now request you to give a talk. I am only a chairperson.
Thank you, sir. Thank you, Professor Vittal. Thank you, Dr. Preeti George and Professor Satish Kumar for giving me this opportunity to deliver a talk in this international webinar.
Yes, thank you. I'm going to introduce now Professor Loganathan.
May I introduce, sir?
Yes, you sure.
Dr. Loganathan is a professor in the Department of Statistics at Manoanmaniam University, Tirunelveli, India. He studied MSc degree course in statistics during 1982 to 84 at University of Madras, Chennai. He was awarded PhD degree in statistics during 1992 by Annamalai University, India, for his thesis on Bayesian estimation of parameters in finite mixture distributions. He joined Manoanmaniam University as a lecturer in Department of Statistics during October 1992. He is the Deputy Coordinator for UGC Special Assistant Program sanctioned to this department. He was supervised the thesis of 10 students for doctoral program and has published more than 50 papers, which include 30 papers in peer-reviewed international journals. He is one of the editors of the volume Current Trends in Bayesian Methodology with Application, published by CRC Press. Also, he was one of the editors for 5 volumes published by his university and 2 special volumes of an Indian journal. He has carried out research project funded by UGC New Delhi. He received Young Scientist Award of Tamil Nadu State Council for Science and Technology. Areas of his research interest include Bayesian estimation, acceptance sampling, and clustering. I welcome you, sir, for this event.
Thank you for your good words, Madam Preeti George, and thank you, Professor Vittal, for chairing this session. Let me share my screen.
Is the screen visible?
Yeah, it is visible.
Visible.
Well, this is the title of my talk. Design. Am I audible?
Yes.
Well, this is the title of my talk, Design and Evaluation of Life Test Based Multiple Dependent State Repetitive Group Sampling Plans for Exponentiated Rayleigh Distribution. This is one of the research works carried out by me in collaboration of Dr. M. Gunasekharan. He was a former student of our department. Let me show a few slides initially as an introductory topic, as an introduction to my talk. Of course, this is mainly deals with the acceptance sampling plan. As all you know, the statisticians, as you know well, that acceptance sampling is a statistical methodology which provides tools to take decision on the outgoing finished products or the services, which helps to take how many products shall be sampled and how many non-conforming or failures can be permissible, and how to take a decision. The decision will be either accepting or rejecting the lot. I'm quite sure that all of you know very well about this. When suppose that the quality characteristic, the decision is taken based on the sampling inspection. We inspect each product sampled. So when the quality characteristic of the interest of the product is lifetime, then the sampling plans are termed as reliability sampling plans, and the plan designing is little bit different, quite not too much, quite a little bit different from other sampling plan designing procedures. And the sampling inspection, in the case of reliability sampling plans, implementation of the reliability sampling plans, the sampling inspection is carried out by conducting a life test. And when the products have a lengthy lifetime, then in order to reduce the time and cost of inspection, some censoring schemes are applied. Many censoring schemes are available. Of course, in the morning also, some speakers were telling about the censoring schemes. One among them is this life test under type 1 hybrid censoring scheme. If suppose there are n items which are taken for the life test, then the life test is conducted with the prescription of two things. One is the number of failures, say C, and the test termination time, say T. And the test is conducted till the occurrence of the Cth failure, or at time T, or before time T, or when C failures, when less than C failures occur before time T, terminate the life test. Or if the number of failures exceed C failures before time T, then the life test terminates, right? These are some of the early attempts on the designing of the reliability sampling plans that dates back to the publication in the Journal of American Statistical Association and the Annals of Mathematical Statistics by Epstein. They carried out the exercise of designing the reliability sampling plans for exponential distribution for under type 1, assuming that the life test is conducted under type 2 censoring and under type 1 hybrid censoring. The objective of this present talk is because since different kind of sampling procedures are applied and different kinds of lifetime distributions are considered, and with different censoring schemes, then new results, new research works are required. In that respect, this talk focuses on designing the multiple dependent state repetitive group reliability sampling plans. It's a lengthy title. Hereafter, let me call this as MDSRG sampling plan. And the lifetime distribution is exponentiated Rayleigh distribution. And the censoring scheme is type 1 hybrid censoring. Now I have to tell something about the exponentiated Rayleigh distribution, and I must tell something about the multiple dependent state repetitive group sampling plan individually, and then let us blend these two topics and the final results. So the organization of this talk goes like this. Initially, some slides, I'll share the ideas of exponentiated Rayleigh distribution, its properties, and its reliability characteristics. In next few slides, in few slides, let us see what is the multiple dependent state repetitive group sampling plan, because MDSRGS has been discussed not more than a decade, in the last decade only. So let us have the definition of this MDSRGS as well as its operating procedure. Then how to calculate the operating characteristic function of multiple dependent state repetitive group sampling plan under the conditions that the lifetime follows the exponentiated Rayleigh distribution, and what are the properties of that operating characteristic function. So these are the initial things which are required before determining the sampling plans. Determination of sampling plans are nothing but the determination of the plan parameters which help us to carry out the sampling inspection. That's it. So then let us switch over to the plan designing algorithm, and then how far this MDSRGS new plan are efficient over the already existing reliability single sampling plans. So these are the in this way I have organized my talk, the rest part of my talk. The exponential Rayleigh distribution, the probability density, is this visible, the expressions?
Yeah, Professor. You can make it full screen if needed.
Yes.
It is visible.
I know.
But
this is the probability density function of the exponentiated Rayleigh distribution and the cumulative distribution function. You can see closely that the term and the cumulative distribution function of this exponential Rayleigh distribution under this power theta, the term 1 minus e raised to the power minus half of t over lambda whole square. It is nothing but the cumulative distribution function of our usual Rayleigh distribution with the parameter lambda. And the cumulative distribution function is exponentiated with additional parameter theta that yields the exponentiated Rayleigh distribution. Not only the exponentiated Rayleigh distribution, all the exponential models initially are developed on exponentiating the corresponding cumulative distribution functions. And the differentiation of this yields the probability density function that is given at the first expression over small f. There are two parameters. You can very well see that when you put theta is equal to 1, you will get back your usual Rayleigh distribution. By mistake, I have typed it as theta. Of course, this is the Rayleigh of lambda only. When theta is equal to 1, it shall be t follows Rayleigh of lambda only.
Loganathan, sir.
Yes.
Sir. Loganathan, sir.
Yes, sir.
Sir. Put it in presentation mode.
Okay.
Right side, it is enough.
So it is visible, Professor. So we can make it full screen if you need it.
Click the third button. Third.
Is this visible now?
It is visible, sir. It should click the third one. Third one is the present. Yeah, that.
Is it all right? Hello?
It is not coming.
Doesn't it come? Is it not coming?
Still, it's not coming. Maybe that.
The second one, from current slide. Yeah.
Is this visible in full screen now?
You just shift F, just shift button F. F1, F5, F5.
No, shift F5.
Yeah.
Function F5.
Shift F5. Not coming. That also not coming.
For me, it is coming.
Okay.
Is it?
In the bottom there is a small cup. You can just.
Yes, that is also I am trying.
Okay.
No, it comes in my screen.
Okay.
Is it?
It is visible, person. You can continue in that way.
No. It should be comfortable to the others also.
Yeah. A slight. Whether the second.
Rosen, is this visible now in full screen?
Professor Gede.
It's not coming. Full screen is not coming. It's okay, sir. It is manageable. No problem.
I don't know where I am going wrong. Of course, it is in full screen for me.
Oh, it is full screen, Professor. Yeah, but
Is
it is visible. Yeah, it is not. It is visible, here, but it is not full screen here. Here, the left portion there are small slides and that indicating. Yeah, shift F. It's better to once again share. Now it is come, yeah. Now it is fine, Professor.
Yeah, now it is coming.
Yeah, it's fine. Oh, please. It's gone away.
Again,
You click the stop sharing.
Yes.
Yeah.
Is it okay now? Hello, Professor.
Yeah. Once again, you share. Please share.
Technical difficulties.
Please share in the same way as you did just before. Yeah. It is fine. It's fine for us. Now it is fine.
I am very sorry. I feel very sorry that. Pardon me for this technical difficulties. Because okay, right. I'm sorry. I have taken some more minutes. This is the slide which shows the behavior of the probability density function. You can see that when the values of lambda, of course, lambda value is fixed at 0.5, and when you vary the values of theta, for lower values of theta, the curve of the probability density function has the very sharp declining tendency. When the value of lambda gradually increases, of course, the probability density function rises up, and then it goes down, having a long tail. So these are some of the properties that I want to mention, because for designing the reliability sampling plans, we want the mean of the lifetime distribution, to calculate the mean lifetime. But in the case of exponentiated Rayleigh distribution, the mean does not exist. You can see that the two expressions, that expected value of the second order non-central moment, and the fourth order non-central moment are functions of the digamma function. They are calculated based on the evaluation of the digamma function and the first order polygamma function. So mean does not exist. And this I want to show that the median lifetime of the exponentiated Rayleigh distribution, median, exists for the exponentiated Rayleigh distribution. This is the one we are going to use for designing the sampling plan for under the conditions of the exponentiated Rayleigh distribution. So this is the expression of the reliability function calculated for the exponentiated Rayleigh distribution, and the reliability functions have this declining tendency, and the hazard functions have this shapes, and here the values of theta are varied from 0.3 to 5, and two different shapes of the curves we got for the hazard function. I do not have much about this to speak about. Of course, now let us switch over to the sampling procedure which we are going to adopt for designing the sampling plan. Multiple dependent state MDSR GS plan is defined by a set of five elements. The first one is the sample size n, and the next two elements are the acceptance numbers. The next one is an integer that represents the number of preceding lots, and the last one denotes the test termination time. There is a very good difference between the other sampling plans with the multiple dependent state repetitive group sampling plans. The element k that helps to keep in record of the preceding lots, keep in record of the information about the preceding lots to take decision about the current lot. Let me come from the first step. Based on the sample size, so we draw a set of n items randomly, then we conduct the live test usual and observe the number of values correctly. Then we have three decisions. The first decision is if when the number of failures is less than or equal to the first acceptance number C1, then we will accept the current lot and the test will be terminated. If the number of failures is more than the second acceptance number, naturally C1 will be less than C2. When the number of failures is more than C2, then we reject the current lot at time t or earlier. That's it. On the other hand, if suppose the number of failures is more than C1, but it is less than or up to C2 at time t, then we look at the record of the k preceding lots. Based on the k, if suppose k is equal to 2, then we look at the results of decisions taken upon the two preceding lots. Here k preceding lots. If those k preceding lots were also accepted under the same conditions of the present acceptance condition, that is x less than or equal to C1, then we will accept the lot. In all other conditions or otherwise, we will repeat the step 1. We will go back to drawing the next set of items, sample them and conduct the live test and keep repeating it. So there are three steps in which we have the state of taking the decision upon the lots. 1, accept the current lot. Next, reject the current lot, or accept the current lot based on a condition, or otherwise repeat the sampling procedure. So probability or the operating characteristic function is a tool which helps to discriminate the behavior of a sampling plan. In order to calculate the operating characteristic, of course, all you know that the operating characteristic function is nothing but probability for accepting the lot. But here you can see that at two stages, we have the chances for accepting the lot. One, at the number of failures is less than or equal to C1. Second one, if C less than or C is C, if number of failures lies between C1 and less than or equal to C2, and all the preceding K lots were accepted under the condition that X less than or equal to C1. So these are the two situations in which we have the chance for accepting the current lot. So taking into the consideration of this, we have to calculate these probabilities. The first stage of acceptance, when X less than or equal to C1, first stage of decision, when X less than or equal to C1, and plus probability of C1 less than X less than or equal to C2, multiplied with K times of probability of X less than or equal to C1 raised to K. The last term represents the probability for accepting the K preceding lots under the condition that the number of values in each of the preceding lot sampling inspection carried out for the K preceding lots are less than or equal to C1. Then the probability for rejecting the lot is P2. Of course, we do not have any work on this. And the probability for repetition of sampling is nothing but this one, P3. That probability of C1 less than X less than or equal to C2. This is for the third stage. And for repetition of sampling, when any one or all of the K preceding lots were rejected, there is 1 minus probability of X less than or equal to C1 raised to the power K. This is the probability for repetition of sampling. Here we have this P1 and P3. These are the two probabilities which we will consider for calculating the probability for lot acceptance under MDSRGS plan. So this is the operating characteristic function of MDSRGS plan for not only for exponentiated Rayleigh distribution, for any other lifetime distribution. The operating characteristic function of MDSRGS plan is defined by this P1 over 1 minus P3. So then the next expression is obtained just by substitution of the terms P1 and P3. And here, the calculation of this lot acceptance probability, P of P, requires the knowledge of the distribution of the number of failures. The number of failures may follow the hypergeometric distribution when the lot size is small, or otherwise you can use binomial probabilities or pass-on probabilities under respective conditions. Here, for the purpose of explaining, here I consider the binomial probabilities. So the probability of X less than or equal to C1 is, of course, the cumulative binomial probability. Here we have the presence of the term P. P is nothing but probability for an item to be good. Now here P is in terms of acceptance sampling, we call P as lot fraction defective. How to calculate this P, lot fraction defective? Here we want the knowledge of the lifetime distribution. This capital F of T over M is equal to P is the equation which helps us to calculate the value of P. For every given, this left side of the last equation is nothing but the cumulative distribution function of exponentiated Rayleigh distribution. There, instead of T, here it is the cumulative distribution function is expressed by means of T over M, not T given M, it is T divided by M. T is the time, and M is the median lifetime. On solving this equation for every given value of M, T will be fixed test termination time. M for every given value of M, we have to solve this equation to calculate the lot fraction defective. With the knowledge of the lot fraction defective, we can calculate this this probability, the operating characteristic function. So the operating characteristic function calculation involves the calculation of these probabilities, for which we have to use this binomial probabilities, knowledge of binomial probabilities. And to calculate this binomial probabilities, we have to use we have to calculate the lot fraction non-conforming on solving this equation. So properties, the operating characteristic properties will help us whenever we discuss a new methodology, acceptance sampling methodology or acceptance sampling plan. We must also take into account of studying the properties of the corresponding operating characteristic function, because that is the statistical tool which helps us to discriminate the performance of one sampling plan from all other sampling plans. Here, the sampling plan is ruled by the 5 sets of values: the sample size, 2 acceptance numbers, and the value of k. Of course, test termination time, here the value of theta. Because the theta also has a knowledge, it also has an influence upon the value of the value of the cumulative distribution function. At first, the behavior of the operating characteristic function shall be of this case, that it should have a bulge at the top and it should have the declining tendency, and it goes on. It is not the ideal shape, but it is the desirable shape of the operating characteristic function curve. This explains that at lower values of p, here you may note that usually the operating characteristic function curve will be drawn taking the value of p along the x-axis and the operating characteristic function values along the y-axis. Here we calculate, we represent the x-axis by the values of t over m, and we have a close relationship between t over m with p. With the previous equation, f of t over m is equal to p, and based on that you can understand that whenever the t over m increases, then the value of p is also increasing. When the value of p increases, then the operating characteristic function decreases. It's a good sign for any desirable sampling plan, because this represents that the good quality lots, that means the values located under the initial stage of at the beginning of this x-axis, has larger probability for acceptance, and it gradually goes down, and the larger values of t over m, we have smaller chance for accepting the lot. It's a good behavior and it is a preferable one. So the operating characteristic function of the present MDS or GS also has such kind of a behavior, and the operating characteristic function behavior based on the changes in the values of n. For fixing the values of all other 4 characteristics, C1, C2, K, and theta, we have changed the values of this n for 4 different values are taken for n, 25, 50, 75, 100. And this gives us 4 different sampling plans. For each of them, we have drawn the operating characteristic function, and they also have the same declining tendency. But at the same time, we can notice that what is the behavior of the operating characteristic function corresponding to the changes in the values of this n. The blue line with the dots correspond to the smaller sample size. Dark blue line represents the sampling plan corresponding to the larger sample size. At any fixed value of t over n, we can notice that the value of p keeps increasing when the value of n is decreasing. When you look at this case, when you look at this point, just when the value of t over m is located here, by drawing a perpendicular line, we can see that the value of p is small at a lower value of n, that is 100, and keeps increasing, and it reaches its larger value corresponding to the smaller value of this n. That is what the property I mean to say, that p is a decreasing function of sample size n. Naturally, when the sample size keeps increasing, definitely there will be a lesser chance for accepting the lots, because more number of failures will be included. That's it. And the properties of the acceptance number, instead of 1 acceptance number, here we have 2 acceptance numbers, and the behavior of the operating characteristic function is displayed in these 2 graphs. In the first graph, the values of C2 is fixed, the value of C1 is varying. And in the second graph, the value of C1 is fixed at 0, the value of C2 is varied from 2 to 8. In both the cases, we have the similar kind of the behavior of the operating characteristic function. Means the larger acceptance numbers lead to producer-oriented plans because the good lots have larger probabilities for acceptance. Smaller acceptance numbers correspond to consumer-oriented plans because we have lesser chance for accepting the lots. So this is what the behavior of the operating characteristic function based on the change of the acceptance numbers.
Time is already over.
Oh,
time.
Right, sir. I think I have taken some time for technical difficulties. Will you bear with me for a few more minutes?
Few more minutes depends upon our organizing committee, because one more talk is to be there.
Yes, I understand. Sir.
Right.
Well, now I come to this point that the designing of the MDSRGS plan is of this one, that here, since we have the chances for repetition of sampling, then the question of average sample number comes into the picture, and the average sample number is calculated at two different values of the lot fraction defective at AQL as well as LQL, and some of them, half of their sum is the actual acceptance sample average sample number, and the problem of designing of the plan parameters or determination of the plan parameters is of minimizing the average sample number subject to these two conditions. These two conditions are the regular conditions, which represents the satisfaction of the producer's risk as well as the consumer's risk, and these two are the points P of P1 and alpha, P of P1 and 1 minus alpha, P of P2 and beta are the 2 points lying on the operating characteristic curve. So any plan which is obtained on satisfying this optimization problem will pass through those 2 points, which assures that the producer and the consumer's risk, producer and consumer's risk will be at the prefixed levels. So this is the algorithm, and on applying that algorithm, we have found that for this given specifications, that median lifetime at the producer's expected value is 1,700 hours, and the median lifetime of the consumer is at 800 hours, and test termination time is fixed at 450 hours. Producer's risk is 5%, consumer's risk is 10%. We found that on applying the algorithm, the MDSRGS plan parameters are obtained like this. And how to implement this, that according to this plan, we have to conduct a live test on selecting 24 products randomly, and we should perform the live test with the test termination time 450 hours. Before 450 hours, if no failure occurs, then we accept the lot. And before 50 hours, if a second failure occurs, then we reject the lot. In other case, when the number of failure is 1, then we look at the 2 preceding lots, the decisions taken on the 2 preceding lots. If the 2 preceding lots were accepted with no failures subject to this condition, then we will also accept the current lot. And the corresponding average sample number in this case is 27. Of course, I have some results to say that why should we prefer the MDSRGS plan? Because it has a sample size efficiency. For the same set of producer's risk, consumer's risk, and M1 and M2, for 5 different plans were generated. In all the 5 cases, we can see that the MDSRGS plan requires less number of products to be sampled in all the 5 cases. And not only that, we should also look into that the risk efficiency of the plan, for which we calculated the producer's risk and consumer's risk, actual producer's risk and consumer's risk under relevant single sampling plan and MDSRGS plans. In both the cases, we have an advantage of applying the MDSRGS plans because it provides, it reduces 1.75% of producer's risk and 0.35% of consumer's risk, and in total 2.1% of total sampling risk. So in all this situation, in combining all these things, what I am trying to say is, when there is an opportunity to design MDSRGS plans for conducting the live test under the conditions that the lifetime is distributed according to exponentiated Rayleigh distribution, definitely that will provide a sampling plan with lesser sample size, with more efficiency in the point of producers risk and consumers risk. So these are some of the references. This is not exhaustive. These are some of the references related to multiple dependent state repetitive growth sampling plans. These include both attribute sampling plans as well as variable sampling plans. I'm sorry, I have taken much of your time. Thank you.
Thank you, Mr. Loganathan. But I have only one question regarding that. In calculating the number of failures of the system,
yes,
you said that hypergeometric distribution could be applied, but you have presented the probabilities with the binomial. You have an extension results using hypergeometric distribution too.
Yes, sir. We have worked for hypergeometric distributions as well as pass-on probabilities also. Presently, for the case of
very good.
describing
It will be quite interesting.
Binomial.
Good. Fine. Is there any question for just one or two questions we can allow? Because the other topic we have to go through. In the absence of no question, we congratulate and thank Professor Loganathan for a wonderful talk here. It's a very informative talk. People always contact Professor Loganathan, and his email ID might be available in your list. Thank you, Professor Loganathan, for extensive talk that you have given.
Thank you, Professor Rovital, and the co-chair, Dr. Preeti George, and Professor Satish Kumar and his colleagues, and the other co-organizers for giving me this opportunity.
May I ask you one question?
Thank you. Thank you.
Preeti, madam, there is one more talk, I think. Mr. Sridharan?
I have one. Question.
Hello, sir. May I introduce J. Srikumar?
Yes.
Dr. J. Srikumar is working as a principal scientist at ICAR.
Sridharan, who is the next speaker?
Dr. J. Srikumar.
I have one.
Correct. Thank you.
Dr. J. Srikumar is working as a principal scientist at ICAR Central Tuber Crops Research Institute, Trivandrum, Kerala. He did his MSc in Agriculture Statistics from ICAR Indian Agriculture Research Institute, IARI, New Delhi, and PhD in Statistics from Mahatma Gandhi University, Kottayam. He has got postdoctoral work experience in bioinformatics sector, plant research international from Netherlands. His main research interests are statistical genetics, genomics, bioinformatics, and computational biology. Dr. J. Srikumar has extensive research contribution in the field of agricultural statistics in general and application of statistics and machine learning techniques in predicting protein interaction using multiple sequence alignment and in gene interaction network prediction using gene expression data. He has handled various research projects with grants received from Department of Biotechnology, Ministry of Electronics and Information Technology, etc. He published many research articles in national and international journals of repute. He has collaboration with the RGCB, ISA, Trivandrum as guest faculty and research guide of MSc Biotechnology students at Kerala Agriculture University, Vellani. He has guided more than 15 MSc Bioinformatics. Welcome, Dr. J. Srikumar to this event.
Yes, Professor Srikumar.
Thank you, Doctor.
Extensive biodata.
Thank you, Dr.
We are happy. We are very anxious to listen to your talk and hope we will be benefited very much by your talk. We request Mr. Srikumar to start his talk.
Is it okay?
Yes.
So first of all, let me thank the organizers, Dr. Satish Kumar sir, and our chairman, Dr. Vittal sir, and the co-chair and my friend, Dr. Preeti Saraj, for giving me an opportunity to present this topic in this National Statistics Day seminar. As every year, this July 29th is celebrated as the National Statistics Day. And this year, as every year, there is a particular theme. And this year theme is the Sustainable Development Goal SDG 2 of end hunger, achieve food security, and improve nutrition and promote sustainable agriculture. So this genomics plays a crucial role to develop nutritionally important stress-tolerant varieties of any crop and to achieve this SDG2 goal. So this related to genomics, I tried to make a topic, and my topic is big data analysis in genomics in the perspective of deep learning and AI solutions. So statisticians, it is a game between the human and nature through data. And the statisticians are expert in producing useful data, survey sampling, experimental designs, etc. And they are experts in analyzing data to make meaningful results by statistical inference and methods and drawing practical conclusions. And in the big data era, is a time for data sets that are so large, complex, that traditional data processing applications are inadequate. The challenges include when the data size become increased, huge. The challenges include analysis, capture, data curation, search, sharing, storage, transfer, visualization, querying, and information privacy. This term often refers to the use of predictive analysis or certain other advanced methods to extract value from data. So when there are more confident decision making, then we can give results in greater operational efficiency and cost reduction and reduce risk when the accuracy of the big data is increasing. So big data affects academic and applied research in many domains, include machine translation, speech recognition, robotics, the biological sciences, agriculture science, medical informatics, etc. So this data science is an integral part of the competitive intelligence, and this is a newly emerging field, and the statisticians play a crucial role in the big data era. Because the data structure is changed here, the data is not more structured data. So usually it is coming as unstructured data. So there are when big data means there are big noises. So statisticians, including some, we nowadays we say that a data scientist who is better in statistics than any software engineer and better at the software engineering than any statistician. So this data scientist is becoming they play a crucial role to analyze this big data. So this big data problems usually it is tackled by multidisciplinary teams. There will be domain experts, computation experts, and machine learning experts and statisticians. So statisticians can find structuring the data and facilitate statistical modeling for big data analysis. So in genomics, especially the promise of utilizing big data to capture and unlock its full potential is exciting. And in the genomics, and when the big data and the genomics is intersect, there are new challenges emerges. So in genomics, make a lot of promises in life sciences, precision medicine, and healthcare. The current way of analyzing genomics suffer from the curse of dimensionality. When the data size is huge, but the number of samples the sample size is becoming very low. So to apply statistical procedures which is suffers from the cost of dimensionality. There are areas like single cell omics and microstructure imaging. big data are coming, which needs to be analyzed by machine learning or deep learning techniques. This is the workflow of an integrated omics, where genotype, in the case of a plant, this can be one plant. If it is a human, this is one individual. So different type of data like genomics, transcriptomics, this is at the gene level, and this is at the protein level, and this is at the metabolomics level. Though this type of huge data set is available now, the data is becoming cheaper and cheaper, and that is why there is a need to develop more sophisticated computational techniques to deal with the data. Their statistical approaches are playing an important role, and statistical approaches, machine learning, deep learning, etc., is needed to analyze this data and to draw conclusions and how these genes or proteins or how these metabolomics are interacting to bring a particular phenotype. Or in the case of plants, whether the plant is having high yield or whether the plant is resistant to diseases. So that type of, to get a meaningful analysis, statistical and machine learning approaches are necessary. So these are the different fields of when we were thinking of, when we are saying of genomics or system biology in agriculture or crop improvement. There are many fields like agriculture, biotechnology. These are the domain experts, and this is the theory, biological networks. So in this network area, statisticians and computational scientists can play a role. And the modeling, visualization, pathway analysis, the topological or graph, topological analysis, the simulations that the statisticians play a very role and very important role. So in the system biology or agriculture crop improvement based on genomics, statisticians is having a very important role. For example, if we have a germplasm collections, its phenotype. Its phenotype depends on the genotype into environment interactions, or its that loci, that the gene, which genes are there in that particular genotype. So in the genomics, the data is coming as sequences, and we have to use that sequences or markers to predict, or genomic selection to predict good individual or good genotype. That big data is analyzed by machine learning models, where the training and computational models are used, and this information is used for precision breeding. For example, this is a sequence data with that individual is having some molecular phenotypes, and this data is first we have to give that data quality check, and we have to curate the data. Then we have to apply some models. Then to apply that models, we have to divide the data into training and test data set. And the training data set, we are applying that models. And these models, then it is evaluated, and the best model, regression model, or any prediction models is used for predicting the genotype or phenotype, and that is used for interpreting. So in the workflow of deep learning in genomics, there are many processes like pre-processing of the target variables, model building and training, model evaluation, and interpretation of the data. So there are many tools. I am just showing one example, that is one package in Python. So there are many tools available in Python, R, etc., to deal with these large data sets and to apply this deep learning or machine learning techniques. So this Django is a Python package that facilitates deep learning in genomics. So the data sets in the different format, like sequence, that alphabetic A, T, G, C sequence data sets. So it has to be normalized. Then we have to apply some machine learning techniques. So in Python, there are keras and scikit-learn packages are available to apply that particular machine learning techniques or machine learning or deep learning techniques. And then we have to predict that in the case of crop improvement or to apply in the plant breeding, we have to find out the particular genes which are, whether it is there in that particular progenies to be selected. So that type of prediction models are developed. There are many thorough statistics procedures are available previously using mixed models, etc. And that linear models are available, but this deep learning is helpful for extracting the nonlinear effect of that particular data also. So this is one example where we have what that machine learning tools for finding out the plant protein with its a pathogen protein interaction. So we are having that host plant proteins sequences and Phytophthora that is the pathogen protein sequences. We are extracting the features from this.
Are you continuing?
Hello, Dr. Srikumar.
So Srikumar, are you continuing? Professor Srikumar.
There may be network issues probably. That's. Hello.
Hello, Mr. Srikumar.
I shall call him. Okay, this. Yeah, network problem. We left. We will join.
So we have to thank him for the work that he has done. Correct?
Let us. Let us wait one or two minutes, person.
Fine, sure. Thank you. We can.
മോനെ ഫോണിൽ എങ്ങനെ വിളിക്കുന്നു മോളി തുടങ്ങി ചോദിച്ചു.
Is there any network problem from Professor Srikumar's side?
Yeah, I think so, Professor. I shall try to call him via mobile.
Fine.
I shall try to call him.
कृपया कुछ समय पश्चात प्रयास करें. The number you have dialed is currently busy. Please try later.
Probably he will be trying to join. Otherwise, he is not taking the phone since he is in the.
Oh, it's a probably network, but a fail in his case.
Yeah, yeah. Since we have up to the next talk is at 6:30, so that by that time it can.
Another 6 minutes over to be there.
Yeah.
Ashish Gupta.
By the time, I think
we can close the session and the next session being started.
No, Professor, just we can wait because there is some more time for the next session.
Oh, I see.
Professor Gedde has some, I think he is raising whether Professor Gedde. Do you have anything to ask Loknath? Professor Loknath?
I think Lognathan sir is not online.
Okay, okay. Oh, he left. Okay.
Yeah.
The topic was quite interesting, especially genomics, big data.
Okay.
Somebody would be interested to connect with the data analytics on business forum. So very promising topic. A lot of information he might have connected. Unfortunately, this network problem comes everywhere.
Yeah.
So he started very nicely on genomics data.
Yeah, Professor. Yeah.
Quite interesting to see how the big data is going to be connected with the analytics.
Yeah.
Many such problems occur in other disciplines, especially in business. People who are interested in insurance might have connected this problem to analysis.
Yeah. You are also associated with such some works.
Yes.
Some financial, yeah, insurance and.
Yes, I'm associated with the Actuary Society.
Yeah. How is the actuarial, that course is running now also in the Madras University?
Yes, yes. See, Madras University is running this course, and these Madras universities offer a MS program in actuarial science, but
Okay.
actually they follow the syllabus of the Society of Actuaries Society of India or even the Britain. They can take any one of these two exams. The
Yeah.
tougher examination, there are very good prospects for students to pursue actuarial science, especially during the coronavirus or flood relief and all that, Innovative data could be analyzed there.
Yeah.
Many of our students are doing promising work, especially in the financial, Cholamandalam, other financial institutions, Sriram Transport, like that.
Yeah. Hi, Professor.
Yeah, thank you very much, Mr. Sandosh. Preeti George, you have too much talked about me, I doubt whether I deserve for that. Very good. Mr. Sri Kumar has now joined. The time is
I think
almost
you can.
over. Sri Kumar is going to continue his work.
I think we can give 5 minutes to conclude.
Sure.
Yeah.
Professor
So
Sri
that
Kumar.
we can find some other occasion to have his elaborate talk.
Correct.
Dr. Sri Kumar, is it?
Not audible, probably appears as if he's speaking, but it is not audible to us.
Yeah.
Srimad sir, you are muted. Please unmute.
Okay. So I presented earlier, but it was not visible.
Yeah, it was not.
Definitely, you have to share it once again. Yeah.
Oh, you presented that. You see, we thought that some network problem might occur.
I presented everything, sir. I thought it was audible.
I see. You presented it. So, in the absence of that, Professor Satish Kumar, shall we thank Professor Sri Kumar for doing the work. So, sometimes we can, unfortunate enough, not to see the real work, what he has done, because we are unable to see what we have presented after some time. You see, first few slides we were able to see. I was going on this genomic data. I was interested to see how it could be connected with the financial analytics. Very good. Anyhow, the bird's eye view of the topic we are able to see. Shall we close the session?
Okay, Professor. Then let us close.
Thank you, sir. Thank you.
Okay.
We thanks Professor Sri Kumar for presenting this topic. The initial was very, very nice. It was giving more enthusiasm for us to proceed, how it could be interrelated to the other discipline. Unfortunately, some network problem might have come. I don't know. We're unable to see that. I hope
I was thinking that everything is going correct, and I was presenting at the up to the end.
I see.
You have the network issues. Yeah.
Maybe.
Anyway, let us move to the next session.
Okay, sir. Thank you.
Yeah.
So,
First
thank you
of all,
especially, yes. Come on.
I utilize this occasion to thank both the speakers, Professor Loganathan and Professor Sri Kumar, for your nice presentations, and also our Professor Vital for nicely chairing the session and supporting by the co-chair, Dr. Preeti Sarah George. We extend our gratitude and thanks to each of you.
Thank you. Thank you.
Yeah, thank you all. Thank you.
Thank you very much. Thank you.
Thank you. Thank you so much. Now, let us move to the next session. I think we are. What about our speaker is Thomas Matthew, Professor Thomas Matthew. Yeah, he's also here in the group.
Yes, I'm here.
Yeah, yeah, Professor. Okay, to chair this session, our great professor.
I'm here.
Thomas sir is here, and to support him, our own alumni and is a biostatistician, statistics professor, associate professor Jagannath Krishnan of Regional Cancer Center is here. I invite Jagannathan is very active person, young researcher. Jagannath, you please carry over the session to and introduce our Yagin Professor before this gathering, and thereby continue the hand over the mic to Yagin sir.
Thank you. Thank you, sir. So good evening to one and all. Welcome to the technical section 8 and the plenary section 4. So now we will be having the plenary session to honor Professor R. Krishna Pillai, former professor and head Department of Statistics, University of Kerala. And also it is my pleasure to co-chair with my teacher, Professor Yagin sir, in this special occasion. And he is a former professor and head Department of Statistics, University of Kerala, and emeritus scientist under the Kerala State Council for Science, Technology and Engineering. He's a great teacher and a great researcher with more than 90 publications and had produced more than 10 PhDs. His research covers order statistics, record values, estimation techniques, rank set sampling, concomitant of order statistics, and so on. And may I now request you, sir, to chair the session and say a few words about Professor R. Krishna Pillai, and then to introduce our speaker, Professor Thomas Matthew. Thank you, sir. Over to you, sir.
Thank you, Jagannath Krishna, for the introduction regarding me. And I am happy to be here and say good evening to all my friends who are attending the 8th session of the 5th International Webinar on Statistical Theory and Applications. And I am happy that this is our I was a very good entertaining teacher, and his teaching skills are very known. And he headed this department for some time, and he then moved to Botswana University and still had good contacts with this department and contributed much for the development of this Department of Statistics. So on this occasion, I pay my respect to Professor Krishna Pillai, and now we move on to this particular session. And I am very happy to notice that this is a session with an important speaker, world-renowned statistician, Professor Thomas Matthew of Maryland University, USA. There are a lot of things that I can speak about Professor Thomas Matthew, but because of time constraint, I am limiting. His areas of interest are statistical methodology for exposure data, calibration problems and tolerance regions, inference in linear mixed and random models, univariate and multivariate bioequivalence testing. He is the author of 2 books, namely Statistical Tests for Mixed Linear Models and Statistical Tolerance Regions. I am happy to say that he is the alumni of this Department of Statistics, University of Kerala. And I am very happy. I invite and welcome Professor Thomas Matthew to deliver his talk on inference on drug interaction index based on binary response data. Professor Thomas Matthew, kindly take over the
session.
Thank you. I want to thank the organizers of the conference, especially Professor Satish Kumar, for inviting me and to be a part of this conference. And I also want to thank Dr. Jagannath Krishna and Professor Yagin Thomas for that nice introduction. It is actually a great privilege for me to talk in a session in honor of Professor Krishna Pillai. He was my professor, my teacher, and also the head of the department when I was a student there. This was way back in 1976 to 1978. And I also noticed that my teacher, Professor Kalyadaraman sir, is also there attending. Great privilege to have you in the audience, sir. Now, let me share the screen and start my talk. Hope all of you can see my screen.
Yeah, Professor. Yeah.
Okay. All right. Okay. Now, I'm going to talk to you about what is called the drug interaction index. Obviously, I'm going to introduce you to the topic of drug interaction. And in today's talk, I will be focusing only the case of binary response data. So this is an outline of what I plan to speak. I will use an example to introduce you to the concept of the interaction index, which is a parameter. And the problem I want to address is the computation of a confidence interval for this parameter. And this confidence interval will be computed using the concept of what is called fiducial inference. I will explain that to you. Fiducial inference actually goes all the way back to R.A. Fisher, but recently there is a revival in interest regarding fiducial inference, and now the theory is much better understood. And with the current computing facility, fiducial inference can now be implemented. I will briefly explain all of that within the given time, but my focus will be on the drug interaction index. Fiducial inference is a topic in itself, so I will not get time to go into the details of that. So let me start with an example, a very simple example. So I took this example from this article that appeared in 2000. Basically, you are looking at two drugs. Basically, I have mentioned here two analgesic drugs. That means these are pain relievers, tramadol and acetaminophen, like Tylenol. So they are pain relievers. They can be used to relieve minor pain and ache. If you combine them, what happens? So that is the problem we are going to investigate. If you combine two pain relievers, is it better or is it worse? So this was carried out. This is an actual study. This was carried out based on data collected on male mice. So these mice, some of them received only tramadol, some of them were given only acetaminophen, and some were given both of them combined in different doses. I will show you a little bit of the data soon. And after these drugs were administered, so the mice were also injected with this chemical acetylcholine bromide. This is some type of a neurotransmitter. So what this will do, when the mice are injected with this will induce abdominal contraction. That is what this chemical is supposed to do. And if the drugs are effective, that abdominal contraction, muscle contraction will be controlled and there will not be any pain. So if the mice exhibits signs of pain, that means they had the abdominal constriction and the drugs were not effective. So this is how the study was carried out. So the mice were observed for a 10-minute period, and then the signs of pain, that means the mice will extend their limbs and they will basically bend back, arcing of the back, etc., indicating pain. So the absence of pain or the absence of constrictions means the drugs were effective. So we have binary response. Either there was pain or no pain. So the absence of constriction, indicating the absence of pain, we will label that as 1 or 0, binary response data. So each mouse was used only once. That means you have independent observations. And at each dose level or at each combination dose level, several mice were used. That means we do have several replications. So I will use M or MI to denote the number of replications, and R and RI to denote the number of positive responses. So positive response means absence of pain, absence of pain. So we have a binomial distribution. So why is that? Let us say I look at 50 mice that received a particular dose, and I count the number of mice who showed pain relief. So I'm counting this among, let us say, 50 mice. So that is why we have the binomial distribution, binary response data. So this is the setup. Now here is some data. So the full data is given in that article I cited earlier, Dawson, Carter, and Jennings. Okay, what does this data mean? To begin with, suppose we have 15 mice that received tramadol alone at dose 2 milligram. Among the 15 mice, just 3 of them showed pain relief. So probably 2 milligram is not very effective. Increase that to 6 milligram. Among 45 mice, 20 of them showed pain relief. So that means it is showing more effect. Increase it to 10 milligram. By the way, this is tramadol alone. So the second drug, acetaminophen, the dose is 0. So tramadol alone. Then you have acetaminophen alone at dose levels 30, 80, 200, and so on. Then you have combination doses, 0.5 milligram of tramadol and 50 milligram of acetaminophen. 60 mice received that, 12 of them showed pain relief, and so on. This is part of the data. So the question is, when you combine the drugs, right, instead of giving only a single drug in various doses, if you combine them, do they show interaction? So we'll clearly explain what exactly is the interaction we are talking about and how we are going to measure the interaction. But of course, the concept of interaction is understood in the usual sense, like we understand in the context of, like, for example, a two-way analysis of variance. So the same concept of interaction. So this is our problem. I have data on pain relief based on single drug and combination drug. So do the drugs interact? Okay. So let us look at single dose administrations of each drug separately. So I will denote by D1I the various dose levels of tramadol, D2J the various dose levels of acetaminophen, and X1I and X2J basically represent 0 or 1 binary response random variables. The probability of a positive response means pain relief, and that will be a function of the dose level. So we model that using logistic regression. So pi1i, this is basically the binomial probability corresponding to dose level D1I of the first drug, tramadol. And that is a function of the log dose, ln of D1I, natural log of D1I. And similarly, pi2j, the binomial probability or the success probability, as we usually call it, corresponding to the second drug dose D2J. You notice the models have a common intercept beta 0. Why is that? In the absence of, so if you don't give any of the drugs, then the situation is the same, right? So the probability of pain will be the same if no drug is given. That means it should have a common intercept. A very important point to notice here is we are not going to use any model corresponding to both drugs given together. So basically, this is what I refer to as a marginal response, not in the usual sense of a marginal distribution. That means we are modeling the probability of a positive response corresponding to the administration of a single drug only. A combination drug, the response probability, we will not be using any model. That is a very important point to remember. We do collect data corresponding to the combination dose, but we don't use any model corresponding to the for the corresponding response rate. Now, the interaction index is a parameter that will be used in order to measure whether there is interaction or not, and in what direction the interaction is. Okay, what do I mean by that is, by combining the two drugs, is it making it more effective, or are the two drugs working against each other and is not a good idea to combine? So the interaction index will tell us both. Now we are going to use a certain reference model, which I'll explain, referred to as a Loewe additivity model. This is a very popular model, very widely used for assessing drug interaction. So the model basically it's a reasonable assumption. The assumption says the following: if there is no interaction, suppose there is no interaction, then the combination dose D1, D2 will have the same effect as a dose D1 plus D2 corresponding to any single drug. Let me repeat that. If there is no interaction, then the combination dose will have the same effect. Combination dose D1, D2 will have the same effect as the dose D1 plus D2 for any single drug. This is the basic assumption referred to as a Loewe additivity model. This doesn't mean we are using a statistical model, by the way. So this particular assumption is referred to as Loewe additivity. All right. Now, suppose I look at a response rate pi. That means this is the proportion of the mice that will show a positive response. For drug 1, in order to get this positive response, suppose the dose level used is d pi 1. And for the same pi, for drug 2, suppose the dose level used is d pi 2. So d pi 1 will produce a response rate pi. D pi 2 will also produce a response rate pi for the second drug. So this means if you look at d pi 1 over d pi 2 units of drug 1, that will produce the same response rate as 1 unit of drug 2. Which means the combination dose d1, d2, this is equivalent to a dose d1 plus d2 times d pi 1 over d pi 2 units of drug 1. Okay, looks like a reasonable thing. So the combination dose d1, d2, it may not be equivalent to d1 plus d2 of drug 1 because they may interact. Even if they interact, it is reasonable to conclude that the combination d1, d2 is equivalent to d1 plus d2 times d pi 1 over d pi 2 units of drug 1. But remember, for drug 1, to get the response pi, the dose level required is d pi 1, which means this sum d1 plus d2 times d pi 1 over d pi 2 must be equal to d pi 1. So there it is. So this must be equal to d pi 1. You divide both sides with d pi 1, you get this displayed equation here. So the dose level d1 over d pi 1 plus the dose level d2 over d pi 2 must be equal to 1 in the absence of interaction. In the absence of interaction. So the quantity on the left is referred to as the interaction index. d1 over d pi 1 plus d2 over d pi 2 is referred to as the interaction index. Now, let us see what all quantities. It is an unknown parameter. Let us see why. Okay, remember that the response rates depend on the parameters beta 0, beta 1, and beta 2 in the logistic regression model. That is why it is an unknown parameter. In addition, the specific response rate we are talking about, pi, corresponding to a dose level, we don't know that. That is also an unknown parameter. In other words, if I look at a dose level D1 for drug 1 or D1 plus D2, whatever it is, the corresponding response rate is an unknown binomial probability parameter, right? So this quantity referred to as the interaction index will depend on the unknown response rate pi as well as the logistic regression parameters beta 0, beta 1, and beta 2. Again, of course, in a talk like this, we don't get too much time to get into the detail, but you can see we never used any model for the response from the administering the two drugs together. We do have a logistic model for drug 1 alone. Similarly, a logistic model for the response rate from drug 2 alone at a particular dose, but we have any model corresponding to the dose combination D1, D2. As I said, this is a very popular model, very widely used in order to assess drug interaction. You can see this can be extended if you're combining more than 2 drugs. If you're combining 3 drugs, there will be just one more term here. Any questions? Okay, let me continue. Now suppose, so we are saying in the absence of interaction, this quantity is equal to 1 because D1 plus D2 times all of this is equal to D pi 1. Now suppose the left hand side is less than D pi 1. What does that mean? So this means the interaction index is less than 1. Interaction index is less than 1. And what does that mean? So that means the combination dose D1, D2 required to produce a response rate pi is going to be less than the amount of dose when a single drug is applied to produce the same response rate pi. So to get the response rate pi, the combination dose required will be less than what you would require if only a single drug is administered. This is referred to as drug synergy, which is a good thing. So we say that there is interaction and they interact synergistically. Now what happens if the inequality is the other way? So if it is greater than 1, then the combination dose to produce a response rate pi will be more than the amount you need to use if you are using only a single drug, which is not good. And this is referred to as drug antagonism. That means one drug is somehow reducing the effect of the other. They are working against each other. And we say that the 2 drugs do interact, but the interaction is happening antagonistically. So here is the situation. So the interaction index D1 over D pi 1 plus D2 over D pi 2 equal to 1, no interaction. Less than 1, there is interaction, but it is synergistic. Greater than 1, again there is interaction, but it is antagonistic. And as I mentioned earlier, so this depends on the dose level because there could be interaction at certain dose levels, but no interaction at other dose levels. And the interaction index depends on the logistic parameters beta 0, beta 1, beta 2, and the response rate pi. So our problem is we want a confidence interval for the interaction index, and we will check if the number 1 is included in the interval. If the number 1 is in the interval, we conclude there is no interaction. Now, as I mentioned, I'm going to use the concept of fiducial inference for computing a confidence interval for the interaction index. You notice this is not a very explicit function of the parameters. So the interaction index, it is a fairly implicit function of the response rate pi, and the logistic parameters. Here's a quick introduction to fiducial inference using a very simple situation, the normal distribution, right? For anything, the simple thing you can think of is the normal. So let us look at the sample mean and sample variance based on a sample from the normal distribution. And we denote the corresponding observed values. That means once you have data, you can compute them. We denote that using lowercase letters. And we know the t statistic. Now, you think of capital T as a random variable. You equate that to the observed value of the t statistic, and you solve for mu. This is a very quick introduction without getting into any of the fine points or the technical details of fiducial inference. You solve for mu. If you solve for mu, the solution I will denote by the mu tilde that is given by this. So here, the lowercase x bar, lowercase s, they are fixed numbers, numbers computed from the data. Capital T is a random variable. So we will refer to mu tilde as a fiducial quantity for mu, and the percentiles of mu tilde can give confidence limits for mu, and they simply reduce to the usual student's T confidence limits. Nothing new here. This did not produce anything new. You can also do this for the normal variance. You look at the chi-square distribution associated with the normal variance. Basically, you suitably scale the sample variance and call that capital U square, which is chi-square, and then do a similar solution. And the solution denote that by sigma tilde square. We will call that a fiducial quantity for sigma square. And this will produce the usual chi-square confidence interval for sigma square. Nothing new here. So we basically showed that the student's T interval for mu and the chi-square interval for sigma square, they can be exhibited in a different way. That's all. However, suppose you have the log normal distribution. That means y is log normal. That means if you take the natural logarithm, it is normal. So you take the natural logarithm, once you have a sample, then you compute the sample mean and sample variance from the corresponding normal distribution obtained after the logarithm. And once you have the log transformed data, you can compute fiducial quantities for mu and sigma square, as I just showed you. In the context of the log normal distribution, an important parameter is the log normal mean, and that happens to be the exponential of mu plus sigma square by 2. Remember, mu is the mean of the log transformed quantity, and so is the variance sigma square. So if you want a confidence interval for the log normal mean, that means I want a confidence interval for mu plus sigma square by 2. The interesting thing is, you can obtain a fiducial quantity for this quantity eta. Simply replace mu and sigma square with the fiducial quantities mu tilde and sigma tilde square. And in the end, you can write the whole thing as a function of a standard normal random variable z and a chi-square random variable u square. The lowercase x bar, lowercase x, they are sample mean and sample standard deviation computed from the given data. So the lowercase s square is the sample variance, just a number. Now, it is very easy to compute the percentiles of eta tilde by a simple Monte Carlo simulation. All you need to do is generate a standard normal and a chi-square, and that will produce confidence interval for eta. Notice, eta is a function of, eta is a linear combination of mu and sigma square, not mu and sigma. If it is mu and sigma, the problem is easy. So this is now a combination of mu and sigma square. And the interval we obtain by this procedure, it is highly accurate, starting with sample size n is equal to 3. So the coverage probability is very close to the corresponding nominal level. So it's extremely handy, extremely simple, and extremely accurate. I mentioned earlier, there is a revival in fiducial inference, and it is mainly due to Hanig and his co-authors. A number of articles have recently appeared investigating the theoretical properties of fiducial inference. And a very important thing to remember is you can use that to compute confidence intervals for parametric functions that are kind of messy, and you want small sample inference. And that is where the fiducial inference becomes extremely useful. Now, we are not in the normal. We are dealing with the binomial distribution and logistic regression. Okay. I don't think I have too much of time to go through the derivation of the fiducial quantities. So I'm going to skip this. In case somebody is interested, let me know. I can share my slides with you, or I can share this article with you. However, let me mention that we have, right. So the this quantity, let me go back for 1 second. So the interaction index is a function of the logistic parameters beta 0, beta 1, and beta 2, and the response rate pi. So the way it is done is you compute fiducial quantities for beta 0, beta 1, beta 2, and pi. And that will give you a fiducial quantity for the interaction index. And then you can obtain the percentiles by Monte Carlo simulation. Very easy. I'm going to skip all of this. And so we will denote the interaction index by tau. And then you can, I will denote the corresponding fiducial quantity by tau tilde. Okay, we go through a derivation to obtain, again, we obtain fiducial quantities for the logistic parameters and the response rate pi. That will give you a fiducial quantity for the interaction index tau. We denote that by tau tilde. So you can compute the percentiles of tau tilde by Monte Carlo simulation, and that will give you confidence limits for the interaction index tau. So a lot of people have worked on the interaction index. There's a lot of literature available on the interaction index and various issues associated with the problem. And the usual solution is you use a normal approximation for the MLE of the interaction index, or you use a normal approximation for the natural logarithm of tau. So it so happens that if you use a normal approximation for the MLE of the logarithm of tau, that gives a slightly better, in terms of coverage probability, a slightly better confidence interval compared to the one based on the normal approximation for the MLE of tau. Okay, let me show you some simulation results. So I'm going to show you the estimated coverage probabilities and the expected length or expected width of the confidence interval based on the fiducial method, which I briefly discussed, did not get time to go through all the details. Then we will look at the normal approximation for the MLE tau hat and the normal approximation for the MLE for the natural logarithm tau hat. So actually we carried out extensive simulations. I will show you a little bit, a sample of the results. So we used the setup of the example. Remember, I started with an example. So I will use the setup of the example to show you some coverage probabilities and expected width. So for the example, the MLE of the parameters are like this: beta naught, beta 1, beta 2. So this will be taken as the true values of the parameters in order to carry out the simulation. And we used the original sample sizes corresponding to the example. I will call that scenario 1. And we also reduce the sample sizes and we'll call that scenario 2. Actually, scenario 1, the original sample sizes, they are actually reasonably large, and we cut down some of the sample sizes to look at a somewhat of a small sample scenario. So we call that scenario 2 to show you some simulation results. So here are the coverage probabilities and expected width for scenario 1 corresponding to the sample sizes in the original data. So remember, the interaction index depends on the particular dose level used. Suppose the dose level used is 0.5 and 50 for the two drugs. And let us say corresponding to this dose level, I'm going to use 60 mice. and suppose the true response probability pi is equal to 0.2. If so, then the fiducial method, you can see the coverage is pretty close to 0.95. I'm using a 95% nominal level. So the fiducial coverages are pretty close to 0.95. The normal approximation of tau hat, it is a bit short of 0.95. But if you take the natural logarithm, the coverage improves. The interesting thing is the expected width. You can see the expected width corresponding to the fiducial method is significantly smaller compared to the other two. In fact, sometimes it is even less than half. Look at this one. So the fiducial method expected width is about 0.4. The normal approximation is 0.87. If you use ln of tau hat, it is again 0.87. So basically, we are noticing the fiducial method gives you better coverage and smaller expected width. Better coverage and smaller expected width. Let us look at scenario 2. Same story. Better coverage and smaller expected width. So even though the normal approximation for tau hat, the coverage is actually much below 0.95. So if the coverage is low, we would expect the expected width to be small. It is not. So compared to the fiducial method, once again, the expected width for both tau hat and ln of tau hat are much more. So you are getting a shorter confidence interval and better coverage when you follow the fiducial method. Okay, I will just show you the result for the example. All right, so if you look at the dose combination, 0.5 and 50. So here are the confidence interval corresponding to fiducial method, normal approximation for tau hat and for ln of tau hat. You can see that again, the fiducial interval is significantly shorter compared to the other two. In any case, the intervals do include the number 1. That means the drugs do not interact at the dose level 0.5, 50. If you look at 0.5 to 100, then you will see that the intervals do not include the number 1, and at this dose combination, the drugs do interact. The normal approximation presents an issue. You can see that the lower limit is actually negative, even though the interaction index is a positive parameter. But anyway, still you can see fiducial method is producing an interval that is substantially narrower compared to the other two. So I presented you two situations. In the first situation, there is no interaction. Second situation, they do interact. Okay, let me show you a couple of references and I will conclude. There are 2 books that deals with drug interaction. This second book is very nice because it talks about various applications where you use drug combination and test for interaction when you use combination therapy for various cancer treatments. Combination therapy for cancer treatments. Combination therapy is very widely used for certain cancers, and they investigate that in this second book. And I have indicated some references here. And in case somebody has any interest in fiducial inference, I strongly recommend this second article here. It is a review article appeared in JASA 2016. So this is joint work with a graduate student and a colleague. I conclude here. Let me know if anybody got any questions.
Any questions? 1 or 2 questions may be asked. Questions or comments? Yes.
Well, if not, thank you once again for giving me the opportunity to speak in this session in honor of Professor Krishna Pillai. Great honor for me.
Sir, it's a good talk. And actually, the fiducial inference is new to me. And one thing, let me say that whether this interaction index, that The inference is similar to that of what we are using in logistic regression, right?
This is not limited to logistic. You can, in the discrete case, you can do in a logistic, Poisson, then logistic with a random effect, lot of applications.
Okay.
And in the continuous case, the interaction index can be investigated when the response is continuous.
Okay.
And what I showed you, the fiducial approach will produce a narrower interval with better coverage is valid there as well.
Okay. Thank you, sir.
Yeah. Dr. Kaul says, Dr. Kaul, I cannot hear you. I don't know if anybody can hear Dr. Kaul. Can anyone hear Dr. Kaul? I cannot.
No.
Professor Kaul, whether unmuted or
No.
Audio may not be working. His audio may not be working, maybe.
Sir, what about the volume of the?
Is the question? Can you type the question, Dr. Kaul?
Audio is on, but Professor Kaul is not here.
There is some disturbance.
Yeah. Okay. Now.
Yeah, Hanik is MSU graduate, right? Yes, I think you are right. I think he worked with that Scorod. Am I right? Yes, right. I think Hanik is an outstanding researcher. He has almost single-handedly brought fiducial inference into the mainstream.
Is there any more questions? So the time is over. Let us thank Professor Thomas Matthew for the nice talk, which actually made us to think in terms of the fiducial intervals and its use. He has used very simple statistics to study a big problem in biostatistics. We congratulate you, Professor Matthew, for your simple approach to study problems. Carry on. On behalf of the webinar, we extremely thank you for giving this invited talk. Thank you.
Okay,
Let us appreciate Professor Thomas Matthew with a big clap. Okay, the session is over. We move over to the next session.
Okay. Hello. On behalf of the Department of Statistics, University of Kerala, ISPS and KSA, I utilize this occasion to extend our gratitude to the speaker, Thomas Matthew, our alumni, as well as a great person in the area of biostatistics. And also Professor Yagin Thomas and Dr. Jagannath Krishnan for chairing this session. Now let us move to the next session. Can you? The next session is in fact dedicated to or to honor our Professor S.N. Roy, a great statistician of our country. And the speaker is our great Professor Hiralal Kaul. To chair this session, I invite Professor Hanagal, and to support him, Dr. Veena also. Veena is also our student, our alumni member, and she is very active researcher. Veena is here in the group. Hello,
Yes,
Veena.
I'm here.
Yeah, Veena, you please come forward and introduce our Professor David Hanagal, and thereby hand over the session to David Hanagal to continue the proceedings.
Okay, sir.
By the time I need to check whether Yeah, Professor Hira has something wrong with the microphone, so he has to correct it. Some problems associated with the microphone of that laptop or computer.
Okay. First of all, I would like to express my gratitude to this organization of this seminar for giving me this privilege to introduce Professor David D. Henniger. He is an expert in many research fields such as reliability theory, multivariate analysis, especially for exponential Pareto distributions. And, yes, so many.
Yeah, Veena, you continue. One thing, Professor Hira, Professor Hira, we are trying to check what is happening there. Don't worry about it. You can solve.
Okay. Professor David D. Henniger, he is a member of the Royal Statistical Society London since 2003. He has more than 120 papers to his credit, and he has served more than 30 years in Savitribai Phule Pune University. He has produced more than almost 10 PhDs, and is a visiting professor of universities in Mexico, Germany, and USA. He has attended many conferences, and it is our honor to have you here, sir, as a chair of this session.
Okay, thank you. Thank you for the nice introduction. And it's my, I think, Irakol. Irakol, can you hear me? Am I audible?
Yeah, I think Professor Henniger, he can hear what we are talking.
He can hear, no? He can hear.
But his microphone has some problem.
Okay.
Let's just wait some minutes more.
All right, no problem. I will introduce. It's my privilege to introduce Sir Hiranlal Kaul from Michigan State University. He's an alumnus of Department of Statistics, University of Pune. He did MA in Statistics with first rank from the University of Pune in 1964. PhD from University of California, Berkeley in 1967. He joined Michigan State University in 1968. He guided more than 25 PhD students and produced more than 125 research papers in well-known international journals. And his research interests are in reliability surveillance, time series, long memory process, inference in stochastic processes, non-parametric and semi-parametric inference, and so on. He got several awards and honors, namely the Fellow of American Statistical Association, Fellow of Institute of Mathematical Sciences, elected member of International Statistical Institute, President of IISA, International Indian Statistical Association, ISA, Indian Statistical Association, and we are very happy to hear his talk today as a keynote speaker. I welcome Professor Hiranlal Kaul. He's my good friend and friend of the entire faculty in the Department of Statistics. Professor Kaul, can you hear me? Professor Kaul?
Yeah. Let us wait a few minutes more, Professor. Because
Is it possible to sort it out from Trivandrum?
Yeah, we hope so. We got create problems, yeah. because of the I think that laptop or that computer's microphone has some,
Maybe he can change the laptop
or otherwise it may be due to the software issues.
Maybe sometime if he can remove and fix it again, it will work sometime.
Yeah,
Yeah,
maybe he can.
my son Nikhil is talking and doing some, yeah.
Maybe he can leave and rejoin again, maybe. That would be possible.
Anyway, these types of problems usually, occasionally, comes in our laptops also. I think so.
Yeah.
Yeah. Yesterday, while Richard Berg has contacted us to familiarize with the Google Meet platform, that time also this type of a problem arises. I hope we can manage it.
Can you hear me? Am I audible? Hello? Am I audible? Professor Kaul.
Hello, Professor.
There is some problem, I think, still. I think he can hear, or there is a problem of hearing also, maybe. I think
The problem is with the software, we can try to manage. I think so.
And we don't know what is the problem actually.
Yeah.
There are
mostly it could be with the setting of that this one.
Yeah.
Microphone.
Yeah.
Microphone setting.
Yeah.
Okay. He can Bala. He can hear you. He can hear.
Yeah, but we are not able to hear him now.
We can't hear him. That is the problem.
Sometimes these types of problems sometimes more files are.
Professor Kal, did you plug in your earphone?
Yeah, that he tried. Earphone he tried. Just before he tried that.
Okay.
To solve that issue.
Yeah, maybe he can use the earphone. I don't know. That is not a reason. Microphone is different. No, hearing there is no problem for him. But
yeah, there is no problem for the hearing.
Yeah, hearing is not a problem.
Yeah, he is trying to another. Where are the try?
Balakrishna.
Here.
Balakrishna, can you hear me?
It is
off. Audio is off, maybe, I think.
Both are unmuted, Professor.
Okay. Satish, what is the solution now?
Yeah, Professor, let us wait some more time because now it is, in fact, the session is at 7:15. Now 15 minutes.
We can give Chris time.
Yeah, we can adjust with the next.
Okay, Hira is now in another window. There is another window for Hira Kaul. Maybe he can you hear? Am I audible? Professor Hira?
It's audible to him. But
he is in another window. There are two windows.
Yeah, another yes, operated.
Sir, here.
There are two windows. Maybe he can hear from, maybe he can speak from another window, maybe.
Time, Professor Hanagal.
Yeah.
You can talk about the Professor S.N. Roy if you anything.
Yeah, there is a message from Hira. I can hear, but the thing is, we can't listen to him.
Okay.
Maybe if there is a mobile phone, one can speak the mobile phone also.
But that slide should be put in the air, or otherwise have to send to us. We can send from here, and he can using his mobile phone get present. That's another solution.
Yeah, mobile phone also is.
Hello, sir.
Hello.
Can you hear me, sir?
Yeah.
I think still there is a problem. It's not sorted out. He has written, maybe he can reschedule my session at later time. Satish.
Yeah, Professor.
He has written, there is a message from Hirakol.
Okay.
You can reschedule my session at later time.
Yeah, that we can do, Professor, if you need that. But the slot, I think it is better. I have to check whether the next session speakers are here in the group or not.
Maybe tomorrow, or tomorrow morning session or evening session.
In fact, tomorrow all the sessions are tightly scheduled. We can do at any time. We don't know. It's not a problem.
Okay.
Anyway, we need his talk. Don't doubt about that.
We'll wait anyway.
Yeah. I think let us wait for him some more time. And if he send the slides, if there is, it is available in mobile, there is network.
Maybe slides he can send, no? That is possible.
Send to us, and whether it is possible for him to.
No, he can display. He can display the slides.
Yeah, we can display from here. Yeah.
He can display the slides. There is no problem, and we can read it. No, there is no problem.
Yeah.
That is okay. Anyway, his son is there to help.
Yeah. Let us request to the next session speakers to adjust with some slightly.
Yeah.
Sorry.
Anyway, he may resolve. His son is there. He may resolve the problem maybe.
Anyway, we can try some more time, and if it is not possible, let us reschedule.
Okay. Anyway, his son is doing some.
Yeah, he's helping so that it will be solved, I think so.
Okay, maybe it may work. He has written some other time. Okay, let us see.
Earlier, we have scheduled today's time up to 10:10.
Okay.
And our Ashish and Gupta has some other issues, and there is some rearrangement.
Okay.
Consequently, the last speaker has to be put in the other his place, and we get a half an hour. That is why we the next time schedule up to 9:30. So if it is resolved, I think it is better to conduct the talk now itself, and we can extend the.
Okay. He has gone out somewhere, I think.
Yeah. Upon he's trying to use with the mobile also. That also has the same problem. Its mic is
maybe
microphone is.
There no, he is not using mobile. Maybe that is the reason.
Yeah.
He is not using mobile. I don't know. When I visited that time, he was not at all using mobile. Now I don't know.
Okay.
Satish,
Sir?
Can you speak to him by a phone or mobile?
Yeah, we are talking, Professor.
Okay,
we are doing. My son Nikhil is managing all those things now.
Okay.
Yeah, in parallel to this.
No, you talked to Professor Kaur?
Yeah.
No?
Yeah.
What he told?
They are trying to solve the issue.
Okay.
In the meantime, Professor Balakrishna also contacted me. The next session is he has to chair, but there is a electricity problem in his where he is staying in his house, I think so.
Okay.
And
internet problem.
Not internet problem, but there is no electricity at present.
No facility means?
No electricity.
Electricity.
So consequently, he wanted me he will join after getting that. By the time Professor Hanagel has to manage the next session too.
Okay, okay, all right.
In the next session, we have two speakers, Richard Burke and David Banks.
Okay, all right. Only thing is somebody can introduce, no? Somebody, two speakers, introduction of two speakers.
Yeah, we can.
That can be done because I don't have details.
Okay. Veena, Dr. Veena. Dr. Veena?
Yes, sir.
Yeah, Dr. Veena, you have to, by the time, in the website, there is the biodatas of Richard Burke and David Banks.
Okay, sir.
Their name, you click on their name, you will get their biodatas. Okay.
Okay.
In our conference webinar website. You take it and just to introduce them before starting. If Professor Balakrishna has not, or the Prasad, do we have Prasad? Dr. Prasad? If Dr. Prasad is here, no problem. Prasad University College. So Veena, you have to try to take their biodata by the time. Okay.
Okay, sir. I'm trying.
Okay.
Okay, sir. First of all, let me introduce Professor Richard Burke. Sir, shall I introduce Professor Richard Burke first?
Not now. You have to get ready by the time. Okay.
Hello.
Hello, Veena. Dr. Veena.
Hello, sir.
You have to make it ready to introduce. By the time we shall try whether to solve this issue of the Professor Hira, and thereafter at 8:05 we are scheduled the time of that session.
Okay, sir.
They will Richard Burke.
Sir, I think Dr. Prasad will also be preparing for this.
Oh, whether Prasad joined here in the group? I can't able to locate.
It is scheduled at 8, so maybe he will join at 8.
Let us wait. Even then, if he is not ready, you have to do that work.
Okay, sir. Okay.
That's good. If he is ready, no problem. We can give assign that work to him, because we already assigned in that way.
Okay, sir.
But Professor Bala has some problems with the electricity there in his house. Probably, yeah. Anyway, we have to wait some more time. Yeah, Richard Berg joined. Okay. Hi, Professor Berg. Professor Haneke?
Yes.
Yeah. By the time they solve the issues, Professor Hira will solve and his son, they are doing some work, try to solve the issue, that network issue or microphone problem. Let us start the next session.
I think it's solved now.
Yeah. So, Professor,
should I proceed?
Yeah, you are ready, Professor? Isn't it?
Okay, I am ready.
Yeah. Then, Dr. Veena?
Yes, sir.
Yeah. Prasad, hello, Prasad, Dr. Prasad? If Prasad is not here in the group, shall I invite Dr. Veena to introduce Professor Richard Berg? And
thank you very much.
Let me introduce Professor Richard Berg. He's a multifaceted personality. He's a professor in the Department of Criminology and in the Department of Statistics at the University of Pennsylvania. Professor Berg is an elected fellow of the American Association for the Advancement of Science, the American Statistical Association, and the Academy of Experimental Criminology, and has served on the National Research Council's Committee on Applied and Theoretical Statistics of the National Research Council and on the Social Science Research Council's Board of Directors. He has been awarded the Paul F. Lazarsfeld Award by the Methodology section of the American Sociological Association. He works on various topics in applied statistics, including causal inference, machine learning, and post-model selection inference. Among his criminology applications are inmate classification and placement systems, law enforcement strategies for reducing domestic violence, detecting violations of environmental regulations, and forecasting criminal behavior of individuals on parole or probation. Professor Berg is the author of over 150 peer-reviewed applications, including 15 books. His most recent book in statistics is Statistical Learning from a Regression Perspective. It is a privilege for us to have you here, sir. It's our honor to see your presentation.
Yes.
Okay.
Thank you.
Thank you. Professor Henagel, you please.
Yeah. Okay.
Yeah. Just to say,
Berg, can you hear me?
Yes, I can.
You can proceed for your talk. And okay, thank you.
Thank you very much. It's an honor to be here. I very much appreciate the opportunity to present some of this work to such a distinguished body. And I hope that this applications focused talk will be of interest to you. What I want to talk about is the use of interrupted time series analysis for causal inference. And the application will involve a ban on military-style assault weapons in California, and whether or not that ban affected...
Excuse me, Professor Richard, your slides we can't see. It's not visible.
You can't see my slides. Oh, let me...
No, we can't see the slides.
I have to move to the slide, Professor. Yeah.
Slides.
Huh.
Open the slides.
I don't know if I can fix that.
We can
according. Let me see. Gee, it says. To avoid mirroring, don't share your intent. I don't know how to fix that. I don't think. Let me try.
You can share and go to window.
Okay, let's try that. It says I'm sharing.
Sharing and go to window and the presentation.
Okay, I'll try again. Let me see. So I'm going to stop sharing. I'm going to
that small
window, then you can see the your computer.
Yes, I can. And now I'm going to click share.
Person, yeah. Now it is coming, person.
It's coming.
Oh, good. Okay, so
you have to open the Keynote.
Is that available now to you?
Not yet.
Yeah.
Well, this is strange because it says I'm sharing.
Sharing.
It says I'm sharing, and the.
Try to go to window.
I'm at the window that I need to be.
Window, you can click the window, then you can see the contents of your laptop.
Click on which?
Click on window. There is the entire screen is there and a window is there. Just click window.
Okay, I'll try it again.
Okay.
There, I clicked on window. Then I click on this.
Then you can see the contents of your laptop there.
Yeah.
There your presentation.
Yeah, now it is visible, Professor.
Now you can see it?
Yeah.
Okay, good. Can you see it now?
Yeah, now it is full screen. Very
Oh,
good.
excellent. Excellent. Sorry for my confusion. I've had trouble with this a bit over the last day or so. Anyway, you heard my brief introduction, I assume, on this front slide. So let me just go ahead. Just to give you some background, if you were familiar with these subject matter issues, I wouldn't have to do this. But I just want to make sure that we understand the motivation behind the analysis. In the United States, there are, as you know, a large number of suicides and homicides from firearms. There's some misunderstanding, though. It turns out that about 2/3 of these deaths from firearms are from suicides, not from homicides. So it's not just a crime problem, it's a public health problem as well. And it can get quite difficult. I live in Philadelphia in the United States. Last year, we had almost 500 homicides. That's 10 homicides per week by firearms, and over 2,200 people shot. That's 40 people a week shot with firearms. Philadelphia is not unusual. Firearm violence is common across the United States, but particularly in urban areas. So what am I going to cover? I'm going to first give you a review, I hope a review for most of you, on the canonical interrupted time series model that's used in statistics. I'm providing that because I'm going to argue that there are some holes in that approach that we need to fix. And then I'm going to talk about the application in a bit of detail so you know the subject matter. And then I'm going to argue that the standard model specification approaches in time series analysis are really an exercise in cherry picking. We have a post model selection inference problem, which is really a multiple testing problem, and I'll give you some ideas about solutions. And then I'm going to go into why, despite that, it's not clear that this intervention is properly defined, and then talk more generally about aspirations for causal inference and gun policies. In the United States, this is very important because there have been a number of efforts, legislative efforts, to restrict access to guns, and we have to know if it's going to be evidence-based, whether or not these interventions work. The bottom line, the conclusion from this talk is that this is very, very hard to do. The data on gun policy in the United States is spotty, often incomplete, and the statistical techniques that we have really aren't well suited to definitively address the policy questions that are raised. It's frustrating, but we have to approach these questions honestly. Statisticians need to jump in and try to fix the problems, and that's what with several colleagues we're trying to do. Now, here's the quick review. It'll take maybe 5 or 10 minutes. If you already are very familiar with this, I apologize, but I want to get everybody up to speed. The standard interrupted time series approach to causal inference is really very, very simple. And I set up this very, very simple illustration. Suppose we have the number of shootings per day on the vertical axis and day on the horizontal axis. And the way I've set this up on day 50, there's some kind of intervention. For example, police change their practices, and there is a sharp jump in the number of shootings. You can sort of see that visually in the time series. That's the blue circles. How would we approach this statistically? Again, this is the very simplest situation. You might simply specify a linear regression model or equation with two predictors. You might have a function of time, which picks up any trends over time in the number of shootings. And then you might use a step function, let's say a dummy variable coded 0 up to the point where the intervention occurs and 1 thereafter. If you run this regression and the disturbance term meets the usual least squares requirements, then you have an unbiased estimate of regression coefficient theta 2, which is the difference in the mean number of shootings before and after the intervention. This is the standard approach. It can be a very powerful tool for causal inference because in the function of time, you can pick up a variety of competing trends. They don't have to be linear. They can be nonlinear. They don't even have to be parametric. You can use non-parametric regression for that particular term. And you can remove, therefore, confounders which change gradually over time, which otherwise would give you biased estimates of the impact of the intervention. This is the simplest case. Unfortunately, the world is typically
Excuse me, can you hear Professor Hannigan?
No, there is some, he has unmuted.
But
he has unmuted. I think by mistake it is unmuted by himself.
Professor Berg, he is talking, but he's not aware that we are.
Yeah.
Professor Berg.
closed on me again. I don't know why. How's that? Can you hear me now?
Now it is
okay.
Well, I'll try again. Okay, let me go back.
Yeah.
Can you hear me now?
Yeah, now it is okay. You can hear.
Okay, so
maybe you can skip some slides.
Yes, I will.
Some slides.
I will go on.
Okay. It's okay.
We good?
Okay.
Yeah.
Okay.
Fine.
So this gets even more complicated because there are a variety of interventions that can occur. This was a plot that was produced by The Economist magazine. They do a pretty good job. The vertical axis is the number of background checks for firearm sales in the United States in millions. We have months on the horizontal axis. And you have various interventions overlaid. You can see them. The light blue line is the actual number of background checks. The dark blue line is a smoothed version. The reason why we're using background checks, we really care about sales. But it turns out that background checks are a pretty good proxy because we don't have direct information on sales. And that's because to sell a firearm in the United States with a licensed firearm dealer, they have to do background checks. So you can see that things get complicated because there are peaks and valleys. And here are some interventions. For example, the election of President Obama, there was an increase apparently in firearm sales measured by background checks. The Sandy Hook shooting was a mass shooting in a school in Connecticut in the United States. There was a spike then also of firearm sales. The San Bernardino shooting was a terrorist attack at a government building in California. Again, there was a spike. And there have been other spikes that have been represented too. Now, to unravel all of this and also account for the obvious trend in the data, we have to use more than conventional regression. And so we go to intervention analysis as originally laid out by Box and his colleagues in 1976. Their textbook, by the way, is in the 5th edition. It's really quite good. So what's the theory here? For statistical inference, as you appreciate very thoroughly, there must be some process, some stochastic process that we can assume that's responsible for the data. The conventional approach in time series analysis is to pose a general linear process where there's some observable outcome YT, for example, firearm sales, which is a linear combination of white noise perturbations with the lagged perturbations weighted by coefficients. We typically impose some constraint on those coefficients. In this particular case, I'm going to assume that the sum of the squared coefficients leads to a bounded process. And then we have the white noise residuals. As a consequence, we have a form of stationarity. The expected value of the series is 0, and the covariance between various observed values of y depends only on the distance between them in time, the number of days. Where in the time series the y occurs, in other words, arbitrary displacements of time, do not matter. That's the underlying formulation. One obvious problem is you can't analyze this directly because the white noise disturbances are not directly observable. Another problem, which I allude to in the bottom of the slide, is that this theory is just fine. In fact, it works quite well. However, in real applications, there can be difficulties translating the general linear process, which goes back limitlessly in time, to the real world. Under point 5, for example, I mentioned that the assault rifle that was commonly available, it is commonly available in the United States, which is basically a military style weapon, wasn't even available until 1973. So the idea of going back limitlessly in time is a convenient fiction. It's a fiction, but it's a convenient fiction. One important consequence of all this is that when we get to actually use this, we're dealing with approximations. And I can't emphasize that enough. There's no concern about whether the approximation of this true process is correct or incorrect in the usual model specification sense. There are no right models. There are no wrong models. There are models that we specify that we hope are good approximations, and we have diagnostics, but there's no such thing as model specification. And many models will fit the same data. So we're really in a quite different process than the standard in economics, where there is a right model and a wrong model. And that's going to lead to the problems that I'll discuss shortly. So what do we do in practice? The standard formulation in practice is to develop a parsimonious approximation of that linear data generation process. We specify a mean function, which has parameters, interventions defined in a manner I'll describe shortly, and those are located in time. And then we have a noise model, which is just a function of the residuals. You can see that the noise model is basically defined as the difference between the observed y's and the fitted values from the function. And we have an ARMA noise process that's commonly applied. I've given it sort of in standard notation. I can unpack that a bit more if necessary. The white noise process that is now referred to, A sub t, is a new perturbation, not those epsilons we saw earlier, which results once basically you filter out the dependence in the disturbances. So how do we specify the mean function? Typically, there's no subject matter or statistical theory, which tells us there are lots of different options. I've laid out some here. We can define our interventions as either a step function represented by S, which is coded 0 up to the intervention and 1 thereafter. Or we can code the intervention as a pulse, which is a single value of 1 when the intervention occurs, otherwise 0. And depending upon other terms, we can get different characterizations of the causal effect. Change in level, a spike, change in slope, a spike with a decline, a gradual change in level, all depending upon how we specify that mean function. And again, I have to stress, there's no subject matter theory which tells us which is right. Basically, we have to explore the data to determine this. And that's standard practice in this field and has been that way for 50 years. The noise model can get quite complicated, but it really isn't all that important because all we're interested in is taking out any residual dependence in the disturbances. Turns out it's common to use multiplicative seasonal models. I've shown you one there, which is the one we're going to use. You can see that on the left, we do some differencing to take out any fixed trends in the data. In this case, a linear trend at a lag of 1 and a linear trend at a lag of 7. Why 7? Because we're going to see our data are for each day, and the same day of the week over time is going to be more alike than different days of the week over time. It's multiplicative, which means that we have an interaction effect built in, which is the dependence at a lag of 1 in the disturbances varies depending upon day of the week. And at the bottom, I just showed you, for those who have forgotten, how the multiplicative backward shift operator leads to the seasonal differencing model I've just shown. I have to stress there's no theory in statistics or in subject matter which tells us this is right. Turns out this is going to be what we use because it seems to work. But again, we're really just looking at parsimonious approximations. So here are the data. We have by day the number of background checks in California over a period from 1996 to 2018. In contrast to the simple example I started with, this is a mess. It's a mess because there are big peaks and valleys, as you can see, and you can see a sort of hole in the bottom. That has to do with the way the data are collected, and I don't really have time to go into it. Turns out it's not a problem because we can address it with our formulation that we use shortly, but it visually creates problems. I should add that we're going to not use a Poisson regression type formulation, even though these are counts, because our mean is large. It's 729 sales or background checks per day, which means that we have a pretty good approximation of normality. And I give you a citation to the right and showing you a normal plot that the normal approximation for these count data are quite good. So what are we going to do? Here's an example in a histogram of that distribution of gun sales. Pretty ugly. We have a long tail to the right, which is those peaks I mentioned earlier, and it drops off quite quickly as a function of things like holidays when gun sales are not made. So what are we going to use for interventions? We looked over a variety of things that happened over that period of time. There were many legislative changes, and we culled some of them, which we think, before looking at the data, are going to help us understand gun sales. This is a correlation matrix plot. The darker the blue, the larger the positive correlation. The darker the orange, the larger the negative correlation. And you can see in the top row that we have some variables, some predictors that are related to sales. But if you also look a little bit farther down, you can see that these interventions, which I'll describe shortly, are related to one another positively. That's going to create some dependence problems among the estimates. We have some basically collinear difficulties that we're going to have to deal with, and we do. Let me quickly describe the interventions. One is a ban on assault weapons towards the beginning of the time series in 2000. I show you a picture of an assault weapon. It's a military style weapon, basically modeled on the AK-47. There's no reason for civilians to have this. But in the United States, they are legal, at least in general, until this ban. Then we have another intervention, which is other legislation, a ban on big caliber weapons. That's a 50 caliber assault weapon. It is used by snipers in war. It's effective at a distance of a mile. There's no reason for citizens to have this. They were on sale briefly, but then they were banned. A third is a ban on rimfire pistols. Rimfire pistols are small caliber weapons, 22 caliber, that you wouldn't think would be a horrible risk to public safety, but it turns out that they have large magazines and can carry a large number of cartridges, so an individual can fire many close together and therefore can be fatal. That was banned as well. Then we have something called the Harriet decision, which is a legal decision, and I won't bore you with it because I don't want to spend the time on it right now. Then we have some mass shootings because there is anecdotal evidence that people buy guns out of fear when there are mass shootings. There's the Los Angeles mass shooting, which killed a very large number of people in Las Vegas. The San Bernardino mass shooting, the terrorist event in California, which killed a large number of people. There was another shooting in Orlando, Florida. And these are just ones that are selected that are appropriate given the time frame we're talking about. We then include the Obama presidency and the Trump presidency, because again, there's anecdotal evidence that affects gun sales. People who are afraid of losing access to guns with the Obama election went out and bought guns, at least anecdotally. Trump didn't matter much. They figured their gun rights were safe. And at the very bottom, we take into account things like days of the week. I should stress that none of this was examined before we proceeded, because that would have been data snooping, providing this here so you have some background for our analysis. So we fit the data with a time series formulation that I described earlier, with interventions I'll mention again quickly. As a sanity check, you can look and see we fit the data pretty well. We get the time trend, we get many of the spikes and valleys, hardly perfectly, but quite effectively. So at this point, at least, it makes sense to continue and see how well we do. Look at more diagnostics. Standard practice in the specification of interrupted time series estimators is to look at the autocorrelation plot of the residuals. This looks scary at first, but actually it's not. The vertical axis are autocorrelations. The horizontal axis is lags. You can see that the largest autocorrelation is less than 0.1, which is tiny. And experience indicates that with autocorrelations less than about 2, it doesn't materially affect the results. Most of the autocorrelations are much, much smaller. Now, with the very large number of observations, 8,400, we have unnecessary power in our statistical inference. You can see the confidence interval is very narrow, plus or minus a correlation of about 0.02. It's really not relevant for our decision. The bottom line is that most analysts looking at this data, most statisticians, would conclude that we have approached the white noise disturbances with our estimates from the residuals once we apply our model. This is good news. It says there is no more structure left that we haven't already taken into account. That's not to say that our model is unique or right. It just says this approximation turns out to be a good one. I'll go through this later. Basically, it says that we get a good approximation of the sampling distribution of the assault weapon ban indicator, again, saying all is well. How we got this, I'll talk about shortly. So let's look at the results. Just focus on the red coefficients for a moment. You can see that during the Obama presidency, gun sales fell, again measured by background checks, by 462 sales, increased by 462 sales per day. During the Trump administration, they increased by 42 a day. It's immaterial. It doesn't really matter. During holidays, when gun shops are likely to be closed, gun sales drop by about 714 per day. After the San Bernardino shooting, which is the intervention we included because it was the only one in California, gun sales increased by 838 per day for the whole state. And finally, for the assault weapon ban, we find a decline of approximately 633 sales per day. You would look at those coefficients and say, those, with the exception of the Trump presidency, are large and of subject matter interest and of policy interest. If you look at the T statistics, they're all large. We would normally use a T value of something like 1.96 or minus 1.96. So all of these effects that I've just described would conventionally be described as statistically significant. Now the complications begin. I'll talk about max T in a second. The complication is that to specify this model, notice I had to use diagnostics. This meant that I had to review a large number of plausible approximations. I reviewed 27. So the results you see here are a result of data snooping. I looked at 27 and picked the model I liked best. There's now a large literature on post-model selection inference, which basically concludes that your T statistics and their interpretation and probability metrics is bogus. One way to adjust for this is to treat this as a simultaneous inference problem, which has been studied in statistics for 50 years. But applied to this setting, we have a variety of new results and approximate ways to fix the problem. The easiest way to approach this is to treat this as a Bonferroni problem and apply the Bonferroni correction. It's not ideal, it's very conservative, but we have such a large sample that it may not matter. If you apply the Bonferroni correction, we need a threshold now of 2.87 or minus 2.87, which is effectively a critical value of 0.002, even though we're using, we thought, a level of 0.05. And if you apply that, all of our statistical inference still leads to a rejection of the null hypothesis, with the exception of the Trump administration period. Now, this is a very conservative approach. A better approach that's been available for some time is the max T correction. It turns out that it doesn't matter much in this application, but if you're unfamiliar with it, it's a really useful tool. Let me tell you quickly how to calculate it. We have 27 models. We generate a bootstrap sample of the data, and I can talk more about this particular bootstrap that we used, although we're still sorting out whether it's fully appropriate. We generate a bootstrap sample. We look at all of the 27 models. We look at the T statistics for the intervention we care about, which is the assault weapon ban, and we store the largest T. We move on to the second bootstrap sample, estimate 27 models, pick the largest T statistic for the intervention we care about, and save it. Over 100 bootstrap samples, we have 100 maximum values of T over all of the models. We then can calibrate that as usual with quantiles, and then our statistical inference proceeds from those quantiles, which, for example, mark the top 5% and the bottom 5% of that distribution, or the top 1% or the bottom 1%. This gives us valid statistical inference asymptotically and is a preferred method to the Bonferroni approach because this is not conservative. Okay, it takes into account that there could be, and in this case there are, dependence across models in our estimates of the parameter for the intervention of the assault weapon ban. I can give more details if necessary. Another advantage of this approach is we get bootstrap estimates over all models and all bootstrap samples of the assault weapon ban. And the good news is that 93% of the time, that coefficient is negative. So while it isn't ironclad that we had a reduction, if you looked at this and you wanted to be a little bit careful about over-interpreting the exact point estimate, you can see in this instance that by and large, the evidence is consistent with the reduction in firearm sales, particularly handgun sales, when we use this approach that I've described. But now it gets really uncomfortable. We have, in our approach to the multiplicity problem, looked at 27 models. That means there are 27 estimates, which is clear from what I've just described. But you must appreciate that there are now 27 estimands. We are estimating 27 different parameters for the causal effect. That's because no matter how you specify the model, each new model specification, each new approximation defines the estimate differently, necessarily. That's in the math. There's no arguments. The difficulty is we have a single causal effect that we're trying to estimate, which is a reduction perhaps in firearm sales, but we have 27 different definitions of that causal effect. The inconsistency is unresolved. We don't really know how to handle that yet. I'm working with a number of individuals who specialize in causal inference, and we're trying to figure out a way to make this work. But right now, that's an unsolved problem. And it's a really serious problem because conventional time series analyses, even up to time series, requires data snooping to arrive at an acceptable approximation, which in turn leads to many estimands, which are used to get estimates, which completely undercut any simple interpretation of the causal effect that you're trying to arrive at. And in this case, it gets still messier. I've been playing a little bit fast and loose here. The assault weapon ban is only on assault weapons. But the background checks that I described are for all weapons, primarily in this case, handguns. So we have an intervention to prevent the sale of assault weapons, but the outcome is really handgun sales. Why would a ban on assault weapons affect handgun sales? Now you can speculate, and people have, for example, concerns about access to weapons in general in the United States, but the mechanism by which the intervention is supposed to work is not clear. The timing is not clear either. This particular ban on assault weapons and most gun control or gun policy interventions in the United States are very, very controversial. As a consequence of that, there's publicity as the interventions are being considered when they're debated in the legislature. They're covered in the newspaper, they're covered in television, they're covered in all sorts of media. So if you're concerned as a citizen about access to firearms, those concerns can begin well before there's actually legislation. When the legislation is introduced, it's discussed at public hearings. The legislation is then voted on, and before it can become law, a governor must sign it. And then usually several months later, in this case 2 months later, the actual legislation is implemented. So there's actually a period of about 1.5 to 2 years when these issues are being raised, where concerns about access to weapons might be a salient concern for citizens. So when does the intervention start? It's not clear. There are also, this is my third point, other complications, because over this period of time, there was other legislation in California, not directly aimed at the restriction of firearm sales, but other things which indirectly may affect firearm sales. And they can't be taken into account. They're just simply, there's too much dependence among estimates of those different effects. So there are confounders that we have to worry about. I already mentioned the collinearity among the predictors, which in time series analysis is often a problem. I can elaborate on that as well. And then of course the results are not unique. So, conclusions. For the effect of the assault weapon ban, despite the fact that that ban was very popular in many political circles and is still very popular, although there's been litigation challenging it, we really can't tell for policy purposes or for subject matter purposes whether the ban worked or not. If you move the ban further or back in time, couple of months, you can change the effects dramatically and make them disappear, which says we not only don't know what the mechanism is, we don't know what the timing is. There are also, even for simple applications, simpler than this, these post-selection inference problems, what's sometimes called POSI, which we in principle can solve with a multiplicity correction, but in turn leads to further complications because we have multiple estimands. We therefore don't have a nice way to get from the solutions that are available statistically to causal inference that we agree makes sense. Now, there have been a number of suggestions in the literature lately about ways to change the modeling approaches. I've listed some authors here. It turns out that those require very demanding assumptions that in turn rest on subject matter knowledge that we typically don't have, so they probably won't help. And I should stress that the problems I'm laying out here are problems